In this video, I'll present an overview of how to debug code using the Java JDB tool. So we'll start with the Java Platform Debugger Architecture, the JPDA. This allows for the implementation of debugging tools for Java in a cross-platform and remote fashion. It provides a reference implementation and a modular architecture for debugging Java. The JDI, or Java Debug Interface, is implemented so that debugger clients, IDEs, tracers, and monitoring tools can connect to the debugger architecture. Once inside of Java debugging, whether from the command line or from an IDE, it's essential for Java to open up the tools to micromanage execution. This is done through stepping, one line at a time, and choosing whether to step into a function or step over it, getting the result while continuing the line-by-line fashion of the current method, setting breakpoints, and running code until a particular line or function is reached, and allowing for the analysis of the current state of the program and variables when an exception is thrown. What are some of the common debugging methods? Well, we can attach to a specified class. We can use comments in the program's source code that can help identify expected behavior so that you can test and work towards what's defined. You can debug code directly. You can debug on demand through the use of breakpoints. You can debug the Java bytecode, debugging the compiled Java directly, as you would do for machine code in compiled languages. You can debug in the JVM language, and remote debugging, so attaching to a running program indirectly through a service, hook, or API. How do we do this with Java debuggers? Well, we can do it through the command line debugger, the JDB, through Notepad or VI, where you focus on the output of stack traces or exception information when a program crashes or throws an exception. Using IDEs, such as IntelliJ or Eclipse, using their built-in debugging tools. And you can use another standalone debugger, a non-JDB or non-IDE, such as the Java Platform Debugger. So how do we handle JDB in the Java Development Kit? Well, we have the Java Virtual Machine Tool Interface, or JVM-TI. This allows for the JVM to provide inspection and debugging of the running state of a Java application. Then through the Java Debug Wiring Pool, or JDWP. This is the back-end debugging process, and the JDI, or Java Debugger Interface, sits on top of the JDWP to facilitate communication with the JVM for debugging. Java debugging with JDB doesn't require any special installations. However, you should verify the Java installation, including the JDK and JVM versions, especially if you're running the debugger outside of your development environment, perhaps on a staging server or pre-production environment. Setting up the Java environment by making sure paths and environment variables are set, such as Java Home, and verifying the JDB installation directly, just by running JDB. Now, what's the syntax for the JDB from the command line? Well, there's the JDB command itself, which we execute by running JDB in lowercase as the command. And the options follow that, such as the class path, the -x, -d, attach, launch, or other common options. The class name we want to debug, and the arguments we're passing to the program. That is, the string args passed into the main entry point into our Java application. So the options with the JDB command, what are they? Well, we have the help command to get details on the JDB command itself, the attach command to attach to the JVM by address, the list any command to connect to the VM using any address, the tclient and tserver for the Java hotspot VM client and server. So in a Java JDB session, we add it to a class or attach to a class, and we add it to the running JVM. So this is what facilitates our JDB session. And we can get information, pause the program, set breakpoints, and step into and over our code. How do we do this with the JDB basic commands? Well, inside of JDB, once JDB is running, we can use help or question mark to pull up the basic commands for JDB. The main ones include the run command, to start execution and specify a class name with the entry point and program arguments. The cont or continue command to continue execution from a breakpoint when the program is paused. The print command to print the value from an expression. The dump command to print all object information. The threads command to list the running threads. And thread to set the default thread. And where to dump a thread stack. And that concludes this presentation on Java debugging with JDB. In this video, I'll demonstrate how to debug code using the Java JDB tool. From a terminal window, in this case I'm using the terminal client built into IntelliJ, I can run the JDB command of my example Java code here in debug demo. I'm running this from IntelliJ from the terminal window, but I can do this from any shell client or terminal window. The terminal window built into IntelliJ makes it convenient because I can display the code just above and take you through the code and run JDB to run this program from the command line. And we can use the debug commands to step through it line by line. So this main.java file starts with package com.example, then public class main for the main class declaration. And this class has two methods, handle string and the main entry point into our application, the main method. So I'll start with handle string on line 5. It's declared public static boolean handle string, and it declares a parameter string str. It checks if string is equal to null or str.length is equal to 0. And if it is, so if it's empty or a length of nothing, it'll call system.out.println with the string is not okay, and return false. And then outside of the if block, so if the if statement does not succeed, it continues executing, calling system.out.println, the string is okay, return true. Then main is declared on line 14, public static void main with string double brackets args. I'm going to use two arguments. The first argument is expected to be a number, an integer, and the second a string. So on line 15, I have int I equals integer.parseInt of args0, and string a equals args of 1. On line 20, I check if I is greater than 0, call system.out.println with I, and then we concatenate the value of I. On line 25, outside of this if block, I have boolean b equals handle string with a as its argument, and on line 26, I call system.out.println of b. Now from the terminal window, I need to run JDB -source path, so I need to specify where the Java source file is. And that's up directories in .. will get me into the main debug demo project folder, and then into the source folder /src. And under that, it's in com.example. But I don't need to specify the full package name, just the main root source folder. And now JDB needs the class com.example.main and the arguments 1 and test. And once I'm into JDB, I'm going to set a breakpoint. I'm going to say stop in com.example.main, so capital M for main, the class, .main, the method, so all in lowercase. And now run. So it shows me the line. Without the source code or without specifying the source path, I wouldn't see the actual line, the code on the line. I would just see the line number. So it tells me breakpoint hit, thread equals main, com.example.main.main, line 15. So now I can type step, and I can see each line as it's executed. I can type list to show me where I am in the code at any given time. So it shows the code. And I'm on line 20 for the if I is greater than 0. I can type print and a variable name, say print I, will print the value of I, print A, which gives me test for the second argument. Now there's another variable down the line called boolean b. If I type b at this point, it's just going to say b equals null and give me a parse exception because the debugger or the source code hasn't gotten that far yet. Now if I keep typing step, it will show me the line. If If I execute a line that prints, it shows me the output, so I:1 from line 21. Now in line 25, has boolean b equals handle string. Now if I type step, it will step into the handle string method. So step by default is step into. I've typed step to the next line of code. I have to type where, and it shows me that I'm inside of handle string on line 6 with the if str equals null or str length. So at any time I can type where and it'll show me the stack trace. If I type step, it will keep executing. And then I set the value b, type step, and it shows me it prints true. And if I step right to the end of the program, it will exit the program. So once I reach the end of the main method, I'm going to arrow up and run JDB again. And this time I'm going to change the values to 0, and I'm not going to enter a second argument. I'll type stop in com.example.main.main, run. And now if I step and then step over the second argument, it gives me an array index out of bounds exception because the second argument wasn't passed, and it can't get anything from args1 because it doesn't exist. So I can see where this exception occurs, and if I try to type step, it gives me the full exception in thread main and exits. So we can see exactly where the exception happens. We can examine variables around it using print. We can examine the call stack using where. And I'm going to run it one more time. This time I'm going to give it the value 0 and Steve, stop in com.example.main.main, run. Instead of using step, I can also use next. So next will step over. So if I get to handle string line 25 and I type next, the debugger won't go into handle string method. It will step over it to the next line and just get the result. And in this case, it prints the string is okay from inside of handle string, so I see that much. And also if I type cont for continue, it will continue executing until it hits a breakpoint or it reaches the end of the program and the application exited. And that concludes this demonstration on debugging with JDB. In this video, I'll present details on how to debug code using IntelliJ. I'll demonstrate this with an example in the video titled IntelliJ Java Debugging, but I'll give you the high-level description in this video. So let's talk about debugging code using IntelliJ. So we launch a program with the debugger attached with IntelliJ's internal debugger. This interfaces with the program and provides information about what's going on. You can put in breakpoints and perform all of the functions you would when running JDB from the command line, and you'll find out what's happening under the hood right inside your IDE. This facilitates the detection of problems, and it makes fixing bugs easier. You can choose where to pause your program, when to query its state, to check the state of variables and objects, and threads and the current stack trace. How do we execute code in debug mode? We invoke context actions by using Alt-Enter and choose Debug option. We click the Run icon in the gutter area and select Debug option, or from the Run menu, or by pressing Shift F9, the default hotkey. When we debug code using IntelliJ, we can pause the program and resume either line by line or until the next breakpoint. We can restart the program entirely. We can resume or continue executing after being paused. And we can stop and end the program at any point. How do we set IntelliJ breakpoint? Well, when we set a breakpoint, it stops the execution of the program. It allows us to analyze the state of code at that point. And when we set up a breakpoint on a line of code, we click in the gutter area in the left side margin of the code next to the line numbers and a small visual indicator. Usually a tiny red circle will be put there where the breakpoint is going to occur. We can use the shortcut key, the Control F8 on Windows or Linux, or Command F8 on Mac OS. What's in the IntelliJ debug window? we get the list of stack frames, the current call stack, console window with the program's output, the threads associated with the program, the step action icons to click and step through code, and we get a variable pane to display the contents of the active variables that are in the current scope. What does our IntelliJ debugging procedure look like? We define breakpoints where the program needs to be stopped. So we set a breakpoint that will manually suspend the program when it reaches the breakpoint. When we launch the program, we select debug mode to launch it in debug mode, and we use the debugger to get information about the state of the program, information about variable values, running threads, to test our program in various conditions, and use the stepping feature to step into functions or over functions and execute code line by line. And we can also fix without terminating sessions within the IntelliJ IDEA. So we can adjust code and reload on the fly, continuing from where we left off. What are some IntelliJ debug tips? How do you debug non-responding applications? We can do this using pause to try and get state information to identify the source of the issue and evaluate expressions and variables. And always remember to take care of your pre-launch tasks. This means making sure you've configured or enabled other services required by your program, such as web or network services or APIs, database connections, and other data you need to load or connect to during the running of your program. And that concludes this presentation on Java debugging with IntelliJ. In this video, I'll demonstrate how to use IntelliJ's Java debugging tools. I'll start in this project, which I've called Debug Demo. Inside of main.java, I start with the line package com.example and add it to this particular package. Then on line 3, I declare public class main, and then inside of this class, I have a couple of methods. One is the main method, and another one is called handleString, which I use to execute a few lines of code so that I can demonstrate debugging inside of IntelliJ. So on line 5, I have public static boolean handleString, and it takes a string as an argument, so I declare the parameter string str. Then inside the body of this function, I have if str is equal to null or str.length is equal to 0. So if the string is empty or null, I print using system.out.println, the string is not okay, and I return false. Then outside of the if statement, I have system.out.println, the string is okay, and I return true. Now in line 14, I have public static void main, string double brackets args. On line 15, I have int I equals integer.parseInt of args at index 0, so the first argument. And line 16 has string a equals args of index 1, the second argument. Then I check to see if I is greater than 0. So if it's greater than 0, I print I and the value of I. And then outside of the if statement on line 25, I have boolean b equals handleString, so I call the method with the argument a, and then I print the result b, so system.out.println of b. Before I continue with the debugging, I want to check my run configuration. So from the run menu, I'll select edit configurations, and then in the build and run, there's a command line argument section where I put 5 for the first argument and Steve for the second argument. So I can edit those here in this menu, select OK, and now I'm going to set some breakpoints. I'm going to put one on line 15, the first line inside of my main function, and if I do Control F8 after it's been set, it will remove it. So Control F8 toggles the breakpoint on and off, or I can select the margin area, the gutter area, by clicking. I can click on the line where I want the breakpoint. So I'll set a breakpoint on line 15 and on line 25. Now I can run the code in debug mode from the run menu by selecting debug main, or I can go in the toolbar and select the debug icon. In this case, it's a green bug, or I can type Shift F9. In this case, I'll just click the button, the icon in the debug menu. It starts executing and stops at my first breakpoint on line 15. And immediately we see that we have a variable set, the args variable. We could see it in the variables section in the bottom panel in the debug panel. And there's also icons here if I want to step into or step over, step out. So all of the actions to step through the code line by line are here in the debug panel. I can also use the shortcut key, the F8, and it will step over line by line, and each step along the way updates the variables. So I have args I, a at this point. And here the test is if I is greater than 0, and in this case it's 5, so it should print. Now if I want to see what's printed, I'll have to go from the debugger panel to the console panel and see I5. And I can go back and forth between debugger and console. I'm going to use F7 to step into the handle string method. And once I'm inside, I can continue using F7. And in this case, the string is Steve, so the str variable is set to Steve. So it should print the string is okay and return true. And I can continue to step. Now at any point, I can resume the program with F9, and it will continue executing either to the end of the program or until it hits another breakpoint. And I can always check the results in the console where it prints my results, such as the string is okay and the true that's returned from the function handle string. And that concludes this demonstration of IntelliJ's Java debugging. In this video, I'll describe some of the best practices when debugging code in Java. The first thing we need to take care of are Java breakpoints. Where do we set Java breakpoints? We can set conditional breakpoints based on conditional if statements, inside of if then else blocks, exception breakpoints, ones that occur when an exception is thrown, watch points based on the value of a variable, and trace points. How do we take advantage of the Java debugging features we have available to us? Well, we should be looking to do things like drop to frame, which means to jump back to a point in your stack frame at a particular level in your call stack. In the Eclipse IDE or IntelliJ, this enables you to choose any frame. We should be using step filtering. So we can skip certain packages, and we can filter out JDK classes from the step into. So stepping into enters a method, which is usually fine for methods in our own source code, but most often we avoid stepping into the JD class code itself. And we can be using shortcuts. You should know the hotkeys, the common hotkeys for stepping into functions like F5, stepping over F6, and running until the next breakpoint, F8. What are some best practices when debugging code in Java? What can we do? We can evaluate expressions and variables along the way, set breakpoints to carry out the evaluations at critical points or uncertain points in the code that you may need to examine. Environment variables and their contents. Make sure they are consistent across different environments, especially if the program is deployed to multiple locations, such as an array of servers or cloud computing environment. Modify the value of your variables directly from within your debugger, so you can set a breakpoint and change the variable's value from the debugging tools and see how the program responds. This is a very handy option for testing hard to reproduce errors. If you need to test a particular failure code that might be returned from an external API or resource, you can set a breakpoint when the call happens or just after the call happens, change the result, and see how your program responds. What about resolving deadlocks in Java? Well, this is when two or more threads are blocked. When the threads are blocked permanently, we call it a deadlock. This is a cyclic dependency of threads. For example, thread A will be waiting for a resource that thread B has, and thread B is waiting on another thread C, but thread C is also waiting on thread A. So at this point, nobody can proceed, and we call it a deadlock. Using JStack on deadlocks is not always fruitful. These errors do not exhibit symptoms of common problems, such as spikes in memory or CPU or some OS metrics that let us know that something is not working properly. Sometimes the memory and CPU are all at a minimum, but we're still blocked and we're still stuck in this deadlock. We may need to turn to external solutions, such as application monitoring solutions and using advanced debuggers and commercial APM tools to track down these problems. I've been in this situation before, with deadlocks happening in production environments, but we couldn't reproduce it in testing. This ended up requiring a manual reset every few hours to avoid these deadlocks for months before we could finally track down the issue and resolve it. We can also do remote debugging in Java. This allows you to debug Java code running on another machine. Most IDEs support remote debugging, such as NetBeans, Eclipse, IntelliJ IDEA, and Visual Studio. What are some common debugging code tips in Java? You can use your IDE to copy the stack and save the results. This might be necessary for debugging multi-threaded programs. You can suspend and resume individual threads, which might be necessary for debugging multi-threaded programs. Use the step into feature to go into a function and the step over feature to step over a function call and just get the result if there's no need for you to go into a function every time. This is especially handy if you have a loop that calls a function and you don't really care to go in and on each iteration of the loop, but you just want to examine the result each time it calls the function and stay within your current context, your current scope, and debug the code locally, and stay under the step return option. And that concludes this presentation on Java debugging best practices. In this video, I'll present some of the common syntax and logic errors that are made in Java code. Errors in Java fall into two main categories. Syntax, which covers the language used to create code. A syntax error is when the language is used incorrectly. Compiler will catch most syntax errors. If you use a keyword in the wrong place or in the wrong way, your code most likely won't even compile. It does not cover mistakes in logic of the program itself. So logic errors are different. Logic errors is where the code isn't performing as expected. It can be difficult to find and time-consuming going through code to find a reason for a logic error. If you have a conditional statement, an if statement, that performs some comparison in the wrong way, your code won't execute as expected. What are some common syntax errors in Java? Unintelligible commands, not following the prescribed format. Java has its own syntax. You can't use syntax from other languages. You can't use Objective-C or C++ in Java. It just won't work. There is some overlap, but you have to make sure you're writing actual Java keywords in the format Java wants. You'll get compiler errors, and most syntax errors will be detected immediately. If you're using an IDE can pick them up as you type them. Syntax errors rarely make it to runtime errors, but it can occur. So a syntax error that results in a runtime error is often not detected until the program is running. And in the case of a runtime error, it's usually a case of a typo or using the wrong keyword mistakenly. Let's say you use the continue keyword when you mean break, or you apply the wrong keywords, but otherwise, syntax errors are most likely to result in compiler errors. What are the common syntax errors in Java? Forgetting to import a class, missing parentheses, splitting a string over two lines without a concatenation with the plus character, treating a static method as an instance method, and using incorrect capitalization. And some more common syntax errors in Java are forgetting the class or object, missing curly braces, mistyping the header for the main method, not declaring it correctly, omitting the break clause from a switch statement, and omitting a return statement. Now, omitting the break clause from a switch statement can also be considered a logic error depending on how you use it, but errors of omission typically fall under syntax errors. Now, what are some of the common logic errors in Java? Assuming a condition is true, defining the wrong count, using incorrect operator precedence, as well as misplacing a semicolon, relying on integer values when values might be strings or floating point values, relying on floating point numbers when values might be integers or possibly null or string values or some other numeric type. And that concludes this presentation on Java syntax and logic errors. In this video, I'll describe some of the important aspects of Java's exception handling. One of the often overlooked and underestimated features, especially when you come from a language and are used to languages like C, where you use return codes from functions or error codes or even goto statements for handling exceptional events. An example to keep in mind for exception handling is if you're trying to connect to a service that's unavailable, and you get a failure in the response, or the connection drops, and then an exception is thrown so you can handle it based on the content of the exception. So exception handling gives you the ability to alter the flow of code in a structured way, so that the logic is easy to follow, the content of the exception is obvious, and the handlers are defined in a consistent way. So where does this come up? What sort of exceptional events require exceptional handling? Well, if you try to open a file that can't be found, if you try to make an internet connection and it drops on you, especially if it drops before the transmission can complete, or if your system doesn't have enough memory. How will your program fail in this case? We can handle this better through an exception hierarchy that classifies our exceptions in 3 ways. The first is checked exceptions. These are exceptions that have to be handled. Your program won't compile unless these exceptions are caught. So this allows you to plan ahead, handle or declare when writing code, and detect problems before runtime. So before they're found when the program is running, you find them at compile time. Unchecked exceptions, also called runtime exceptions, because they happen when the program is running, and they're not caught at compile time. These occur to human error, to programmer error. They're checked at runtime. There's nothing forcing them to be caught, but the programmer should be aware of them, because if they're not, the chances of introducing a bug increase. And they're often encountered in many different areas, such as null pointer exceptions or number format exceptions. Now, a part of the unchecked exceptions are errors. This is a special type of unchecked exception that are the most serious exceptional conditions, and these are very hard to recover from. They're irrecoverable. So an out-of-memory error if your operating system runs out of memory and you can't allocate anymore, or if you have a stack overflow within your application, these errors don't need to be caught, and the best practice in this scenario is to let the program crash and hope you get information from your log files as to what exactly happened, ideally a print of the stack trace of when it happened. These can occur due to human or programming errors, such as a stack overflow if you have too much recursion, or operating system environment errors. So the best practices for Java exceptions is to use them to clean up resources such as closing file handles, database connections, and network connections when you're done with them, even if they fail partway through the operation. Prefer specific exceptions rather than generic exception classes or broad exceptions that cover many types. Make exception handling code self-documenting by using specific exceptions. And document exceptions. Describe how particular exceptions might occur if it's not obvious from the context. You should also throw exceptions with descriptive messages and catch the most specific exception first. And don't catch throwable. Throwable is the base exception superclass. It's the most general, generic, broad exception in Java. It's too general. It catches all exceptions and errors of all types. It makes the code harder to read and follow. It makes it too easy to catch exceptions, such as errors, that you shouldn't be trying to catch anyway. Some more best practices are to not ignore exceptions. For checked exceptions, but don't assume all unchecked exceptions don't need to be caught. Some, if you know that they're likely, you can catch them and redirect the user to recover. Don't log and throw, or rather, log and rethrow. I've seen many exceptions caught, a log line written, and then the exception is rethrown farther up the call stack. This usually results in duplicate log messages for the same exception and not really doing anything productive to handle the exception. You're just adding more work. In this case, exceptions should be in the method signature so that it can be handled by the caller. And you can wrap exceptions. So extend your own exception classes where you need a specific handler tied to your application's functionality or underlying architecture. Wrapping exceptions is perfectly fine and may make debugging easier when you run into problems in your code. And that concludes this presentation on Java exception handling. In this video, I'll demonstrate how to handle exceptions in Java, focusing on two different types, the checked exception and the unchecked exception. So I'll have an example of each. So in my main.java file, I put this class in the package com.example, and then I have my imports. Import java.io.file input stream, because I'm going to demonstrate opening a file and what happens if the file can't be found, for which I need import java.io.filenotfound exception. So this will be part of a checked exception, an exception that we need to catch or the program won't compile. Whereas an unchecked exception, which I'll also demonstrate, is something that we typically don't check, because it's usually an error that we can't recover from or that we can't anticipate. So I'll explain this as I go. So inside of public class main, I define a function. So the first exception is going to be an unchecked exception, and I'm not going to catch it. And the exception I'm going to force this program to have is a stack overflow error. So it's when you call too many functions, especially recursive functions, and the program runs out of stack space. A program running out of memory, things to do with the operating system that are external to the program are all errors that are typically unchecked exceptions. In general, in Java, errors or runtime exceptions are these exceptional conditions, you can think of them as, that we don't need to catch. And when we don't catch them, the program crashing or exiting, usually printing a stack trace of where the error occurred, might be the best or only course of action that can be taken. So on line 8, I have public static int factorial that defines the parameter int n. So this is computing the factorial successively and recursively. So in it, I have if n is equal to 1, return 1. So that's the first one. And then else, return n times factorial of n minus 1. So the idea is you pass it a number n, and it will multiply it by all the numbers up until n, and then exit returning the result. And then in the main function, in public static void main, where I have string double brackets args, inside of the main entry point on line 17, I have int result equals factorial with the argument -1. Well, if we pass -1, the factorial will never finish because it's expecting a positive n, and if we don't check for it, factorial will be called recursively and never exit. But it will exit because we'll run into a stack overflow. We'll have called factorial recursively too many times, and it will cause our program to fail. So on line 18, I have system.out.println of the result that's returned by the factorial. So I'll run the program at this point before I get to the second exception. So shift to F10 to run the program. And there's a whole long line of factorials. So this is the actual stack trace, the actual function call stack trace. And it just keeps calling factorial. And I scroll up through all of these calls to factorial. I'll select the scroll bar and go right to the top. And the exception in thread main, java.lang.stack overflow error. So this isn't an exception that we'd look to catch. This is an error that happened due to a programming error and should be fixed in our code. This is an actual program bug. So using exceptions to catch program bugs are not something you typically do, and arguably better to let the program fail, see what the exception was, and fix the code so it doesn't run into that exception. But this is not the case for checked exceptions. So what I'll do is I'll comment out those two lines of code with the factorial and the result on lines 17 and 18. So I've commented out those two lines. And then I have my checked exception. Now there's a try block, and inside of it I have file input stream f equals new file input stream. And the string is /non_existent_file. A file that I know doesn't exist on this system. So it's opening a file that doesn't exist, which should cause it to throw a file not found exception. And that's my catch. Catch file not found exception E and system.out.println E. So it's going to print the exception. or the results of the exception. Another way of doing this, if we want to see what the details of the exception are, we could also call e.printStackTrace. But what happens if I remove the try and catch block? So I comment out the try and the catch and the contents of it, so I put double slashes, but I leave file input stream f equals new file input stream with the file. So if I save it, IntelliJ signals that there's an error. So there's a red underline, and there's this stop symbol saying 1 error and 3 warnings. If I do Shift F10, it's going to try to build, and it shows what the error is. It says unreported exception, java.io.filenotfound exception must be caught or declared to be thrown. So you either have to catch the checked exception or make sure that it gets thrown. So in this case, we're going to catch it. So I have to put in the try block and the catch. And once I save it, type Shift F10 again, it compiles successfully and it gives me the result. And in this case, it prints java.io.filenotfound exception / non-existent file, no such file or directory. So we caught it successfully, the file wasn't found, and this is the type of thing that should be caught. So if you're trying to open a file and it fails, you should be able to handle it. If you're trying to write to a file and you don't have write permissions, you should be able to inform the user that you can't write to the file doesn't exist, or you can't read it, or there's some error handling a file. So these type of external resources, such as trying to connect to a web page and download some contents from your code, if you can't make that connection, if your internet connection goes down, or the site you're connecting to goes down, that's the type of exception that you always need to catch, which we call checked exceptions. And that concludes this demonstration of programming with Java exception handling. In this video, I'll describe some of the more common exceptions in Java. So Java has 2 main categories of exceptions. The checked exceptions. These are exceptions that must be caught, otherwise your program won't compile. Most IDEs, like IntelliJ, will flag checked exceptions as you're writing them. Unchecked exceptions are ones that don't need to be handled, but areas where things can be thrown. Unchecked exceptions are typically exceptions that don't expect a program to recover from. So if your system runs out of memory, the operating system itself, or some other type of error external to the application causes an error in your application, Java can still throw an exception. Unchecked exceptions don't need to be caught, but in some cases you can catch and handle them, but some, such as ones generated by the underlying operating system, if there's an out-of-memory error, they don't need to be caught, and your program can just fail, printing a stack trace. And that's generally accepted as the best approach. Checked exceptions are often things like I/O exceptions, so input-output operations fail, such as reading a file, reading network, that you may not have write permissions for. I/O operations typically come from the java.io package or java.net package, so network communications and file and device input-output operations. Checked exceptions, one of the most common examples is the parse exception. This is used to create an object based on a given string. This happens when you're trying to parse useful information out of a string to create an object, and it's not in the correct format, or you can't pull out the desired information. So the formatting might be something like a date. Let's say you're expecting a date in dd/mm/YYYY, so 2-digit day, 2-digit month, and 4-digit year, delimited by slashes, or say another date format with a 2-digit day, a 2-digit month, and a 3-digit year separated by commas. So dates can come in all sorts of formats, and if you're expecting a certain one and you're not given that date format, then your program will throw a parse exception. I demonstrate the parse exception with example code in the video titled Programming Common Java Exceptions. Other common checked exceptions are the interrupted exceptions for threads. So this is a thread-based exception thrown for join, sleep, and wait during wait states or timed waiting states. So the thread can interrupt another thread either before or during the activity, and this can be checked by calling the interrupt method. And the current thread can test whether it has been interrupted by calling the interrupted method. And these are all directed through the interrupted exception. A common unchecked exception is the null pointer exception. So an application attempts to use null when it requires or expects an object instance. So an object gets set to null, and then later on, a method for that object is called. You'll get a null pointer exception. So this is illegally using null or a null reference when you're expecting an object. So the method of a class that has no object instance will throw a null pointer exception. And if you try to access or modify instance variables with null references, you'll also get the null pointer exception. Another common unchecked exception is the array index out of bounds exception. So a negative index, or most likely an index that's greater than the array's maximum. So anything from the size of the array and higher will end up with an array index out of bounds exception. A string index out of bounds exception usually happens with the char_at method of a string, where you're trying to index a single character with the string result in a negative index or an index past the end of the string's length. So these are unchecked exceptions. You might think, well, why don't we check these exceptions? These are typically driven by programmer error, a result of unchecked bounds, or checking past the end of an array. Another unchecked exception is a number format exception. This happens when you're converting a string to a number or numeric type, and it fails because of an invalid format. For example, it's thrown when the integer.parseInt fails. So if you call integer.parseInt on a string, and you pass it something that's not a string, you'll get a number format exception. Now these unchecked ones can be caught and handled. Let's say a user inputs a number or expected to input a number and they don't, then you can catch the exception until they input something valid. Division by zero is a common exception where you get an arithmetic exception error thrown, or if you're trying to convert using an object cast to an unsupported type. For example, if you're trying to print an object by casting it to a string, using a prepended string in parentheses, if the cast is unsupported by the object, a class cast exception is thrown. Another unchecked exception that's occasionally thrown is an illegal argument exception. This is where a method is passed a bad argument incompatible with its parameters, such as null, or the state of the internal object. Throwing the illegal argument exception can't recover from it. Remember, this is an unchecked exception. If the caller can recover from the exception, then it should be checked. An illegal argument exception wouldn't be appropriate in this case. But if the calling method is forming the argument passed to the method from an external source or from an operating system source that may cause a null or an invalid value, then the program can't recover from the state. You can think of this exception as the unchecked version of parse exception in many circumstances. The illegal state exception comes up when trying to call a method when the current state of the object doesn't support it. For example, trying to start a thread when that thread has already been started or it's currently running. And that concludes this presentation on common Java exceptions. In this video, I'll demonstrate some common exceptions in Java through this example code I have opened here in IntelliJ. So in my main.java, I start by including it in the package com.example. And then on line 3, I import java.text.parseException. Then import java.text.simpleDateFormat. So we're going to try and parse a date from a string and store it in a date object. But if we can't parse that string, a parse exception will be thrown. Then on line 5, I have import java.util.date and import java.util.scanner to read our input when we run the program. So inside of the class main, inside of the main function, the entry point into our application, I have scanner input equals new scanner of system.in so that we can type our input in to test it. On line 13, I have system.out.print, enter a date, and in parentheses, I have yyyyy-mm-dd. So this is telling the user, telling us that we're expecting a date in the format of year, month, day, separated by hyphens. So the ISO 8601 date format. And then on line 14, string A equals input.nextLine. And then we go into a try block starting on line 16. Then I have simple date format called date format equals new simple date format with the string yyyyy-mm-dd in the expected format for our date formatter. Then on line 18, I have date of variable date in lowercase equals dateFormat.parse of our string A that was entered. And then on line 19, I call system.out.println with the variable date. On line 20, I have the catch. So catch parse exception. So this is the checked exception thrown by the parse method. So we have to catch that. And if we don't, if we ignore it, if I comment out the try and catch block, it's going to complain and tell me that this is an unhandled exception. So we need to handle it. Otherwise, the code won't compile and run. In the catch body, where I catch the parse exception, I call system.out.println of parse exception caught, and then I call system.out.println of E, the exception.toString. Then the second part of the code, on line 25, I have system.out.print, enter a number from 1 to 10. Then I enter a try block where I have int I equals input.nextInt. And on line 28, I have int b equals 10 divided by I. So there's a couple of things that can happen here. One, if we enter 0, which we don't check for, we'll have a division by 0. And that's an arithmetic exception. If the input is not an int, if we enter some string, some letters that can't be parsed into an int, we'll get a number format exception. So on line 30, I print the result. So I print 10 divided by, and I concatenate the variable I, is, and then I concatenate the variable b. My catch block starts on line 31 with catch number format exception, the pipe character, which is a logical OR, arithmetic exception E. So this is a way of catching multiple exception types with a single catch block. So it's going to look for both of those exceptions, and regardless of which one it is, it will store the result in the variable E. It'll print exception caught and call e.printStackTrace to see the entire stack trace of the exception. So now I'll run the code with Shift F10, and I'll type in a date. I'll put it in accurate dates, 2021-01-01. So it's of the correct format, and it prints Fry Jan 01-0000 AST 2021. Enter a number from 1 to 10. Well, I'll enter 5. And it shows 10/5, or 10 divided by 5 is 2, and it worked fine. So no exceptions thrown. And let's have it throw an exception. So enter a date. I'll enter my name, Steve. Parse exception caught. Unparsable date Steve. So Steve is not a date, and I knew that going in. So it's not unexpected. Now I'll enter a number 0. Exception caught. Java lang arithmetic exception, division by 0, at com.example.main.main, main.java line 28. So it happened on line 28. Let's run it one more time. And let's enter a number this time. Let's say 1, 2, 3, 4, 5, 6. And it tells me that it's an unparsable date. 1, 2, 3, 4, 5, 6. The parse exception was caught. And now I'll enter a number. In this case, my number will be Steve, which is not a number. And the exception thrown gives me an input mismatch exception. So it's not quite what I expected. I put in the number format exception, which could be a possibility. I can also put in input mismatch exception and put in an OR if I want to catch that same one. And let's see if we can catch that input mismatch. So it doesn't matter what I put in for the date. And now I'll enter my name again, Steve, when my program's expecting a number. And it tells me that the exception is caught. And it prints the java.util.input mismatch exception. So these are unchecked exceptions. And generally, when you're expected to input an integer and you put something else, it's going to do bad things in your program. And in many instances, you should almost let the program fail and print this stack trace as it would by default so that the bug can be fixed. And that concludes this demonstration of programming common Java exceptions. In this video, I'll describe how try-catch blocks are used in Java. I've covered exception handling and common exceptions during this course, but I haven't devoted direct attention to try-catch blocks themselves, including the finally statement, which I'll do here in this video. So Java exceptions are a way of handling and passing error information. It's our way of dealing with exceptional events. We're not passing around error codes or return codes, which is what happens in other languages that don't have exception handling, like in the C language. The syntax in Java is driven by the try and catch blocks. So there's a try keyword and a catch keyword, and their blocks are surrounded with braces, like you would see in an if statement. And there's also a finally block with statements to handle situations. Regardless of what happens in the try and catch blocks, the finally block will always execute. So Java try blocks are part of our exception handler syntax. So a try block is a block surrounded in braces that follow the try keyword, which is then followed by a catch statement. So the catch keyword followed by parentheses that contain the types of exceptions that we're looking to catch. And following the catch statement, there's a catch block surrounded in braces where we execute code when an exception is caught. So the try only designates an area that corresponds to the catch block. So if an exception is thrown outside of the try block, the catch block won't have anything to do with it because it's only looking within its corresponding try block where the exception may be thrown. And you can't have a try block without a catch, and you can't have a catch without a try. They're connected to each other. The Java catch block specifies an exception type. With an if statement, you have an if block where you specify an expression that results in a true or false. A catch block specifies an exception type. The exception thrown is indicated by its argument. It's executed if and when the exception handler is invoked. So the runtime system breaks out of the try block and proceeds immediately to the catch block, skipping over the remaining statements within the try block. The Java catch blocks are triggered within the corresponding try block. The try block jumps to the catch statement, skipping over any code that remains within the try block. So we have to take that into account when we're designing our catch blocks and our finally blocks. So it checks for a matching exception type. So if an exception is thrown and it's not contained within the catch statement, the program will exit, printing the stack trace of where that exception occurred. But the catch statement, if it is matched, then it leaves you with a way of handling the error, recovering from it if you can. And quite often this results in prompting users to make a decision, either re-entering input that might be invalid, or reconnecting to a database or an external server that may have dropped the connection, which resulted in the exception. And in some cases, we can propagate errors by handling the error locally and rethrowing the exception further up the call stack. But this is something we use sparingly. It's typically bad form to catch an exception and just propagate it, rather than just propagate it without catching the exception, if we know it's going to be handled further up the call stack. The catch blocks in the Java exception handler can handle more than one type of exception. So you can chain them together using the single pipe character, which I demonstrated in the video titled Programming Java Try Catch Blocks. This is available in Java SE 7 and up. It reduces code duplication, so you don't need multiple catch blocks. You can just have one catch block with multiple different types. It lessens the temptation to ignore certain exceptions or to use more generic exception classes. So your exception classes should be more specific if you can, which it makes it easier for self-documenting code when we know exactly what types of exceptions are being caught. And a catch parameter is implicitly final. So we don't need to declare it final. The parameter is already flagged final for us. Now the Java finally block is typically used or mainly used for resource cleanup. So if you have open files or network connections or database connections that need to be closed or cleaned up, then you can perform that in the finally block. And the code in the finally block must assume both success and failure conditions. So if the try block fails before the file can be opened, then the file object might even be null at that point. If you try to call close on the open file where the object is null, you'll generate another error, another exception within your finally block. So you should have checks for null and partial failures where your try block might fail before it reached the end, or what to do when the try block completes successfully. And that concludes this presentation on Java try-catch blocks. In this video, I'll demonstrate a full example of a Java try-catch block, including a finally block. So I start in this main.java by including this in the package com.example. Then I import the classes we need for this example. So on line 3, I have import java.io.filewriter because we're going to write to a file. I import java.io.io exception because if FileWriter has a problem, it's going to throw an IO exception. Then import java.io.printWriter to help us write to the file. And import java.util.scanner because our input is going to be what's written to the file. So I have public class main and the main function entry point, and then the code begins on line 11 with scanner input equals new scanner of system.in. And then I print using system.out.println, enter a string, and then on line 14, string str equals input.nextLine. So we're going to enter some text, hit enter, it's going to save it in the str variable, and we're going to write that to the file. On line 16, I create printWriter output equals null. So we initialize this output variable set to null because this is what we're going to use to write. It's also going to have a handle to an open file, which we need to close when we're done with it. So I set it to null just so we can check the state of it if there's an exception thrown. On line 18, I start my try block and then system.out.println try writing to file ... So I have a little message saying that we're entering the try block and what we're doing. Then on line 20, I check the length of the str variable. So if str.length is greater than 0, we try to write it to the file. Otherwise, so in our else block, we just print input empty. So if a string was entered and not just an empty string, we'll get into the block, the if block on line 21, where I set output equal to new printWriter, and to its constructor, I pass new FileWriter with the string output.txt. So we're going to open this file output.txt in the current location, and then on line 22, output.println of str. So we write the string. If there's an exception thrown, I catch it on line 26. So I have a catch of IO exception E, which can be thrown by our FileWriter constructor. On line 27, I have system.out.println could not open the file for writing, and then I print e.toString to see what the exact exception was. On line 29, I have my finally block. So no matter what happens, as long as we start processing in this try block, if there's no exception thrown, finally is called. But if there is an exception thrown and we catch it, finally is still called. So this is called no matter what. So on line 30, I check if output is not equal to null. So if something happens that output cannot be assigned, it will still be null at this point, so we don't have to do anything. But if it's not null, it will get into this if block and call output.close to close our file handle to the output.txt file we opened. So when you open a file, at some point later on, when you're done with it, it's important to call close. Else, system.out.println file not written. So if it wasn't open, I just say file not written because it's still null at this point and something bad happened. So now I'll do a control F10. This will run the code. I'll enter the string test, hit enter, and it tells me trying to write file, and everything seems fine. If I look in my project explorer, I see there's a file created, output.txt, and its contents has test, exactly as expected. And that concludes this demonstration of programming Java try-catch blocks. In this course, we've examined how to handle exceptions and how to debug your Java code. We did this by exploring how to debug code using the Java JDB tool and IntelliJ, best practices when debugging Java code, common syntax and logic errors, as well as programming Java exception handling, common exceptions in Java, programming Java try-catch blocks. And in our next course, we'll move on to explore how arrays and array lists are designed to handle looping through lists of data. In this video, I'll present some details about Java arrays and array lists. So conceptually, an array in Java is a container object that we put values in. It has a fixed length, a fixed number of elements that can be put into the container, and they must be of a single type. If you create an array for integers, then you can't put strings in it. When the array is created, the length or size of the array is fixed. If you allocate an array for 100 integers, you can't later resize it to hold 101. What the container can hold can be primitive types or objects, whatever you decide when it's declared. An array has elements which we access using an index, a number starting from 0. So the first array element is at index 0, and the last element is at length -1. So a 10-element array has a max index of 9. So we specify the number to access the individual elements of an array, whether we want to retrieve it or change it. An array list is a special type of array container object. It's implemented as a class in what Java calls its collections framework. Its size is not fixed and can grow as needed when new elements are inserted, so we say the size is dynamic. However, it can only hold object types and not primitives, although we can use the java.lang packages that wrap the primitive objects into a corresponding class. For example, the integer class wraps the primitive int type, but we can't create an array list with the primitive type directly. What are some similarities between Java arrays and array lists? Well, they're both used to store elements, so they can both act as containers for holding them. Arrays and array lists can both store null values for objects, and they can both store duplicate values. Some containers are built to store unique values, like the Java set class, but arrays and array lists can have duplicate elements, and the element order is not maintained. Arrays and array lists don't hold a particular sorting, nor can they perform stack or queue-based insertion and removal, such as first in, last out, or first in, first out ordering. What about the differences between array and array lists? Well, an array is a dynamically created object in a contiguous memory location. Its size is fixed and static in size throughout the life of the array. It's set when it's created, and it must stay that way. So the size is established when it's declared, and it stays that way throughout the life of the array. And it stores both objects and primitives, whereas the array list is a class in the collections framework. So it's a special type of class with a dynamic size. So you can start with a particular size or a particular number of elements that the array list can hold, and the array list will grow to accommodate. The size is not necessary at declaration, so you don't need to specify an initial size at all, and the array list will grow as necessary based on what it's initialized to and what elements are inserted into it. But it only stores objects. So I can't have the primitive types, I can't have a primitive int or boolean or double. It has to be parameterized with a class. And that concludes this presentation on Java arrays and array lists. In this video, I'm going to talk about Java arrays. I'm going to describe them and how they're used within Java. Let's first look at array declaration and creation. So to declare an array of integers, we specify the array with an open and close bracket along with the type. So I have int, an open and close square bracket, and then the name of the array, the variable name, in this case, my array. So this declares the array. Now to create it, creating an integer array, an int array, we have my array equals new int, and then in square brackets, we specify the size. And this one's created to hold 10 elements, 10 primitive integers or 10 ints. Then for the life of the array, it cannot be resized, and the size is fixed from this point on. Let's look at how we initialize an array. So to initialize the my array we declared on the previous slide, we could set the individual values based on the array index. So I have my array in square bracket 0, so I say indexed at 0 equals 21. So we're setting it to the int 21. My array at index 1 is equal to 22. My array of index 2 is equal to 23, and so on until we get to my array of 9, which is equal to 30. So this is one way to do it. We can also create and initialize in one statement. So I have int, open and close bracket, my array equals, Then we have the open brace. Inside of it, we specify a list of ints. So I have 21, 22, 23, 24, 25, and then the next line I have 26, delimited up to 30. And then I close the brace and close the semicolon. What this does is create an array with a size big enough to hold all of the initializers, so all of the numbers, in this case the 10 numbers from 21 to 30, so it will be an int of size 10. So we can either declare and create it like we did on the previous slide, set all of the elements individually, or we can create and initialize in one statement if we know some initial values. How do we access the array elements? So as we did on the previous slide, to set the array elements, to access them, we specify the array name with the index in square brackets, but we do it without the assignment. So in this example, I have system.out.println. Of the literal string, I have element1 at index 0, and then a space, then plus, so I concatenate my array at 0. So this will take the value at 0 and put it into this print statement. If we'd like to access the second element at index 1, we specify my array and 1 in square brackets, and so on. And we can do this all the way up to index 9 because it's an array of size 10, so element 10 is the last one, and the index for this element is index 9 because we start at 0, so my array of index 9. Arrays are very convenient for looping, especially using the for and for each loop constructs in Java. So with the for loop, we use the length property of the array. So to get the size of the array, we call .length on the array variable. So to print all elements in my array, I have for, and then in parentheses, I have int I equals 0. So that's our index value, our index variable, semicolon, I less than my array.length. So while the I variable, the index variable, is less than the array length, then semicolon, I plus plus. So on each iteration of the for loop, we increment the I variable, which is going to be our index. And we call system.out.println of my array at index I. So I will go from 0 to 9 and then exit the loop. We could also use the for each syntax, which simplifies it. If we'd like to print all of the elements in my array, we can use for, and then in parentheses, int I, my array. So this is the Java for each syntax, and the int I in this case is not the index, but the current value depending on the iteration of the loop. So it will start at the first element and take its value and call system.out.println of the value I. And that will print the same thing, so both of these loops print the same values. So arrays are primitive containers in Java. They don't have the same functionality or capabilities as ArrayLists or other collection classes. However, there are utility methods to work with them. So we have some array manipulation methods provided by Java. And these methods are in the java.util.arrays class. There's methods for searching, sorting, and copying elements, as well as methods for comparing if two arrays are equal. So the java.util.arrays class is a helper class for working with standard Java arrays. And that concludes this presentation on Java arrays. In this video, I'll demonstrate the standard array syntax used within Java. So we'll start in this video inside of the typical main function that's declared public static void main, string double brackets args as its parameter inside of my public class main. Now on this first line inside of the function on line 6, I have int, then open and close square brackets, ages equals an open brace, then 39, 27, 97, close brace, semicolon. So what this says is to create an array called ages of type int with 3 elements initialized to 39, 27, and 97. The double brackets after the int says that we're declaring an array. Now there's a separate syntax that's also valid, is to take the double brackets and put it after ages. So if you've come from C or C++, this syntax might look familiar to you, as the array syntax in Java follows a similar syntax. But it's also recommended in Java that the double brackets be attached to the type before the variable name. So the preferred way is int double brackets, so open and close square brackets, followed by the variable name. So we have an array ages at the moment with 3 elements, 39, 27, and 97. Then on line 7, I extract an element from the array and save it into a variable. So I've int my age equals ages, an open square bracket, followed by the array index, in this case indexed at 0, and then close the square bracket. So whatever's in the square brackets is the array index. And it's important to note that arrays are indexed from 0. So the first element to access it in the array is element 0. In this case, it should set my age to be 39. On the next line, I have int your age equals ages indexed at 1. So in this case, that would be the 27. So your age will be set to 27. And then on lines 10, 11, and 12, I print some of the results so we can verify it at this point. So when we run the program, we'll be able to look at this. So I print my age is with the variable my age, your age is, and then I concatenate your age, and then I print my friend's age is ages at index 2. And then what about ages at index 3? Well, in this case, if I save it and leave that in there where I reference ages at index 3, so this will be the 4th item in the array, which doesn't exist, and it will be past the end of the array. So I'll leave that line 13 in, for the first time I run it. And the program will fail at this point. So I'll use Shift F10 to run it at this point before I explain the rest of the code, and we can see that there's an exception in the thread, array index out of bounds exception. So we've gone out of bounds. So I'll comment that line out on line 13 so we don't have that problem. Then the next part of the code on line 15, string, open and close bracket, names equals the initializer list, so the values, the strings surrounded in braces with Steve, comma Mary, comma William, comma Bob. And on line 17, I set names indexed at 2 equal to Bill. So we change William to the shortened Bill. And to verify that, I use system.out.println with names2 colon plus the variable names indexed at 2. So we look inside the array and we make sure it's set to Bill. We can also loop over all of the elements in an array. And one of the easier ways of doing so is using a for loop. So the conventional for loop, on line 23, I have for, and then in parentheses, I initialize a loop variable, an index variable, int I equals 0, followed by a semicolon. I is less than names.length. So .length is a property of arrays that we can access that'll give us the size of the array. And so double ampersand I less than ages.length. Now, if we just look at names.length, it has 4 elements. But ages has 3 elements. So if we continue looping without checking both arrays, then we could go past the end of the array and we'll get an array index out of bounds exception. So this will ensure that it stops after the smaller of the 2 arrays, in this case ages. And then another semicolon, I++, and then I have the body of the loop, which is enclosed in braces, which I print system.out.println names indexed at I, the loop index variable, plus a colon surrounded by spaces, and then I concatenate ages indexed at I. So we'll associate the name with the age and print the results. There's another syntax for a for loop called a for each loop, which I demonstrate on line 28. So if we don't need the index variable and we just want to access the elements in the array, we can use the for syntax with the for loop, and in parentheses, we have int age. So we actually have the value variable, colon, and then the array, in this case ages. And on each iteration of the loop, it will have the current element in the variable age. And then inside this loop, I do system.out.println of age. So now I'll run the code with Shift F10, and let's have a look at the results. So I have my age is 39, your age is 27, my friend's age is 97, names2 is set to Bill, the for loop produces Steve, 39, Mary, 27, and Bill, 97. and the for each prints the contents of the ages array 39, 27, and 97 as expected. And that concludes this demonstration of programming Java arrays. In this video, I'll present some of the important details to keep in mind about array lists and how they're used within Java. Array lists are created to hold a single type of element. We say that the array list is parameterized to hold a type of object. And it's only object types and not primitive types, at least not directly, though we can use a wrapper class for a primitive type in case we need to use them as our elements. So for example, if we need an integer, instead of using the primitive int, we can use the integer class to parameterize the array list. Array lists are also resizable. They can grow as needed as more elements are inserted. What are some of the features of array lists? Well, they're part of the java.util package, and we import java.util.ArrayList to include them. They can be slower than regular arrays, but mostly due to their added functionality. ArrayList is a necessity when you need an array that can be resized to fit more elements, whereas a conventional array in Java is fixed. Array lists are useful when array manipulation is necessary because of the capabilities and characteristics of the ArrayList class. What are some of the common ArrayList capabilities and characteristics? Well, they support retrieval by index using the get method. It supports box types, so converting primitive types to the wrapper classes of the array list with Java's auto-boxing and unboxing functionality to automatically perform the conversions to the parameterized type, say from int to the integer class or vice versa. It permits duplicate and null entries, and it maintains the order of the elements. So if you traverse the array list one element at a time, add another element, and it's not going to change the order of anything in it. It's not implemented with any type of tree structure under the hood. It only maintains continuous arrays internally. However, it doesn't support primitive types, so no basic primitive int or char or boolean or double or short or any other primitive types in Java, and it's not synchronized for multi-threaded use. So if you have an array list and multiple threads can modify it, then you need to handle the synchronization at the thread level outside of the array list. How are array lists declared and created? Well, we import the ArrayList class using import java.util.ArrayList. We declare the array list of integers by using ArrayList and then in angle brackets the integer parameter. So we say ArrayList parameterized by integer my array list, the name of the array list. And then we can create integer array list using my array list equals new array list with integer and angle brackets, and then in parentheses an initial size, in this case 5. That doesn't mean it's fixed or that's the maximum size, just the initial size. So when it reaches 5, it will increase the size of the array list. So when using ArrayList, we can initialize it by using the add method. So myArrayList.add1, myArrayList.add2, myArrayList.add3, and so on until we get to the last element. So if we have 5 elements we want to add, we can stop there. But we can also populate it with a loop. So in this example for int I equals 1, while I is less than or equal to 5, I plus plus. And in that loop, we call myArrayList.add with I, and it will perform the same thing as inserting them individually. Now, to access array elements, we can't use the double bracket syntax like we do with arrays. We have to use the getMember function. So we have this method that retrieves based on an index value. So in this first part, I have system.out.println with the string element1 at index 0, and I concatenate myArrayList.getZero. So it gets the first element. And just like regular arrays, they're indexed starting from 0. So the first element is at 0, and the last element is at the size of the array list minus 1. And to get the next element, element 2 is at index 1, element 3 is at index 2, and element 4 is at index 3, and so on, until we get to the last element, element 5. What about modifying ArrayList elements? Again, we can't use the square bracket syntax like we do with the array, so we have a method set. So myArrayList.set element 0, so index 0, and we set its value to 10, so 0, 10 as the arguments to the set function. So set takes 2 arguments, the first one the index and the second one the value. We can delete an element by specifying an index. So myArrayList.remove 0. So this removes the element at index 0 from the array list. We can clear the entire array list, all of its contents, by calling myArrayList.clear, and we can get the number of elements, the total number of elements in the array list, by calling myArrayList.size. And that concludes this presentation on Java Array. In this video, I'll demonstrate how array lists are used within Java. So array lists are a resizable array implementation. This provides us with features we don't get in a conventional array. So in this example on line 1, I declare it to be in the package com.example. Then I import the required classes. I import java.util.ArrayList. Then import java.util.arrays, import java.util.collections, and import java.util.list. And I declare my class public class main with public static void main with string double brackets args as its parameter, the main entry point into our program. So on line 11, our code begins. I declare a conventional array, int, open and close brackets, nums equals the initializer list, so the list of numbers in braces, with 5, 43, 99, 27, negative 50, 100,022, negative 75, 0, 1, 7, 5, then 774. So I'm going to take this array of ints and convert it to an array list of integers. So we're going from the primitive int type to the integer object type. On line 13, I declare list of type integer called numContainer equal to new array list, the open and close angle brackets, because the type has been defined, and we pass to the constructor the initial size, nums.length. So to get the elements from our primitive int array into our container, we need to loop over the elements and add them to the container. So on line 14, I have a for each loop, for, and then in parentheses, int num colon nums, and then inside the loop, numContainer.add num. So this array list has an add method that will add the numbers one by one again. And then when we exit the loop, all of the numbers from int nums will be in numContainer. So on line 17, I output the contents of numContainer with system.out.println with numContainer colon space, and then I concatenate numContainer. So numContainer has a toString method which will take all of the elements in the list and display them when we output them. Now, if I tried to do this with nums, it wouldn't work. We can't take a conventional array and try and output the contents in this way. So numContainer gives us that feature. We can also use the collections utility to sort our array list. So to put it in sorted order, on line 18, I have collections.sort, and I just pass in numContainer, and it will sort it. I create a second int array. So what I'm doing is taking the array list, sorting it, converting it back to an array of ints. On line 20, I have int, open and close brackets, sorted ints, so this is the name of our array, equal to new int, and the size is going to be numContainer.size. Our array list has a size method to return the number of elements. On line 21, I have a for loop, a conventional for loop with for int I equals 0, while I is less than sorted ints.length I++. And then sorted ints I equals numContainer.get of index I. So in a conventional array, we use the bracketed notation to index the array, and in the array list, we use the get function. And then on line 25, I have system.out.println returned ints, so this is what returns into our sorted array, plus arrays.toString of sorted ints. So we can use arrays.toString of a conventional array to return the elements in a string that we can display. So use Shift F10 to run the code, and in the results we get numContainer with all of the elements in the original order, and then the returned ints in the sorted order from negative 75 all the way up to 100,022, the largest element at the end. And that concludes this demonstration of programming with Java ArrayList. In this video, I'll describe the iterator interface and how it's used within Java collection classes. So the Java iterator interface is part of the collection framework in Java. It's used to retrieve elements and step over them or traverse them. There are three iterator types: the enumeration, the iterator, and list iterator are the main interfaces. However, the enumeration is now considered a legacy method, and nowadays we typically only use iterator or list iterator interfaces for iterating over collections. So what are the iterator methods? The first is the hasNext method, which returns a Boolean saying whether or not there's another item in the collection that the iterator can point to. The next method returns the next object, a reference to it. If there is none, it returns a no such element exception, and where hasNext returns false, you can expect this exception to be thrown if you call next. The iterator also has a remove function to remove an element from the collection. This is something that the legacy enumeration interface did not have. The list iterator is a two-way navigation of lists. It provides a next element and a previous element, so it provides for bidirectional traversal. It also permits modifying elements like the iterator that it derives from. So what does this look like in terms of declaration and creation of iterators? Well, first we have to import the iterator class with import java.util.iterator. We declare an iterator by parameterizing it with a type, so iterator and in angle brackets string, the type of iterator, the elements that it's going to iterate over, in this case called myIterator. So this will be an iterator to iterate over the contents of a string. And we can create an iterator from an array myList. So myIterator equals myArrayList.iterator. And how do we use the iterator? How do we get an item from an array using an iterator? MyIterator.next will return the item from the array or list. We can use the hasNext method to loop through an array. So while myIterator.hasNext, system.out.println, myIterator.next inside the body of our while loop. So the iterator maintains a current position, and every time next is called, it advances that position. Let's look at the list iterator declaration and creation. So to import it, we import java.util.listIterator. So when we declare list iterator, make sure that the list iterator, the L in list, and the I in iterator are in uppercase. So list iterator called myIterator, we can create, so myIterator equals myArrayList.listIterator. So the member method returned by myArrayList uses a lowercase l, so list with a lowercase l, and then iterator with the uppercase I. We can get the first item or next item by calling myIterator.next. We can get the previous item and go backwards with myIterator.previous. And we can loop through an array in reverse using the previous method. While myIterator.hasPrevious, so is there a previous item? And if so, system.out.println myIterator.previous. And that concludes this presentation on Java iterators. In this video, I'll describe the LinkedList class and how it's used within Java. So the LinkedList class is similar to ArrayList on the surface. However, under the hood, inside the implementation of LinkedList, it looks very different and is used for different types of problems or programming design patterns. Its performance is very different than the ArrayList. LinkedList contains objects of the same type, so it's parameterized by a particular type of object and does have some of the same methods as ArrayList. What are some of LinkedList's features? Well, it's easy to add and remove elements to the front or to the back of the list, as well as remove them. Elements are stored as separate objects, and they're not stored in contiguous blocks like in the ArrayList. Elements in a linked list are linked by pointers and addresses. So a linked list, you can think of it as a chain of elements with each link pointing to the next in line. And elements in a linked list are referred to as nodes, like they would be in a graph. What are some of the common linked list methods? Well, there's add first to put to the front of the list, add last to put at the end, remove first to remove the first element, and remove last to remove the last element, as well as get first to look at the first element but not remove it, and the same with get last to retrieve the last element, but get last is also a non-destructive operation. How do we declare a linked list and create one? Well, to import it, we need to import java.util.LinkedList. We declare it using LinkedList followed by a type. So the type of the node, in this case integer, we parameterize it by integer inside of angle brackets and then give it a name, myLinkedList. We can create the linked list with the new keyword using myLinkedList equals new linked list, integer in angle brackets, and open and close parentheses. How do we use the linked list? Well, we can add an item by calling myLinkedList.add with the element as an argument, in this case the number 5, which gets stored as an integer object. We can get the first element by calling myLinkedList.getFirst. In this case, it would return 5, and get the last element. Well, if there's only one element, myLinkedList.getLast will return 5 as well. So getFirst and getLast point to the same element if there's only one item in the linked list. We can loop over the elements using hasNext to loop through the linked list. We can create an iterator. So I have iterator parameterized by integer, the same object type as in my linked list, and I call this iterator I, and I set it equal to myLinkedList.iterator. So myLinkedList.iterator returns the iterator. And we can loop using while I.hasNext, and then inside of the loop, I print using system.out.println of I.next, and I close the loop. And that loop will print all of the elements, and if there's one, it will only print the one and then exit. HasNext will return false, which quits out of the while loop. How do we modify linked list elements? So I'll add 20 to the beginning, calling myLinkedList.addFirst of 20. So it prepends an element to the front of the list. It adds a node for it. We can add 20 at the end by calling addLast. And we can remove the first element by calling myLinkedList.removeFirst, or remove the last element by calling myLinkedList.removeLast. So the linked list class can behave as a stack or a queue, with many of the same operations that can be thought of as pushing or popping elements to the front or back of the list. And that concludes this presentation on Java linked list. In this video, I'll demonstrate how the linked list class is used within Java. I have a file here, main.java, which is in the package com.example, and I have an import java.util.LinkedList. So this is a member of the Java Collections framework. It's a type of collection or container of elements that can be used as a type of stack, a list, or queue data structure. Internally, it's implemented as a doubly linked list, one with forward and backward iterators. So inside of my class main, inside of the main function, on line 8, I start with linked list, parameterized by string, called books equal to new linked list, with double angle brackets and double parentheses to call the default constructor. So linked list will resize itself internally as necessary. And another point is it's not synchronized internally for multi-threaded use. So you need to synchronize it externally if you have multiple threads trying to update a single linked list. On line 10, I add my first element. So for this, I use books.push and pass the string Ulysses. Then on line 11, books.push War and Peace. On line 12, I call system.out.println with the string peak plus books.peak. So I call the peak method to see what the current element is. So this we could think of as the element on top of the linked list, if we think of it in terms of a stack or a list or a queue. If we're going to be putting elements on using a push and taking them off using a pop, then we can think of a linked list as a stack. On line 13, I print after peak plus books. So the peak operation is a non-destructive operation. It just looks at the element. It doesn't actually take it off. If we want to take the top element off and return it, we call the pop method. On line 15, I print pop with books.pop. So the item popped out of the linked list will be printed, and then after the pop operation, I print the contents of books. Then on line 18, I call books.pop, and it just removes the element. And at that point, since I put 2 books on the linked list and pulled 2 books off, it should be empty. So I print empty after another pop, plus books.isEmpty. It returns true if the linked list collection is empty. Now I create an array of books, book names, so string, open and close brackets, book names. So I'm creating a conventional string array called book names, and I initialize it. So inside of the braces, I have Pride and Prejudice, comma, A Tale of Two Cities, comma, the Iliad, comma, the Republic, comma, Alice's Adventures in Wonderland. So I have these 5 book names. I'm going to loop over them using a for each loop. So for string name, colon, book names, books.push name. So it's going to take them individually and put them into our linked list. Then I print after loop to push array elements onto linked list. I use println to print books. Then I print books.peak, books.size, books.peak first, and books.peak last. So the peak functions have some certain behavior, and because it's a doubly linked list, we can get the first element or the last element. And then on line 35, the last operation is an operation you shouldn't do. If you need to index elements in a linked list, you're probably using the wrong collection, and you should use an array list or some other type of list. So this is a slow operation, where I print system.out.println get element 3 plus books.get index 3. So if you need to get items from the front of the list or the back of the list, or insert to the front or to the beginning, then a linked list is fine, but if you need to index it quickly, then it's not the data structure to use. Now I'll do Shift F10 to run the code, and at the beginning, when we call our peak method, after we've pushed Ulysses and War and Peace into the list, the top item is War and Peace. So that's what we get when we return. And then after the peak operation, the 2 books are still there. We get War and Peace and Ulysses. Then we pop War and Peace. And then after the pop operation, we're left with Ulysses. Then we call books.pop by itself on line 18. And empty after another pop, that equals true at this point. Then after the loop to push array elements onto the list, when we print the list at that point, we have all of the names: Alice's Adventures in Wonderland, the Republic, the Iliad, A Tale of Two Cities, and Pride and Prejudice. So these 5 books, they're in the reverse order of what they were on line 21 when they were initialized in the array book names. So the linked list will put them on from back to front. And then if we peek, Alice's Adventures in Wonderland is at the top. The size is 5, so there's 5 elements. So the first element is Alice's Adventures in Wonderland. The last element is Pride and Prejudice. And the element at index 3 is A Tale of Two Cities. If we look at the output, Alice's Adventures in Wonderland, the Republic, the Iliad, A Tale of Two Cities comes at index 3, counting up from 0. And that concludes this demonstration of programming with Java's linked list. In this video, I'll describe Java's Hashmap class. So a hashmap stores elements in key value pairs, like an associative array, where the key uniquely identifies the value. So instead of a numeric index, the key could be any object, and oftentimes we use a string, so we have a name that indexes a value. So objects are accessible by an index defined by the key. And the reason why it's called a hashmap is that the key is hashed, or a digest is created to help find the value. So there's no searching for the value. We just compute the key that points to the particular value. So how does the Java hashmap reference the value? So the object key is an index, and that object corresponds to another object called the value. And the key and value could be different types. So we need to parameterize a hashmap to define the type of key and the type of value. So to declare a hashmap, we first need to import the hashmap class using import java.util.hashmap. Then we declare it using hashmap, and then in angle brackets, we need to specify the 2 types. First the key, in this case a string, comma, integer. So it's going to use a string key to get the value, which will be an integer type. And I call this my hashmap. To create the hashmap, we could use my hashmap equals new hashmap with the parameters string, comma, integer, followed by the open and close parentheses. Using a hash map, we can add an item using the put method. So myHashmap.put with the first argument the key, in this case oranges in quotes, comma 50, where 50 is the integer value. To access a hash map, we use the get method. So myHashmap.get with the argument being the key. So oranges, in this case, would return 50. How do we determine if a hash map contains a specific value and return the key value? We could use if myHashmap.contains key oranges. So in this case, it can look up the key to see if it exists. And if it does, it sets integer I equal to myHashmap.get oranges, and then prints using system.out.println key value plus oranges plus I returns the number. How do we modify elements in a hash map? Well, we can remove a specific element by calling myHashmap.remove and providing the key. We can clear the hash map using myHashmap.clear and get the number of elements by calling myHashmap.size. How do we get hash map keys and values using a loop? Well, we can get all of the keys for the hash map and put it in a for each loop using for string I colon myHashmap.keySet. So the key set returns a set view to the keys in the map. Now, one thing about Hashmap, there's no specific order that this will be returned in. And inside the loop, I print system.out.println of I. So it will print the string element. But there's no guarantee each time I insert a new element into the hash map, a new pair, that it will be put in any particular location. The location is based on the hash value or the hash digest value of the key so that it can look up the value with a constant time. So it's built for speed so that it doesn't have to search for elements, it doesn't have to search for keys to find the value. It can look it up in constant running time instead of having to search through the elements to find what it's looking for. We can get all of the values in the hash map by using the values function. So for integer I, the type of the value, colon myHashmap.values, and inside the loop, I call system.out.println of I. Now, one thing to keep in mind with hash maps is that the keys are unique. So if you try to insert a key that already exists, it will overwrite the existing key. And that concludes this presentation on Java's. In this video, I'll demonstrate how a Hashmap class is used within Java. So Hashmap is an associative array type of data structure. It allows a constant time key-based insertion and retrieval of elements. However, the order of the elements is not guaranteed and does not stay constant over time. So if you need elements in a particular order, such as the order they were inserted or sorted in some way, then Hashmap is not the right choice. But the basic put and get operations are what Hashmap excels at. So in this main.java, I have package com.example, to which it belongs, and import java.util.hashmap. So Hashmap is a collection in the java.util package. I declare public class main, and then a private static final int map underscore capacity equals 10, which gives me a nice constant value to set the initial size of the hash map. Then in my main function, on line 10, I have hashmap, then in angle brackets string, comma string. So the first parameterized value or type is string, which says the key is a string type, comma, string as the value type. So we have name value pairs that take a string and return a string. We have email username as the name of the hash map equals new hash map, the double angle brackets, and we pass the map underscore capacity to set its initial capacity through the constructor. Then on line 11, email username.put. So I call the put method to add a pair to the hash map with the key being steve@example.com. So an email, then comma steve456, a username. So if we need to retrieve someone's username based on their email, we can call get on the hash map with the email address and it returns the associated username. On line 12, I put another username with bob@site.co.uk, comma bob1962. Then email username.put alice@somewhere.ca, comma havingfun55. Then on line 15, system.out.println size, So to retrieve the number of elements inside of the hash map, we call the size method. So email username.size. And then on line 16, I print the username associated with steve@example.com. So I call email username.get steve@example.com. Now what happens if we try an email that doesn't exist? Now this won't generate an exception. What it's going to do is print null. So system.out.println, where I have the string try a non-existent email plus email username.get with nobody@example.com as the string we pass to it. So it's going to look for this key, it's not going to find it, and it's going to return null. We can also delete by the key. I can call email username.remove and pass bob@site.co.uk. And this will remove the entry associated with this email address. And at this point, if I call size, it will return a size of 2. Because we put 3 in, we removed 1, and we're left with 2. We could also replace an entry. If I call email username.put with a key that already exists in the hash map, then it will replace it. In this case, I'll replace it with Steve123. We can also loop over all of the keys, although it won't give us the results in any particular order. So there's no guaranteed order in how they're retrieved, but it will return them all. So I have a for each loop with for string email email username.keyset. So this returns all of the keys, and on each iteration of the loop, it stores the key value in email. So system.out.println, the email variable plus a colon in between each, and then I concatenate email username.get by the variable email. We can also loop over all the values, but we can't get the key based on the value. So it doesn't work in reversed, but we can extract just the values and print them using a for each loop as well. So for string username email username dot values. So the values method returns all of the values, and we loop over them calling system.out.println of username. Now I'll use Shift F10 to run the code, and we'll have a look at the results. So in the results, the first output is the size. So the size after I've put 3 elements in, which returns 3. The username associated with steve@example.com at this point in the code from line 16 is Steve456. The non-existent email returns null. After I remove bob@site.co.uk, we're left with 2 elements in the hash map. And when I loop over using the key set, so that was from line 29, I have alice@somewhere.ca ;havingfun55 and steve@example.com ;steve123, which we changed on line 26 by calling the put function with steve@example.com and giving it a new value. And the values from the final loop give us having fun 55 and Steve123. And that concludes this demonstration of programming with Java's Hashmap. In this video, I'll describe Java's Hashset class. So the Hashset is a collection of elements. So it's a container that contains unique elements of a particular type that's parameterized when we create the object. Duplicate elements are not permitted in a Hashset, so it's a unique collection of elements. If you try to add something that already exists, nothing happens. And this includes a null element. And although null is allowed, only one is allowed inside of your Hashset. It also implements the set interface, which is also a member of the Java Collections framework. What are some features of the Hashset? Well, elements are not ordered. The Hashset makes it performant in adding, removing, and checking to see if elements exist in the set, but not for their order. So this is not for an ordered set of elements. It allows null, but only one, and it has consistent performance for operations. So the runtime in big O notation would be O of 1 for operations to test the existence, to insert and remove elements from the hash set. So how do we declare and create a hash set? Well, we need to import the Hashset class from java.util.hashset. We declare with Hashset and the parameter in angle brackets, in this case, a hash set of strings called myHashset. And we create the hash set with myHashset equals new Hashset with the string parameter and open and close parentheses. where we can specify an initial capacity if we wish. How do we use the hash set? Well, to add an item, we call the add method. So my hashset.add and the string oranges adds oranges to the hash set as an element. We can loop through the hash set, but not in any particular order. And there's no guarantee after removing or adding another element that the items will stay in the same order. I can loop using Java's for each syntax with for and then in parentheses string I colon my hash set. Then inside the body of the loop, I call system.out.println to print the element I, and then I close the loop. We can modify elements, we can remove an element, my hashset.remove oranges, and we can clear the hash set or empty it out calling the clear method, my hashset.clear. And we can get the current number of elements by calling size, for example, my hashset.size. How do we test for the existence of an element to see if the hash set contains the element? Well, we call the contains method. For example, if my hashset.contains oranges, system.out.println found oranges. So calling the contains function returns a true or false, telling us whether the element exists. And that concludes this presentation on Java's hash set. In this video, I'll demonstrate how the Hashset class is used in Java. So the Hashset provides for fast insertion and removal, and it's fast to check the existence of an element in the set. And it's fast to check the size of the set at any given time. However, it's not an appropriate container for ordering, nor traversing in a particular order. So if you need an array of things or a container of things that's sorted, a Hashset is not what you want to use. So I start in this main.java file by including this in package com.example, and I import java.util.hashset. Then in my public class main, inside of the main function, the entry point into the application on line 8, I have hashset parameterized by string, so string in angle brackets, called names equals new hashset, the open and close angle bracket, and the open and close parentheses to call the constructor. Now that it's created, I can add elements. So I call names.add with the string Steve. Then I do the same for the string Mallory, Alice, Jane, and the empty string. Then on line 16, I call system.out.println names in single quotes has names.size elements. So the size function returns the number of elements. And then what happens if we try to add an element to a hash set that already exists? So system.out.println add Steve again. So names.add Steve with the same case, so an uppercase S, T-E-V-E. Then system.out.println new size, names.size. Now in this case, the size will be the same because Steve already existed and it won't add duplicates of entries into the hash set. It's also case sensitive. So if I call system.out.println to check to see if it contains Steve spelled with a lowercase s by calling names.contains Steve, so the contains function checks for the existence of an element. In this case, it will return false. But if I call contains on the string Mallory, spelled correctly with the uppercase M, it should return true. Let's say I want to get rid of the empty element or the element with the empty string. I call names.remove with the empty string and it will remove it. If I want to empty out or clear the hash set, I call names.clear, and I can check to see if that worked by calling names.isEmpty. So I print that result at the end. Now I'll do Shift F10, and in the results, I get that names has 5 elements. I add Steve again, and its new size is 5. It's still 5 because it didn't re-add Steve because it already existed. Then my check to see if it contains Steve spelled incorrectly with a lowercase s, it returns false. So it is case sensitive. And then if it contains Mallory, that returns true. And then after I call clear, isEmpty is true at the end. And that concludes this demonstration of programming with Java's hash set. So in this course, we've examined how arrays and array lists are designed to handle looping through lists of data. We did this by exploring programming Java arrays and array lists, using Java iterators and linked lists, and programming Java Hashmap and Hashset. In our next course, we'll move on to explore the components of a basic Java program, such as classes, attributes, methods, and variables.
In this video, we'll describe what classes are and how they are used in Java. A class can be thought of as a blueprint. For example, we can have a car as a class, and the car class will be a blueprint of a car. So we could think of the different attributes that a car has, such as a make, model, color, and price. We could think of the different methods it has, such as speed up, slow down, stop, and start, and so on. So the class defines all the attributes and all the actions that could happen to that particular item that we're trying to describe with the Java programming language. Now, an object is an instance of a class. So a class could have one to many instances, and each instance of a class can be different because we could pass in different parameters when we're instantiating the class. And instantiating the class gets done through a constructor. So for the car example, we could have a car that's a Toyota, for example. So the make would be a Toyota and the model would be a Corolla. It might be a red color and the price might be $10,000. And we could also have another car object that could be a BMW X3 that could be gray and cost $30,000. So there's some examples of objects. As we mentioned, a car is a good example of an object, and that would be an instance of the car class. We could also have a class called dog, and the dog class could have various attributes such as the breed of dog, the age, the color, and so on. And then when we instantiate that class of dog, we're going to have an object of dog. And we could have various types of dogs by passing in different parameters when we're instantiating a dog, such as a different breed, different color, different age, and so on. Another example would be an employee. So an employee could be a class, and we could then instantiate an employee, and we could have an object of employee. So examples of attributes for the employee class would be first name, last name, salary, age, and so on. And then we could create various employees within an organization based on that class blueprint, and each employee would be its own object. So we could pass in, for example, a name of Fred, a last name of Smith, salary of $50,000, and an age of 30 years old. So that would be an example of one object, and then we could create objects for each employee within the organization using that employee class blueprint. So object-oriented programming is really based on classes and objects. So classes have attributes. So we were speaking about attributes previously, and basically an attribute, as we said, for a car could be the make, model, color, price, and so on. For an employee, it could be a first name, last name, email address, age. And for a dog, as we mentioned, it could be the dog's breed, the dog's age, the dog's weight and height. Now, methods in a class are what used to actually define the actions of that class. So a method of a class, for example, for a car could be turn on. So we could turn the car on. We could have a method that increases the price of the car or decreases the price. So we're modifying the attributes by those methods. We could also have methods that get and set certain attributes, which we'll cover later. So basically, we could pass in a parameter into the method to set a value of an attribute or to get the value of an attribute, and this follows proper encapsulation. We could also have methods, for example, in the case of an employee, to make the employee older, to increase their salary, to change their first name, change their email, and so on. So as we mentioned, for the attributes, so for the car, we could have a make, model, year, and color. For the dog, we could have the breed, size, color, and age. And for the employee, we could have a name, age, position, and salary attributes. So as we mentioned, for the methods, for the car, a car could be parked, it could be started, it could be driving. We could think of all the different states or actions that could happen to a car and implement methods for those within our car class. For the dog, he could be wagging his tail, he could be eating, sleeping, and so on. And we could also, once again, think of a comprehensive set of actions that dogs can do and add those methods within our dog class. And for an employee, they could have different states, so they could be at work, traveling, or on vacation. And once again, we could think of more things. They could be eating, they could be exercising, sleeping, and so on. And we could add all those methods to the employee class. So in order to create a class, we are going to specify public, which is our access modifier, space class space fruit. So this is a class that's defined with the public access modifier, and the class is called fruit. We're then going to have an opening bracket, and we're going to make sure that at the end of our class, we have a closing bracket, and everything contained within the class is between the two brackets. So here we have an attribute, string fruit is equal to apple. So we're creating a new attribute or instance variable of the class called fruit, and we're setting that equal to apple. So now to create an object, we're going to instantiate the class. So we have public class fruit, we have attribute string fruit equals apple, and then we're going to have our main method. So the main method is what Java goes into to run our program. So public static void main, it's going to take a string array of arguments, so we're not going to be passing any in. And what we're going to specify is fruit, so we're specifying the class name space, the name of the object, so it'll be called fruit, and then uppercase obj or fruit object equals new. So new calls the constructor of the class to instantiate a new object or a new instance of that class, and fruit. And notice that we're not passing anything in because we didn't define a constructor that takes any parameters. Now we'll go over this later in the course, but a constructor can take either no parameters or multiple parameters to set the attributes or instance variables of the class when that object gets instantiated. So right now we're not passing anything in because we don't have a constructor that takes in any parameters. So we just have a open bracket and close bracket. So this is going to instantiate a new object called fruit object. And then below that we have system.out.println, which is going to print to our console fruit object.fruit. So we're accessing that attribute or instance variable, and we're going to get apple, and that what we see in the output, we see apple. And once again, under system.out.println, we have a close bracket to close the main method, and then another close bracket to close public class fruit. So now to create multiple objects. So in order to create multiple objects, it's similar to creating a single object. So we have our public class fruit again, we have our string fruit equals apple, we have our main method, and then we have fruit object 1 equals new fruit. So we're instantiating a new object from that blueprint, from that fruit class. Then we have fruit object 2 equals new fruit. So once again, we're instantiating a new object that's going to have a different memory address, and it's going to be called object 2. And then we're going to print out object1.fruit and object2.fruit. And we could see they're both identical because we haven't modified that string apple within the two objects. So it's just going to print out that string apple. In this demo, we're going to go over creating a new class and running it. So here I am in my Ubuntu 18.04 environment, and I have IntelliJ IDEA Community Edition open. We're going to go ahead and click on File, New, Project. We're going to select the project SDK as Java version 1.8, click Next, and then we're going to pick a project location. So in my case, it'll be my home Boris directory, and I'll go inside my code directory and inside my classes directory and click OK. I'm going to give my project a name of car. I'm then going to click Finish to create the project. It's going to ask me if I want to open it in this window, and I'll say yes, this window. So here I have my template of my project in the left-hand pane. I could click on the arrow, and I could see my whole project structure is defined, including my external libraries. So let's create two new classes inside the source directory. We're going to right-click on the source directory, click on New Java class. We're going to create one class called car, and another class that's going to be called main. So let's start working on car. So the public class car is going to have a few instance variables which are going to define the characteristics of a car. So we could think about the classic characteristics of a car. So we could have a string make on line 2, On line 3, we'll have a string model. On line 4, we'll have a string color. And on line 5, we'll have an int price. We could then go ahead and create a constructor to initialize all our instance variables for our car object. So let's create a constructor for car, and it's going to take 4 arguments. So it's going to take a string make, string model, string color, and an int price. Inside our constructor, we're going to initialize all our instance variables. So we're going to use the this keyword, which is essentially going to refer to the instance of the object that we're speaking about. So this.make is going to refer to the make instance variable for that instance of the car object. And we'll set this.make is equal to make, which will get passed into the constructor as a string parameter when instantiating a new car object. This.model is equal to model. This.color is equal to color. And this.price is equal to price. So that completes our constructor. Now we could create some more methods, and we could play around a little bit and see how our class comes together, and then we could test it out inside our main.java class. So what we're going to do now is we could actually right click and click on generate, which is a shortcut in IntelliJ IDEA. And we could set and we could generate a toString method. So we could click on toString. We're going to select all the instance variables and hit OK. That's going to override the default toString method and return a toString or a string representation of our car with the make, model, color, and price. So now that we have our basic car class defined, we could go ahead and save it. And now we could go inside our main.java class, and inside public class main, we're going to define our main method which Java is going to execute our program from. So public static void main, it's going to take a string array of arguments, and inside this method we're going to be instantiating a new car. So car BMW on line 4 was new car. We're then going to have to pass in our constructor parameters. So the make is going to be a string BMW. The model will be a string x3. The color will be gray. And the price will be 30,000. So now that we have a new car object, we could then do a system.out.println on line 5 and simply say BMW.toString, which is going to return the string representation of our car. So let's go to File, Save All. We could click on Main, right-click, and click Run Main.main. So we're going to open up the build window and see the compilation, and we could see that it executed. We have our make BMW, model X3, color gray, and price 30,000. Now, if we wanted to change the price, for example, what we could do is we could say BMW.price equals 20,000, for example. And we save that and rerun it, and we should now see that we actually have a price of 20,000. So this is just a very simple example of how we could define a class for a car, define some instance variables, define a constructor, and then override the toString method, and then inside another main class, define a main method and instantiate a new car object and call the toString method. In this video, I'll talk about access modifiers in Java and how to use them. So there's 4 access modifiers in Java: public, private, protected, and default. Access modifiers help us in encapsulation and limiting the scope of classes, fields or variables, constructors, and methods in Java. The default access modifier is applied if no access modifier is specified. The public access modifier is the least restrictive, with the private being the most restrictive, and protected is in between public and private in terms of its restrictiveness. So access modifiers can be set on fields or variables, constructors, methods, and classes. So an example of an access modifier on a field could be within a class, you could have, for example, a car class. You could have an instance variable price. So you could have a private int price, and that would set that price variable to only be accessible within that class. You could have access modifiers on constructors. So if you have a private constructor, it would only be accessible within the class, and you wouldn't be able to call that constructor when instantiating a new object from outside the class. You could have access modifiers on methods. So once again, you could have private or protected or public methods that are only accessible either within the class or within the package by other classes. For classes, you could only have either the default access modifier or the public access modifier. You cannot have the private or protected access modifier for classes. So first we'll talk about the public access modifier. So the public access modifier allows access from everywhere, whether that be inside or outside of a class, or inside or outside of a package. So generally our classes are defined with a public access modifier so that our classes could be instantiated from anywhere, from any class, anywhere in the program. And this is really used because it gives us the most flexibility in where the different classes, fields, methods, or constructors could be called from. The private access modifier is the most restrictive, and it basically only allows access within a class. So if we have private integer within a class, that integer is only accessible within that class by the methods of that class. Any methods that try to call or update that variable from outside the class, even if they're in the same package or even if they're child classes of that class, are not going to be able to modify that variable. The protected access modifier is in between the public and private access modifier in terms of restrictiveness. So it allows access to fields, constructors, and methods inside a package. So any class within that package can basically call anything that's protected by the protected access modifier. It also allows access to fields, constructors, and methods that are outside of a package, but that are part of a child class. So that could be, for example, if we have a class as shape, and then inside that shape class, we have a child class that extends a shape class called rectangle. So rectangle would be able to access everything, all the protected members of the shape class. And finally, we have our default access modifier. So that allows access inside a package like the protected access modifier does. And basically, if we don't specify anything in front of a field, constructor, class, or method, Java is going to revert to the default level access modifier. So let's take a look at examples of access modifiers. So we have public class fruit. So remember, the classes can only be defined with either a public or a default access modifier. So we have public class fruit. And then we have private access modifier on our instance variable price. So private int price equals 10. So this means that anyone trying to access our int price outside of the fruit class won't be able to. Now we have below that, we have class fruit. So notice we didn't put the default access modifier because if we don't specify anything, the default access modifier is used. We have protected int price, which essentially means that instance variable is going to be accessible by any class within the package, as well as any child classes of the fruit class. Now let's take a look at an example of using access modifiers. So here we're defining a class multiply with a public instance variable called multiplier and setting that to 10. And then we're going to have a public int multiply, which is going to be a method. And it's basically going to take a number to multiply. And notice that number we just have int num to multiply. There's no access modifier in there. Then we're going to return num to multiply times multiplier, which is set to 10. Below that, we have public class perform calc. And we have our main method, so public static void main. And inside that method, we're defining a new object num1 of type multiply. And we're instantiating it by calling new multiply. So we're instantiating the multiply class in the object num1. And then below that, we're running system.out.println to print to the console num1.multiply 5. So we're calling that multiply method and passing in 5 for int number to multiply. And then it's going to return num to multiply times multiplier. So we're going to get 5 times 10 or 50 as the output to our console. Now notice that if we changed inside the class multiply, if we change this int multiply method, if we change the access modifier to private, we would throw an exception in Java when we're compiling because we wouldn't be able to access that private int multiply method from public class perform calc because it's in a different class, and private access modifiers only allow us to access methods within the same class. In this demo, we're going to talk about modifiers and specifically using the private modifier in our classes. So here I am in my Ubuntu 18.04 environment, and I have IntelliJ IDEA Community Edition open. I'm going to click on New Project, and I'm going to set the Java version as 1.8. Click Next. Click Next. I'm going to select a directory to put my project in. So under my home bars, code directory, Java, I'm going to put it in the modifiers directory. Click OK. And my project name will be car, and I'll click Finish. I now see that I have my basic project structure set up, and including my external libraries as well. So now I could click on my source directory, and I could right click and click on New Java Class. So we're going to be creating two classes similar to the previous demo. The first one's going to be car, and the second one is going to be main. So let's start working on our car class. So just like before, we're going to define some instance variables. So we're going to have a string make, string model, string color, and then int price for the car. We can now generate a constructor. So one trick to generate the constructor, we could right click and click on generate in IntelliJ IDEA and click on constructor. And we'll click Control and select all 4 instance variables and click OK, and that's going to generate our constructor for us. We could also right click and generate a toString method. So click on toString, make sure all 4 instance variables are selected, and click OK, and we have a toString method. So now let's go to our main.java class and let's define our main method. So public static void main. And we're going to take a string of arguments, a string array of arguments. So now what we could do inside here is we could instantiate on line 4 new cars. So car BMW hosts new car. And we're going to call the constructor. So we have to specify make BMW a model X3, a color, which will be gray, and a price, which will be 30,000. And now we could go ahead and call the toString method on BMW object and display that with system.out.println on line 5. So let's go ahead, save that, and just run program and make sure everything works, just like in the previous demo. So we should expect to see we have our car. So makes BMW models X3, colors gray, price is 30,000. So now let's try to change the color. So let's say BMW.color equals red. So we want to get the red BMW instead of the gray one. What we're going to do differently now from the previous demo, however, is we're going to go back to the car.java class, and under the instance variable for color, we're going to say private string color. So if we go ahead and save that, we could already see IntelliJ is already giving us a problem. So let's try and compile that and see what issue we get from the compiler. So we could see here Java color has private access in car. So since we've set the instance variable color to private, we can now no longer access it in the way we were accessing it before when it was public by simply doing object.instance variable. So How do we get around this? Because this is what we're going to need to implement in all our projects adhere to encapsulation standards. So one thing we could do is we could create getters and setters. So IntelliJ IDEA has a quick way of doing that with the generate method. So we could right click and go to generate, and we're going to select getter and setter. We're going to click control and select all 4 of our instance variables and click OK. And we can now see that we have getters and setters for each instance variable. So if we look at the make one, get make, between lines 14 and 16, we could see that we're simply returning the make as a string. Between lines 18 and 20, we have set make. So we're actually taking a parameters of type string make, and we're setting the make instance variable of the object to the make parameter that we're passing in. So now let's go ahead and set all our instance variables to private access. And then what we're going to do is we're actually going to go ahead and we're going to call those getters and setters. So instead of in our main.java class, instead of on line 5 doing bmw.color equals red, let's do bmw.setColor, and we'll pass red in as the string argument for that method. Now if we call the toString method, we're just going to save and rerun. We should see that we're now actually getting the red BMW. We're not getting compilation error, which we are. Now let's try using a getter. So bmw.getPrice. And before that, on line 7, let's actually do a bmw.setPrice. So we're going to change the price. So it's currently at 30,000 set on line 4. Let's set it to 50,000. So maybe we got like the M model or something. And then we're going to run the bmw.getPrice on line 8, which is going to return a string. And we could output that string with a system.out.println statement. And we should see that we're now actually going to have a price of 50,000. So let's go ahead and save and rerun. And we could see here that our price is now 50,000. So by using getters and setters, we were able to use the proper encapsulation and set all our instance variables in our car class to private. And now we have all the proper ways to access them from another class by utilizing our getters and setters that we created. So that's it for this demo. In this video, I'll describe how members are used by classes in Java. So Java members, or instance variables, are variables that define the state of a class. And the variables really are used to define attributes of a class. So we mentioned in a previous video about a car. So instance variables could relate to the car's make, model, price, and so on. So it describes the different attributes of a car, and they're declared within a class. And generally, instance variables are defined right after the class definitions, right at the top of a class, and they could use access modifiers as well, with the private access modifier being preferred for encapsulation. And we want to define all our instance variables outside any methods or the class constructor. So an instance variable gets created when an object is instantiated by using the new keyword. What ends up happening is that Java allocates space on our memory heap for each instance variable. So any method within a class could access the instance variables and modify them, even if they're defined with the private access modifier, because even with the private access modifier, any method is able to access the different instance variables within a class and modify their states. So once an object is no longer needed and gets destroyed by the Java garbage collector, all the memory in the heap that was reserved for the instance variable is then released back for use with other things in the program. So with instance variables, the order of defining them is not important. For example, in the car example, we could have the model above the make or the make above the model. It doesn't matter when we're defining them. We can use access modifiers. So as we mentioned, we could have public, private, protected, or if we don't specify any access modifier, it would just be default. The private access modifier is preferred for encapsulation reasons, however, and we will go over this more in other videos with getters and setters and how we could use the private access modifier with instance variables. So instance variables could also be set to default values. So for example, we could set the price of a car by default to be $20,000. And these default values could also be updated in the constructor by passing parameters from the constructor call. So for example, if we have a constructor for car and someone wants to instantiate a car object, they could pass in the price for the car that they want, and that price could then update the instance variable within the car class. And as I mentioned, private is recommended for the access modifier for the instance variables, just because private gives us the best encapsulation and protects our data, and that's very important in object-oriented programming principles. So here's an example of some instance variables. So we have public class car, and we have a private string make and a private string model, which are attributes of a car. And then we have a constructor. So we have public car, and the constructor takes two parameters. It takes a string make and a string model. Now, notice that I've actually used the same variable names as the instance variables in our constructor. So this is common principle in Java. And basically what we do to get around this is we use the this keyword. So this essentially references to this instance of the object. So by specifying this.make equals make, we're saying the instance variable make is equal to the parameter make that we're passing into the constructor. So we have this.make equals make and this.model equals model. So we're essentially setting the default value of the make and model of the car when the constructor gets called. And whoever's responsible for calling the constructor with the new keyword is responsible for passing in the make and the model of the car into that call so that we could properly initialize our instance variables. So another example of using instance variables, we have public class fruit. So notice we've used the public access modifier for the instance variable, so public string fruit type. So this is going to be accessible to any class. We have our constructor public fruit, and it takes a string fruit1, and we're setting that fruit type to that parameter we pass in. And then we have public void display fruit, and we're just printing to console with system.out.println type of fruit plus fruit type. Below that, we have our main method public static void main, and we're defining a new fruit object fruit1. So we're calling the constructor by using the new keyword new fruit, and we're passing in the parameter. So if we look at the constructor, it takes one parameter, which is a string. So we're passing in the fruit type, which is an apple. And then below that, we're calling the display fruit method. And notice that once again, it has the public access modifier, so we could call it and fruit1.displayFruit, and we're going to get type of fruit apple. So that's it for instance variables. Let's get started. In this demo, we're going to go over programming class members in Java. Here I am in my Ubuntu 18.04 environment with IntelliJ IDEA Community Edition open. Let's open the existing project from the assets. So we'll click on Open, and we're going to select the Objects and Members project and click on OK. You could see here, if we quickly go over it, it's very similar to the previous two demos. We have in our source directory two classes, a car class and a main class. Our car class has several instance variables. We have a make, model, color, price, and an int for the horsepower of the car. We have a constructor that initializes everything. And we also have getters and setters for each of our instance variables, and a toString method that prints out a string representation of our class. Inside our main.java file, we have main method, public static void main, and here we're instantiating a new car object with a make of BMW, models X3, colors gray, price is 30,000, horsepower is 250, and then we're going to print that string representation of that object by using the toString method defined on line 5. So now we could go ahead and right-click on main and click run main.main. And inside our build window, we should see that we build successfully, and then we execute. And we could see the car make is BMW, models X3, colors gray, price is 30,000, horsepower is 250. Now let's go back to our car.java file, and we're going to be creating some more methods. So let's create a method called private void set power. And this method's not going to take any arguments, and we're basically just going to have an if statement. So if horsepower is less than 300, we're going to add an extra 50 horsepower. And so this is a private member method, so it can't be called from outside of the class. So we're going to call it from the public setHorsepower method. So what we're going to do is just going to call setPower. And notice that we're not returning anything from setPower because the horsepower instance variable is accessible to all methods inside the car class. So what's going to happen is if we enter in with a horsepower of the car, if the current horsepower of the car is under 300, we're going to add 50 to it. And then we're going to add the horsepower that we're passing in through that int horsepower parameter on line 52 for the setHorsepower method to the current horsepower. So let's go ahead and save that. And inside main method, we could try and run that call. So let's do bmw.setHorsepower. And let's try adding 50 horsepower. So now we should see the end result of 350 horsepower because when we go inside the setHorsepower method, the setPower method, our current horsepower is only 250. We're going to add 50 on line 59, getting us to 300, and then we'll add the remaining 50 that we're passing in to the setHorsepower method. So let's try running that and see what happens. And we could see we have 350 horsepower. Now what we could try is, just for fun, let's try calling that setPower method directly from main class to see what happens. So bmw.setPower. And we could see that it doesn't let us because it says setPower has private access in car. So because of that encapsulation, that member method setPower can only be called from within the car class. What we could do, however, is change the access modifier to protected on line 57. So that means that any class within the package, including subclasses, could now call that setPower method. And since our main class is in the same package as our car class, we could now actually call that setPower method. So you could see it's not giving us an error anymore. If we now go and run, we could see we're getting 300 horsepower, which makes sense because we're calling setPower directly. So if horsepower is less than 300 on line 58, which it is, it's 250, we're going to add 50, which is going to bump up our horsepower to 300. And then we're simply on line 6 in the main method doing BMW2string to print out a string representation of our BMW object, and we're getting 300 horsepower. So that's how we could adjust and modify class instance variables and our class member methods. In this video, we'll talk about different types of variables: class variables, instance variables, and local variables, and how they relate to Java. Class or static variables are variables that are defined with the static keyword within a class outside of a method and a constructor, and there's only one instance of the class variable for the class. So if an object gets instantiated for that class, it's only going to have that same one instance of the class variable. Instance variables we took a look at before, and they essentially describe our different attributes of our class, and they get created on runtime when a class gets instantiated, and they get deleted when a class gets deleted. And instance variables are unique to each object. Local variables are variables that are only alive or existing within a method. And when that method exits, the local variables then get destroyed. They're unable to be accessed from outside of a method. So let's start talking about class or static variables. So class variables, as I mentioned, are declared using the static keyword. So for example, for an integer, you would have a static int price, for example. So they're declared inside a class, and they're declared outside of a method or a constructor. So in the same place where an instance variable would be defined. And the important thing with static variables is that there's only one copy per class. So that essentially means that, for example, if we have a class car, if we keep instantiating objects of type car, we're going to keep getting more and more instance variables. So each object is going to have its own instance variables. However, each object is going to share the same class variable. So we're only going to have one copy of a class or static variable per class, and that variable will be able to be accessed by the class name. So for example, car dot and then the static variable name, for example, price. Whereas if we're accessing instance variables, we're going to write the object name dot and then the instance variable name. So now let's talk about instance variables, which we've already covered in some previous videos. So they're also known as member field variables. They're declared outside of a method or constructor within a class. And they're referenced by one or more methods. So the instance variables really define the different attributes of a class. For example, for a car, we could have a make, model, color, and price. As instance variables, they get initialized usually within a constructor, and then different methods within the class could use the instance variables to update the object state. Finally, local variables. So local variables are declared in methods. They are created by the method, the call stack. So essentially when a method gets called, the local variables are pushed to the call stack, and then once the method exits, they're popped from the call stack and they no longer exist. The scope of the local variables is only within a method. So for example, if we had two methods within a class and one method had a local variable called price, if the second method was trying to update that local variable price, it wouldn't be able to because the scope of a local variable is only within the method that it's defined in. So let's take a look at an example. So we have public class variable types. So we have an instance variable that's a double, so double instance variable. Below that, we have static int class variable equal 10. And we have our main method, so public static void main. It takes a string array of arguments. And we're setting int local variable equals 100. So this local variable is only in scope inside that main method. So outside of the main method, if we try to access the local variable integer, we wouldn't be able to because it would be outside of the method. Below that, we have we're defining a new object of type variable types, and we're calling the default constructor with the new keyword. And then we have three system.out.println to print to the console. So the first one's going to print the class variable. And notice that to print the class variable, we're going to write the class name, so variable types.class variable, and that's going to output 10. Below that, we have system.out.print, and we have instance variable. So to print out an instance variable, we're going to specify the object name. So different from the class variable where we specified the class, in the instance variable we'll specify the object. So object dot instance variable, and then we're going to be printing out the value of that instance variable, and that is going to be 0.0 because it's a double and we didn't define any default value, so it's going to revert to the default double value, which is 0.0. And finally, the last system.out.print statement, we're printing the local variable and we're printing the value, which it got set to 100. And we're going to see the local variable value as 100. So that's it for class, instance, and local variables. Okay, let's get started. In this demo, we're going to be going over different types of variables. We're going to cover instance variables, class variables, and local variables. Here I am in my Ubuntu 18.04 environment, and I have IntelliJ IDEA Community Edition open. What I'm going to do is I'm going to go ahead and click the Open button, and I'm going to open up my variables project that exists in our code assets for this demo. I'm going to click OK, and that's going to open up my project. We could see, just like in our previous demos, in our source directory, we have two classes. We have a main class and a car class. The car class is simply going to define a car with some instance variables, which are going to define the attributes of a car. So we're going to have the string make on line 3, on line 4 string model, on line 5 string color, and on line 6 int price. Notice that we're also using the private access modifier for encapsulation purposes. So instance variables exist basically throughout the lifecycle of that instance of the car class. So if we go to main.java, we could see here that we're defining a new instance of the car class called BMW, and we're calling the constructor by using the new car keyword and passing in parameters here on line 4. So basically what we're doing by passing in these parameters is that we're initializing the instance variables for that instance of the car class. Now there's two ways we could go about editing the values of the instance variables. One way would be to just type in the object or the instance of the class that we want to edit and then do a dot, and then we could, for example, say color equals red. So this only works if we don't have the private modifier in front of the color instance variable, which we do in this case on line 5, because otherwise we get the error message color has private access in car. So one way we could get around this, which we covered in a previous demo, is to actually create getters and setters. So if we take a look at color, we could scroll down between lines 31 and 33. We have public string get color, which returns our color. We also have between lines 35 and 37, public void set color, which takes a parameter, string color, and it sets the instance variable for that object using the this keyword. So this.color is equal to the color parameter we pass in. So we could try that. Instead of doing bmw.color equals red, let's say bmw.set color, and then we're going to pass in red as the string parameter to that method. Then when we call the system.out.println on line 6 and we do a bmw.toString, we should now see that the color is in fact going to be red. So we could go ahead and run the program. And we should see that, yes, we do have the color as red. So that's it for the instance variables. Let's move on to the local variables. So let's go ahead and create a new private method within a car class. And it's just going to be called unique color. So what this method is going to be doing is we're simply going to specify a unique color and set color to that method. So let's define a local variable here. So we're going to define string unique color is equal to aqua. And that's defined on line 49. And then what we're going to do is we're going to set the color to the unique color. So now we have this method and we have a local variable called unique color that's set to aqua. Well, instead of calling this method, what if we just wanted to access that unique color local variable and set the color to the unique color inside public void set color method? So let's try doing that. So color is equal to unique. Instead of calling the method itself, we could simply try to set it to that local variable. And you see we can't do that because we get the error message cannot resolve symbol unique color. This is because the local variable only exists in the context of that private void unique color method defined between lines 48 and 52. Any method outside of unique color that's trying to access that unique color local variable will not be able to. Finally, let's move on to class variables. I'm just going to get rid of this method, unique color, and we could go over class variables. So class variables exist for the duration of the program, and they're defined with the static keyword. So if we want a class variable horsepower, we could specify int static int horsepower, and we could set it to some value, let's say 300. So this class variable is not associated to every single instance of the car. It's actually associated to the car class itself. So it is different from the instance variable. So if we go back to main.java, one way we could edit class variables, instead of having to instantiate the actual class as an object and then call the variable or the setter method from there, what we actually do is we call the class itself. So car dot horsepower, and we could set a new value like 400. So you could see that we're actually able to do this by directly calling the class instead of calling an instance of the class, for example, BMW. And just to make sure it works, we can actually go ahead and run, and we will see that we get a program that's properly compiling. So that's static. So that static variable on line 7 in the car class, static int horsepower, is going to be valid for the duration of the program, and it doesn't depend on the instance of the class getting garbage collected, such as the instance variables. And the same is true for methods. So you could see our main method is declared with the static keyword because it's alive for the duration of the execution of the program. So that's it for instance variables, local variables, and static class variables in Java. In this video, we're going to describe the concept of overloading and how it relates to methods and constructors in Java. So Java constructor overloading essentially lets us define multiple constructors that take different numbers of parameters. So basically what we could do is, for example, if we have a car class, we could have a default car constructor that doesn't take in any parameters and just initializes our instance variables to default values. We could then also have a car constructor which takes in just the price, and we could set the price. And we could finally have a car constructor that takes make, model, price, and year of the car, and we could set all those instance variables in that constructor by the different arguments or parameters that we pass in. So why should we use Java constructor overloading? It's very useful for different objects. So different objects might have different uses. For example, we might just want to create a car and we might just care about the price. We don't care about the other values. We want them to be set to the default so we don't have access to the other values to pass them into the constructor. So we could just call one constructor that just takes in the price in that case. In order to do that, we're going to be using the new keyword to instantiate a new instance of the class. So for example, for the car example, we could have car BMWs equals new car. And then within the brackets, we're going to specify what we're passing in. So we're going to specify the parameter list. So if we don't specify any parameters, that's going to call the default constructor with no parameters, or we could specify 1 to any number of instance variables for the different constructors that we've defined within our car class. So some rules for Java constructors, they must be the same name as the class. So for example, if we have a class car, our constructor would be public car. So it has the same name as the class. And we never return a value. So unlike a method, a constructor is always void, so it never returns a value. So by defining a car constructor, we would just define public car and a list of arguments or parameters, and that's it. We never have to worry about returning a value from a Java constructor. So the constructor syntax, to call a constructor, we're going to use the new keyword to instantiate a new instance of a class. For example, here we have my class variable. So that's the object name, class variable, and we're using the new keyword to instantiate a new instance of my class. To pass an argument to a constructor, we'll do the same thing. So my class variables equals new my class. However, you could see here that brackets are left empty. To call the default constructor here, we're putting 100 in to pass in that integer that's a parameter or argument to the my class constructor. So we have multiple constructors in this case for different uses with different objects. So another example of using constructors, so we have public class overloading. We have a private string myvar, and we have our constructors, so public overloading. And this constructor takes no arguments or parameters. So inside it, we're just setting myvar to a default string that's going to be hard-coded, so testing overloading. Then we're going to have a second constructor that's going to take a string as a parameter. And we're going to use the this keyword. So we're passing in a string myvar, and the this keyword specifies the instance variable that belongs to this object. So this.myvar equals the string that we're passing in myvar. So in this case, we'll be able to actually pass in a string and customize the value of the myvar instance variable. Finally, we have a public string getMyvar. So we have a getter here that's going to return myvar. The reason being is that we've defined myvar with the private access modifier. So if we don't have that getter method, we won't be able to directly access myvar from outside of the class if we're trying to get that value. So next we have our main method, and we're defining a new object of type overloading called overload1. And we're just calling the default constructor with the new keyword, so we're not passing in any parameters. And then we're going to do a system.out.print overload1.getMyVar. So in this case, we should expect to have testing overloading because we're not actually updating that value. We're just calling the default constructor, which sets myvar to testing overloading by default. Under that, we're creating a second object of type overloading called overload2, and here we're calling that second constructor that takes a string parameter, and we're passing in overloading work. So in this case, we should see, instead of testing overloading, we should see overloading work because we're setting myvar to that value that we're passing in. And when we do a print on the line below with overload2.getMyVar, we get overloading work. So that's it for using constructor overloading. In this demo, we're going to talk about overloading constructors. Here I am in my Ubuntu 18.04 environment, and I have IntelliJ IDEA Community Edition open. What I want to do is I want to say new project. I'm going to select Java Project SDK version 1.8, click Next, click Next. I'll pick a directory. I'll put it in my code Java overloading directory and click OK. And the project name will be car, and I will click Finish. And it's asking that it already exists. Would you like to overwrite it? I'll say yes. And that's going to go ahead and create my project. I'm going to be creating two classes just like before. We're going to have a main class, and we're also going to have a class called car within our source directory. So let's build our car class. So we're going to have some instance variables. So private string make, private string model, private string color, and private int and price. And we're also going to add another instance variable. So this one is going to be called all-wheel drive, and it's going to be a Boolean. So private all-wheel drive. So now let's go ahead and generate a constructor getters and setters in a toString method for our car class. So we'll right click, go to generate, we'll click on constructor, we'll click control, select all 5 of our instance variables, click OK. Then we'll also right click and click generate, and we're gonna say getter and setter. We're gonna click control and select all 5 instance variables and hit OK to get all the getters and setters. And finally, right click, generate toString, and make sure all 5 instance variables are selected, click OK, and we get a toString method. Now go inside our main class. We're gonna create main method. So public static void main string args. And inside here, we're going to be instantiating car object called BMW and passing in the parameters. So the make will BMW, the model will be X3, the car will be gray, the price will be 30,000, and the all-wheel drive, we're going to pass true. And we're going to do system.out.println on line 5, and we're just going to do BMW dot toString. So now let's save it, and we could right click on main and click on run. And we're going to build it, and we could see that everything works as expected. So we have our make BMW model X3 color gray, price 30,000, all-wheel drive equals true. So we've seen this in previous demos. Now let's go ahead and overload the constructors. So back to our car class. Inside this class, we're going to be creating 2 more constructors. So one is just going to be public car, and it's not going to take in any parameters. So in this case, we're going to initialize all the instance variables to default values without initializing them to the parameters of the constructor. So this dot make, we're just going to leave it as an empty string. This dot model will also be an empty string. This dot color, once again, empty string. This dot price So the price will be 0, and this dot all-wheel drive will equal to false. We're also going to go ahead and create another constructor that is simply going to take one parameter, which is all-wheel drive. So it's going to be public here on line 24 car, and we're going to have a Boolean all-wheel drive. And what we're going to do here is we're going to call this. By calling this on line 25, what that's essentially going to do is it's going to call our default constructor, which in this case is the car constructor with no parameters defined between lines 16 and 22. And it's going to initialize all of our instance variables. And then what we could do below that is say this dot all-wheel drive equals all-wheel drive. So we're going to set just the all-wheel drive parameter to that one we pass into this car constructor with only the all-wheel drive parameter. So now we have three constructors, three different ways we could create a car object. So let's go back to main. So we have our original way defined up here, which is simply calling the constructor we defined between lines 8 and 14, which is going to pass in all the 5 instance variables for the parameter values. Now we could create another one. So let's call this one BMW2 equals new car. And in this case, we're not going to pass in any parameters. So we're simply going to create a car with all the default parameters, and let's print that one out as well. So on line 7, system.out.println, and we're just going to do bmw2.toString. And finally, let's create one called BMW3 on line 8, new car, and we're simply going to specify true here for the all-wheel drive. And once again, we're going to do a system.out.println bmw3.toString. Let's save it and rerun it, and let's see what happens. So we're just recompiling. And here it is. So we rerun it. So the first line is just like before. We have all 5 parameters, and all of those show up in our toString for instance variable parameters. Next, we have the one that gets called with on line 6, we're creating BMW2, a new object, and on line 7, we're outputting the values of the instance variables for that object. You could see here it's just set to the default values, so empty string for make, empty string for model, empty string for color, price is 0, all-wheel drive is false. On line 8, we're creating a new car with the third constructor we defined, only taking the all-wheel drive parameter. We set that to true. And you can see the only difference between BMW 2 and BMW 3 is that all-wheel drive is set to true in BMW 3 because we're explicitly passing that all-wheel drive parameter to true. You can notice that all the other values in BMW 3 are the same as in BMW 2, such as make, model, color, and price. This is because inside the car class, we are calling this on line 25. So it's essentially calling the default constructor, which is that car constructor that isn't taking in any parameters, setting the default instance variable values, and then modifying that all-wheel drive value to the one we pass in to that car constructor. So that's all for overloading constructors. In this video, we're going to talk about how to instantiate a class with and without constructor parameters and how to modify object fields. So a Java constructor can be parameterized. And if it's parameterized, that basically means that the constructor is going to take one to many arguments or parameters that get passed into it when a new object is instantiated. So to instantiate a new object, as we've seen before, we're going to use the new keyword, and then after we're going to call the class name, which also happens to be the same name as the constructor. And then within the brackets, we're going to pass in the different parameters. So we're going to have no parameters in some cases if we just want to call the default constructor, or we're going to have up to as many parameters as we want to define for the constructor. These parameters are going to set the initial state of our object that we're creating. So let's take a look here at some constructors. So the first one has a single argument. So we have my class that takes one argument or parameter int x, and that's going to be able to initialize any type of instance variable using that int x argument. Next, we have multiple arguments. So my class, it's the same constructor definition. So we're just overloading that myClass constructor. However, the difference is that we're now passing in two parameters. So we have int x and int y. And finally, the last one, once again, we're overloading again, and we have a myClass that takes three arguments, int x, double y, string z. So in order to invoke parameterized constructor, we do that when we're creating a new object. So we have the type of object or the class. So for example, car, then the object name, for example, BMW. And then we have equals new, and then we specify the class names again, which is also the constructor name. So new myClass in this case with no argument, and we would just have an open brace and a closed brace, and that would instantiate the constructor with just the default values without passing in any arguments. With multiple arguments, we have the same thing. However, now we're passing in the arguments we want. In this case, for myClass, it's two integers, 10 and 20 for the two arguments. Finally, for the mixed types, we once again call new myClass, and then we pass in 10, 100.0, so a double, and we pass in a string hello world. So how can we use the constructors? So we have a public class Java constructor, and we have 4 constructors defined. So the first one is just the default constructor that doesn't take in any arguments and prints out system.out.print nothing. The second one takes 2 arguments, an int x and an int y, and we're going to print out the value of x plus y. The third one's going to take an int x double y float z, and we're going to print out x plus y plus z. And finally, the last one's going to take an int and a string, and we're going to print out the int x and then the string y. We have our main method and instantiating a new object of type Java constructor. And in the first case, we're not passing in any arguments. In the second case, we're going to pass in 50 and 100 for the two integers when we're calling that second constructor. In the third case, we're going to pass in 10, 20, and 30. So that's going to be an integer, a double, and a float. And in the last one, we're going to pass in 100 for the integer and hello world for the string. And now if you take a look here, have the system.out.print. So in the first case, it'll print nothing. In the second case, it's going to print x plus y. So we're going to get 50 plus 100 because those are the arguments we're passing in to the constructor. In the third case, it's going to print at 10. And then since the second one's a double, it's going to print 20.0. And the third one's a float z, we're going to print 30.0 because we're passing in 10, 20, and 30 as the arguments into the constructor. And finally, for the fourth one, we're passing in 100 for the integer. So we're going to print 100. And then hello world for the string argument in the constructor, and we're going to print hello world. So that's it for using parameterized constructors. In this demo, we're going to take a deeper dive into constructors and ways to create constructors both with parameters and without parameters, as well as creating methods to modify instance variables and create copy constructors. So what you want to do here in my Ubuntu 18.04 environment with IntelliJ IDEA Community Edition up, you want to open up the asset for this demo. It's called Overloading is the project name. So I'll open up that Overloading project name, and it's a car project. You can notice just like in our previous projects, we had our source directory with two classes, car and main. So the car class defines a car, and the main class runs our program by instantiating a car object and printing out the instance variables to the command line. So you could notice here in our car class, the difference from before is that we actually don't have a constructor. So we could actually in Java create a class without a constructor, and it will compile and run. We only have getters and setters instance variables as well as a toString. So what's going to happen without the constructor is essentially all the strings are going to get set to null, any boolean is going to get set to false, and any ints are going to get set to 0. So you could see here in our main method on line 4 in setter main.java class file, we're creating a new BMW object or a new car object called BMW on line 4. And then we're calling system.out.println bmw.toString to print the attributes or the instance variables of that object. So let's go ahead and run that, and we'll see what happens. We could see that the make is null, model is null, color is null, price is 0, and all-wheel drive is false. So that's just calling the default constructor that's actually not even defined by us, but it exists within Java. So now let's go ahead and generate standard constructor. So we'll right click, go to generate constructor, and we'll select with control, we'll select all 5 of our instance variables, hit OK. We could also generate a constructor that takes no instance variables or that takes no parameters. So just public car. And inside here, we could initialize our instance variables to anything we like. So let's just copy these over. And the make, we'll just leave it as an empty string. The model will be an empty string as well. The color will be an empty string. The price will be 0, and the all-wheel drive will set to false. So now we have 2 constructors. We have one that takes parameters that's defined between lines 8 and 14, and one that doesn't, define between lines 16 and 22. Now what we have to do is we could call it 2 ways. We could either call it by the way we're calling line 4 without any parameters, or we could also call it the way we're going to do on line 6. So we're going to create a new BMW or a new car object called BMW2, and we're going to pass in all the parameters. So the make is going to be BMW, the model will be X3, color will be gray, price will be 30,000, and all-wheel drive will be set to true. And then we could also print this out on line 7. We'll call system.out.println BMW2.toString. So let's just run this and make sure everything works as expected. So we should see that we now have one that's getting defined with that default constructor with no parameters. So make, model, color are just going to be empty strings. Price will be 0. All-wheel drive is false. And then we have one that gets defined by the parameters that we pass in for each instance variable. So makes BMW, models X3, color is gray, price is 30,000, all-wheel drive is true. Okay, so let's create a method now inside car class that's going to be called increase price and int increment. So this method is simply going to increase, and of course it's going to be a public void. It's going to increase the price of our car object by the increment. So we could specify this dot price plus equals increment. Okay, and then we could call that from our main class. So when we create BMW2, let's call BMW2.increasePrice, and we could say, for example, 10,000. So it's going to increase our price by $10,000, and then if we rerun it, we should see that we now have a price of $40,000 for that BMW 2 car object. So now that we've talked about creating a method inside our car class, we've talked about different ways we could create constructors. Let's go ahead and create a copy constructor. So a copy constructor essentially takes one object as a parameter of the same type and copies it into another object of the same type. So we'll create a third constructor on line 24, so public car, and it's going to take a car object as a parameter. And what we're going to do is we're simply going to copy all our instance variables, and we're going to say this.make equals car.make, this.model equals car.model. So we're essentially just copying one object to another by copying all the instance variables. This.color equals car.color, this.price, car.price, and this.allwheel drive equals car.allwheel drive. So you could see we have all our instance variables are being copied from that car object we're passing in. Now let's go back to our main class. So inside here, let's create a new car object called BMW3 equals new car, and we'll call that copy constructor by passing in BMW2 inside it. And then we could do a system .out.println, and we should expect if we print out bmw3.toString that we actually get the same result as bmw2.toString, because what we're going to be doing is essentially just copying all the attributes, all the instance variable values into bmw3 from bmw2. So let's go ahead and run that. And we could see that the result is identical. So we have make BMW model, it's 3 color gray, price 40,000. All-wheel drive equals true for both of them. That BMW 2 car object into the new car object called BMW 3. So that's all for deep dive into constructors, and I hope you have enjoyed this course. So in this course, we've examined the components of a basic Java program such as classes, attributes, methods, and variables. We did this by exploring programming Java classes, programming access modifiers, class members and variables, Java overloading and working with it, and working with Java constructors. In our next course, we'll move on to explore data types and how to perform actions on them.
In Java, collecting, manipulating, and working with information means using variables. No problem. But what's important to understand is that depending on the kind of data you're working with, you need to use the proper data type. Now, data types can be classified into two groups. The first classification of a data type is what's called a primitive. A primitive data type strictly specifies the size and type of information that can be stored in the variable. It also has no methods that can be called against a variable. The second category of data types is the opposite of primitives, non-primitives. A non-primitive data type is usually referred to as a reference object because it references an object. Shocker, right? Well, with non-primitives, you have much more control over what information can be stored in the variable, and there's almost always methods that you can call against a variable too. So let's dig into these, shall we? First, let's talk about primitive data types. I already mentioned that there's strict specifications of type and size of information. So what kinds of primitives are there, and what are their sizes? Well, first we have the Boolean. Now this is the most basic data type that you can have. It's true or it's false, 1 or 0. That's it. Then there's the byte. A byte is a whole number, but it can only be between -128 to 127. And then comes the integer. This is also a whole number, but its range is 32 bits, and that means that it can be anywhere between about -2 billion to 2 billion. Then there's something between an int and a byte, and it's called a short. Now, short can hold whole numbers between about -32,000 to 32,000. And actually, there's one more type of whole number primitive data type, and that's a long. A long can store a value between -9 quintillion and +9 quintillion. But primitives don't have to be based on just whole numbers. There's also data types like the float. And floats can store values of up to 7 decimal digits. Meanwhile, doubles can also store decimal values, but up to 15 decimal digits. And the final primitive type is the char. Chars can store any single character, letter, or ASCII value. Now, when you create a primitive variable in Java, it always defaults to something. It can't be nothing. In Java, nothing is also referred to as null, and since primitive data types can't be null, they need to have a default value. And there's a real easy shortcut for remembering what the default value of a primitive data type is. It's always 0. Of course, a Boolean value can't be 0, it has to be true or false. But in Java, 0 is false and 1 is true. And we'll talk about that later in the course. But suffice it to say that if 0 is false, then the default for a Boolean value is false. Then, for all the numbers, the default value is 0 too. So if you create an empty variable of type byte, int, short, long, float, or double, the default value will be 0. As for the char data type, the default character is the /u0000. Now, that's not the letter 0, but rather the 0th character. In a way, it's a null character, but it's not actually null. How can I put this? Effectively, the default value for a char data type is the character that means null, but it isn't actually null. Weird, right? But there it is. It's the 0th character that represents null without actually being null. Okay, so we know what primitive data types are, so what about non-primitive data types? Well, as I said earlier, non-primitive data types are objects that can be used as references. Generally, they have methods that you can call against them too. And you can't do that with primitive data types. Non-primitive data types are extremely common in Java. For example, probably the most common type of non-primitive is string. You can create an instance of a string, and you can even call some methods against that string to do some additional actions, and we'll talk about that later in this course. Another common type of non-primitive is an array. An array is a list of things that share the same data type. So you can have an array or a list of integers, bytes, booleans, and so on, and you can even have an array of non-primitives. Heck, you can even have an array of arrays. Now, the next most common type of non-primitive is a class. Class is an object. It has properties and methods. So imagine you wanted to define a car. You would create a class called car and then provide properties like make, model, and year, number of wheels, and mileage, and so on. You could even create methods like start and stop. And then there's interfaces. Interfaces are interesting because they aren't actually a thing. They're a definition of a thing. That's getting a little bit advanced, but it's worth understanding that it's another type of key non-primitive. So what are the differences between primitives and non-primitives? How can you tell the difference or even decide which one to use in which situation? Well, first let's look at a primitive. As I said earlier, primitives always have to have a value. They can't be null. They're also predefined by Java, so you can't create your own primitive. In fact, they're reserved keywords in the programming language. The size is also defined by the data type. So an int can only have a value between about -2 billion and +2 billion. Now, the keyword that you would use to use a primitive always starts with a lowercase letter. And finally, primitives don't have any methods. Okay, so now let's contrast that with non-primitive data types. Well, non-primitive data types can absolutely be null. In fact, that's their default value. And non-primitives are also created by programmers, and that's particularly true for classes and interfaces. Now, it's a bit tricky to wrap your head around, but non-primitives all have the same size, for want of a better word. So while a primitive size can vary depending on which one you use, in Java, all non-primitives are the same size. Now, the other hint is that non-primitives always start with an uppercase letter. And the last difference between primitives and non-primitives is that you can call methods against non-primitives. In this demo, we're going to look at the different data types in Java. To do that, we're going to create a Java project, set up a static class to run some code, and then we'll run through some primitive data types as well as some non-primitive data types and how Java renders them. Alright, so the first thing we want to do is create a Java project. Now to do that, we need a Java IDE. For my purposes, I'm going to use the open source Eclipse IDE. So I'm going to go ahead and open Eclipse now. Great. Now let's go ahead and create a Java project. In Eclipse, that's as simple as opening the File menu and clicking on New Java Project. Now, when you create a project, you need to give it a name. So for the sake of this demo, I'm going to call my project Demo16. Now, all the data types that we're going to explore in this demo are fundamental aspects of Java, and so they've been around from the very beginning. Now, all that means is that there's nothing really special beyond setting the name of the project that we have to do to get this going. So let's just leave all the defaults as they are and click Finish. Good. Now Eclipse is asking us for a module name. Now, this isn't super important for what we're trying to do in this course, so let's just leave this as the default too and click Create. Perfect. Now our project is created and we're just about ready to get started with data types. But before we can actually explore code, well, we need a file that we can actually code in. So let's go ahead and do that. First, let's close the module tab that opened up on our screen. Alright, in order to be able to play with any sort of code, you first need to have an entry point into the project. So let's do that by creating a class to play with data types. From the File menu, let's select New Class. Perfect. Now in the pop-up, we're being asked for information about our class. Now, the source folder and package are pointed to the root of our project by default, and that's fine for our purposes. Let's give our class a name. In this case, let's call it data types with a capital D and a capital T. And we'll leave all the modifiers, the superclasses, and the interfaces as the defaults, but let's make sure that we check the public static void main method stub checkbox. And let's leave all the other ones unchecked. Good, now let's click Finish. Excellent, we have our class and we're finally ready to get started. Now in Java there are two categories of data types. The first type is primitive and the second type is non-primitive. Java actually renders these differently so you know what you're dealing with. So let's see that in action. Now inside the main method, let's remove the comment and replace it with char. Perfect. Now notice the word char is bolded. In fact, it's bolded just the same as the other words in package, public, class, static, and void are all bolded words too. And that's because these are all reserved keywords in Java. Reserved keywords are language-specific key commands, objects, or operators. Primitive data types are considered reserved keywords in Java. And so that's why we see the word char bolded like this. Now let's do one more thing with our char keyword. Right at the end of the word, let's add a period. Now, what a period does is tell Java that we want to access something about that object. This includes properties or methods. In most IDEs, like Eclipse, you can type the period, or dot as it's often called, and it will automatically pop up a drop-down of the available properties and methods. So if we type the dot at the end of the char keyword, we'll see what properties or methods are available. And look at that. There's nothing. The pop-up is empty, well, except for the actual title, of course. Now, this isn't a surprise, though. One aspect of primitive data types is that it doesn't have any properties or methods. So let's type out some other primitive data types. On the next line, let's type Boolean. Good. Now notice that it's also bolded just like the char. And if we type the dot, we once again see that there's nothing in the pop-up. So what are the other primitive data types? Do they all render the same way? Well, let's find out. On the next line, let's type byte. Great, it's bold too. And now let's go to the next line and type short. Bold again. And now let's add each of the following: int, long, float, and finally double. Cool. Those are all the primitive data types from Java, and they're all bolded because they're all keywords. Nice job. But what about non-primitive data types? Well, let's try a couple of those and see what we get. Let's drop a couple of lines down and type the following code. String with a capital S. Nice. Now notice a couple of things right away. First, the word string is not bolded. So even though it's a fundamental aspect of development in Java, it hasn't been elevated to the role of keyword. The other thing that we can see is that the S in the string is capitalized, whereas all the primitive keywords are all lowercase. Now let's do the dot thing again, but this time with the string word. So right at the end of the word, let's type the dot. Wow! Now notice that this time there's lots of functions that popped up here. In here you can see that we can call copy method, a join method, and lots more. And that's one of the biggest differences between primitives and non-primitives. With non-primitives, you can actually generally access lots of methods and properties on the object. Of course, what you're looking at here is what's called static methods and properties, and we'll get to more about that later in this course. So what are some other common non-primitives? Well, one type is a class. Technically, the string is a class, but there are others like it. For example, let's drop down a line and type StringBuilder with a capital S and a capital B. Nice. StringBuilder is another way to manage strings. In fact, we'll talk about that later in the course too. Regardless, you can see that a class is rendered the same way as a string. And finally, let's talk about one more non-primitive data type. It's a bit of a special one. It's the array. There are a few different ways to create an array, but let's focus on the most common one. On the next line, let's type string open close square bracket. That's it. An array is shown as whatever data type we want, but with the square brackets. So what if we wanted to create an array of primitives? Well, let's try it. Let's go down another line and type int open close square bracket. Great. Now notice that this time the code is bolded again, but wait, we said that non-primitives aren't reserved keywords, so what gives? Well, that's why I say that arrays are a bit of a special snowflake. In this case, we've created an array of integers. Put another way, we've created a list of primitives. So we can tell that this is an array because of the square brackets, and we know that arrays are non-primitives. So this is just something that you need to get used to when you're programming in Java. Anyways, that's data types in Java. You can see the difference between primitives and non-primitives. Great job! To make use of Java data types, you need to define a variable. A variable is defined by its data type and its value. In reality, a variable is the most basic storage unit in a memory location used by Java. You define a variable, and Java will allocate a portion of memory to house the value assigned to that variable. Now, how much memory is allocated isn't based on the value, but rather on the data type. So earlier in the course, when I said that non-primitives were all the same size, this is what I was referring to. Now, another characteristic of a variable is that its value can be changed during execution. So if you started off by saying an integer value was 0, you could absolutely be allowed to change its value to something else. But before you can change a variable's value or manipulate it in any way, you naturally have to declare it first. So to use a variable in Java, you must declare it. The good news is that the syntax to declare a variable is always the same. It doesn't matter what data type you're using, primitive or non-primitive, and it doesn't matter what actual type you're using, Boolean, byte, int, double, char, string, class, or interface. The syntax is always the same. It boils down to 4 important details. First, you declare the data type. In this example, we're using an int, and that means that the variable we're going to create is an integer type. Then you type a space, and next you give your variable a name, any name you want. Well, I mean, there are some rules about what you can and can't name your variable, and we'll get to that in a second, but for the most part, it's pretty open. And lastly, you type a semicolon. But there is one more thing that you can do when you're defining a variable. You can actually define its initial value. Now, remember earlier in the course that I said all data types have a default value. Well, in the previous little code snippet, we created an integer variable called myInt. Now, the rules in Java say that doing that means that the initial value of myInt is going to be 0. But what if I want to start as a different value? Well, when you declare a variable, you can do that. Take a look at this example. All we did here was take our original variable declaration of int myInt and add equals 10 after the variable name and before the semicolon. So the whole thing reads quite nicely. It's saying that we've created an integer variable called myInt and set its initial value to 10. So as I said a bit earlier, you can name your variables just about anything you want. But there are some rules and conventions in Java about what you can and can't do when it comes to naming. For example, the first character of your variable must be a letter, a $, or an underscore. But even though you can do it, Java recommends never using the $. So just keep it to letters or underscores. Now you can use numbers in your variable name too, but Java doesn't allow numbers to be the first character. And it's also important to note that variable names are case sensitive. So you can actually create 2 variables with the same name as long as they aren't the same from a case usage perspective. Now, variables are all one word and alphanumeric, so that means spaces and special characters can't be used in their names. And finally, you can't name a variable the same as a reserved keyword. So if you wanted to name your variable int, you wouldn't be allowed to. Now, to paraphrase Dr. Ian Malcolm, yeah, but you developers were so preoccupied with whether or not you could do a thing, you didn't stop to think if you should. Put another way, while it's true that you can name some variables just about anything you want, it doesn't mean you should. In Java, there is a certain set of best practices that you should follow for naming your variables. And these aren't hard rules, meaning Java won't fail to compile your project, but you should still follow the guidance. First, try to always begin your variable names with a letter. Now that might seem obvious since we're so limited on how we can begin a variable name. The main point is to avoid using the $, and underscore. It's also very important from a perspective of clean code that your variable names are composed of full words and meaningful names. Calling your variables foo, bar, or baz doesn't help the next developer to understand what that variable is for, but calling a variable number of people is very obvious. It's also very important to avoid creating variable names that are only a single character. Just like foo, bar, and baz are terrible and nondescriptive names, so are variable names like a, b, or c. The reason I bring this specific example up is because there is a situation where there is an exception. The only exception to the single character name rule is for situations where the variable is truly a well-understood, transient, throwaway variable like the I variable used in iterators. Another best practice for variable naming is to use lower camel case. Now that means that every single word in the variable name should have its first letter uppercase, but the very first word in the variable name should be all lowercase. And finally, while variable names can be any length, be prudent. You don't want to write a novel to describe the variable. It's okay to be long, just be concise. Now, in the earlier syntax example, I showed you how to create an integer variable. But of course, there's all kinds of other primitive types too. So let's take a look at how we would create variables of different data types. First, we have a Boolean. Now, this is pretty simple. For Booleans, we use the keyword Boolean. And then we give any name we want, and then use the keyword true or false, all lowercase, to initialize the value. Then we have the byte. For bytes, we can use the byte keyword and then create it just like we did with the integer earlier on. Now take a look at the short variable. Notice that we've set the value to about negative 32,000. Now it's important to see that we can set the value to any value we want, positive or negative, as long as it's within the range that the data type supports. Then we see the long variable. Now notice at the end of the value that there's a capital L. That's not technically required here because we're declaring the value, but without the L, Java would technically be widening an integer into a long. And we'll talk more about narrowing and widening later in the course. And you'll notice the same kind of syntax being used for the float and double. And finally, there's the char variable. Now notice that the value is in single quotes. Characters are always represented in single quotes. Okay, so that's how we create primitive data types, but what about non-primitive data types? Take these code snippets, for example. In the top snippet, we're creating an instance of a string. And notice that we declare it in exactly the same way as a regular primitive variable. We define the variable type, in this case string, and then the variable name. And then we declare the initial value after an equal sign. So in this case, we're setting the string value to hello world. Now in the bottom snippet, we're creating an array. Now arrays are interesting because they aren't an object per se. Rather, they're a collection of things. So we're actually creating two arrays here. The first array is an array of strings and the second array is an array of integers. We know the variable is an array because the data type is followed by an open and closed square bracket. The other hint is that the values that we're setting the array to are comma delimited and contained inside the squiggly brackets. Now what's important to note here is that whatever the data type of the array is, the contents of the array must be that data type. So in the first array, the values are all strings, and in the second array, the values are all integers. Now earlier I talked about there being different types and levels of variables in Java. In actuality, there are three types of variables. A local variable is a variable that's defined inside a code block and therefore usable inside that code block. And that's important. If I create a variable inside a method, I can't access it from outside that method. It is local to that code block only. Another type of variable is an instance variable. Instance variables are variables that can be declared on a class definition. So for example, imagine that there was a class that you used to define a car. Now there could be an instance variable defined on that class named make and another called model. From anywhere in the code where you have access to an instance of the car class, you would be able to access those instance variables. But you must have an actual instance of the car class to access those variables. Instance variables are also sometimes called properties. And the final type of variable is the static variable. Static variables are similar to instance variables, except you don't need an instance of the class to access the variable value. Now let's pull all that information together and see how we would actually go about creating a local, non-primitive variable and then use an instance and static variable. In this code snippet, we have a main class with a static main method. So let's take a look at what's happening inside this method. Now right at the top, we're outputting a value to the console using a print line command. The value that we're outputting is from the variable named static variable on the myClass object. But what's important to see here is that we haven't actually created an instance of the myClass object yet, and in fact we're calling for the variable value against the myClass definition. So if we assume that the value of the static variable is 20, then that's what we'll see in the console. Now below that, we actually do create an instance of the myClass object. And this is how you would create a variable for a non-primitive type. Almost always, you'll have to use the new keyword. And right after that, we create a primitive variable named local variable. And that's what it is. It's a local variable. Technically, so is the myClass variable that we created right above it. So now we have two local variables. One is primitive, the one named local variable, and one is non-primitive, the one named myClass. Anyway, the value of local variable has been set to 10. Now in the next line, we set the value of the myClassInstance variable named instance variable to equal the value of local variable. What's important to understand here is that the instance variable is not accessible until we create an instance of the class. So while we can access the static variable without an instance, we can't do that for the instance variable. And finally, the last line of code outputs the value of the variable named instance variable to the console. So since we set it to the value of local variable and local variable was set to 10, we would see that the value of 10 is output to the console. In this demo, we're going to explore declaring variables in Java. To do that, we're going to use our previous demo to create variables for each of the different data types that we typed out. We'll then initialize each variable with a value. And we'll know we're doing a good job when the code is able to compile without any errors. Alright, so as I said, we're going to piggyback off our previous demo which we built in Eclipse. So let's head over to the Eclipse IDE now. Alright, so I already have our project open from the previous demo, but if you don't, go ahead and open it now. Alright, so in our last demo, we typed out a whole bunch of data types. Some were primitives and some were non-primitives. But there's a problem with what we did. There are no variables yet. And so in this demo, we're going to convert each of those data types into real variables. Now, as we go along, we'll also initialize each variable with a value. Alright, so the first thing we need to do is access our data types class from the previous demo, and we can do that by double-clicking on the datatypes.java file in the Package Explorer panel on the left-hand side of the screen. And I've already got mine open. Good. So as you can see on the screen, we've typed out a bunch of different data types, each on a new line. Now notice that there's lots of red underlining. These are complaints from Java. The Eclipse IDE is looking at our code and telling us that it's all wrong. Well, that's true. It's because we typed out all of our data types, but we didn't actually define them as variables. In fact, that means that this code can't be compiled. Actually, let's prove that. Let's start by saving the file with a Control-S and then running it with a Control-F11. Out! Now in the console log at the bottom of the screen, we're seeing a nice big red exception. Now this is telling us that there's a compilation problem. It tries to figure out what the problem is, but it's actually saying there's quite a few. So ultimately, trust me when I say the problem is that we haven't defined proper variables and the code can't compile. So let's fix that. Let's go ahead and create some variables. Let's start at the top. The first line of code that we wrote was char dot. Well, that's not proper code, and you can see that Eclipse has highlighted it telling us that. So let's convert it to a proper variable. Now remember that the syntax for a variable is the data type, a space, the variable name, and then a semicolon. So let's replace the char line of code with this, char mychar semicolon. Nice! Now notice how Eclipse is no longer underlining the code. That's great. That means that it now understands that line of code. So we've now created a variable called mychar that is a char data type. And notice my naming. My variable name starts with a lowercase letter and each new word is capitalized. Okay, so let's keep going. Let's fix the rest of the primitive types. Let's change the Boolean line to Boolean myBoolean. And don't forget that semicolon. And then let's fix the byte line to byte myByte. And now let's fix the short line to short myShort. And next let's fix the int line to int myInt. And the long line to long myLong. And the float to float myFloat. And we'll name the double myDouble. Perfect! So now we can see that there are no more complaints on our primitive variables. Now there's still some complaints about our non-primitives down below, but maybe those don't matter anymore. So let's save the file again and try running it again. And remember that's Control-S and Control-F11. Dang, still broken. Well, I guess that means that we have to fix our non-primitives too. So let's do that. Let's replace our string line with string myString. And we'll do the same with StringBuilder and call the variable myBuilder. Good. Now let's give our string array the name of myStringArray with a capital S and a capital A. And notice that that means that the first letter of each word in my variable name is capitalized except for the first letter. And finally, let's name our integer array myIntArray. Perfect! So now we can see that there are no more complaints in the file at all. Well, at least no more red ones anyways. So let's see if this compiles now. Let's save it and run it. Nice! Now our console at the bottom of the screen is empty. There is no code that outputs information to the console, so a blank output is exactly what we expect. So that's it. We've created a bunch of variables. They're all different data types and they all have different names. And that's actually important. You can't name two variables the same in the same scope. Okay, so what if we wanted to set the value for each of these variables? So how do we do that? Well, let's go back up to our char line and I'll show you. Now before the semicolon, let's add this text. Space equals space single quote s single quote. Good. Now what we've done here is we've initialized the mychar variable to the letter s. Pretty easy, huh? Well, let's do that for our other variables. Let's set our myBoolean variable to true by typing equals true before the semicolon. Excellent. Now we'll set the byte to 1, and the short to 2, and the int to 3, and the long to 4, and the myFloat to 5.6, and the mydouble to 7.8. Excellent. Now notice that Java is a bit confused by the value that we gave our float variable. Well, that's because in Java, any number that has a decimal place is automatically considered to be a double. And so according to Java, we're trying to put a double value in a float. So we can fix that by telling Java that the number really is a float. And we can do that by typing the letter F at the end of the number 5.6. Perfect. The error went away. But floats aren't the only data types that we can do this for. In fact, we should technically be doing this for other numbers too. So let's do it. At the end of the long number, let's type the capital letter L. Good. Now that tells Java that the number that we typed truly is a long. And finally, even though it's the default, let's type the letter D at the end of the double number to tell Java that we're dealing with a double value. Excellent. So all of our primitives are configured and have been initialized with a real value. So what about our non-primitives? Well, let's do it. Let's drop down to our string and initialize the variable by adding equals, double quote, hello, space, world, double quote. Nice. Now for strings, you can see that we can initialize them in pretty close to the same way as primitives. But not all non-primitives are like that. To prove that, let's look at our StringBuilder. Let's initialize it too. Now before its semicolon, let's add the code space equals space new space StringBuilder with a capital S and a capital B, and then open and close round brackets. Perfect. Now you can see that we used the new keyword, and this created a new instance of the StringBuilder class for us to use. And finally, we get to our special snowflakes, the arrays. Now let's start with the string array. Now before the semicolon, let's add the code space equals space open squiggly bracket, double quote, hello, double quote, comma, space, double quote, world, double quote, end squiggly bracket. Perfect. Now what we've done here is created an array of strings. The array contains two strings. The first one says hello and the second says world. Now notice how the syntax to initialize the array includes a comma-delimited list of items surrounded by squiggly brackets. So let's do the same for our integer array. Let's add the code equals open squiggly bracket 1, 2, 3, close squiggly bracket. Now the integers are comma-delimited and all surrounded by squiggly brackets. Okay, so let's do one more thing. Let's quickly touch on the final keyword in Java. Let's pretend you wanted to create a variable and set its value just like we've done here. But then you want that variable to never be allowed to change ever again. Well, in Java you can do that by using the final keyword. For example, let's go up to our int variable. Now right below that variable, let's add another line. Let's type myInt++ semicolon. Good. Now this isn't really hard code. All it'll do is add 1 to the integer variable that we have. So what that means is that after this code runs, the value of my int variable would be 4 because we added 1 to the 3 value that was initialized. But let's say we decided we didn't want the variable to ever be allowed to change. Well, let's do that. Now before the keyword int, let's add the code final. Now notice what happened to our myInt++. Notice that Java doesn't like it anymore. And if we tried to run this file, we get an exception because we're not allowed to change the variable. Pretty cool, right? And so there you have it. We've converted our data types to real, actual variables, and we've even initialized each and every one of them with a value. Great job. In Java, there's a specific kind of thing that you can do with variables, and it's called typecasting. Sure, that might sound like your variable is stuck doing a certain kind of acting gig for the rest of its life until it sinks into a terrible depression, but that's not what it is at all. In Java, typecasting means that you take a variable and effectively convert it from one data type to another. So you can take an integer and convert it to a double, and vice versa. But one thing that you have to watch out for is that sometimes certain data types aren't compatible, and so the casting isn't possible. Now, when it comes to typecasting, there are two ways that you can do that, or actually put another way, there are two directions that you can do that. The first direction you can go with casting is what's called widening. Generally, widening can be done automatically by Java for compatible types. Widening is about taking a data type and casting it to another, bigger data type. So for example, you can take a short data type, which remember has a maximum size of about 32,000, and easily cast it to a long data type, which has a maximum size of about 9 quintillion. The other direction you can go with casting is what's called narrowing. Narrowing can't be done automatically because there's no real backwards compatible type. Narrowing is about taking a data type and casting it to another, smaller data type, or at least a different data type. So for example, you may want to try to take a long data type and cast it to a short data type. But you can see the problem. If you have a huge number in your long variable, it may not fit in the short variable. So narrowing can be problematic. So what are the differences between widening and narrowing? How can you tell the difference or even decide which one to use in which situation? Well, let's take a look at widening. As I said earlier, widening is effectively automatic. Without any real work on your part, Java can easily widen a data type. And in fact, that's the key. When it comes to widening, it's the compiler that does the job. You tell Java you want the data type to be widened, and it can handle the rest for you. Now, when you ask for a variable to be widened, you don't have to give Java a casting operator or any other special code. You can just tell Java that you want the variable to be a certain type, and it'll take care of it. But widening isn't magic. There are still constraints. The data types that you're casting have to be compatible. And finally, and most importantly, the target type in the cast operation can't be smaller than the source. In other words, you can't cast an integer to a byte. The target type has to be bigger. So you could cast a byte to an integer. Okay, so let's contrast that with narrowing. Well, with narrowing, the cast is manual. Java won't be able to figure out what to cast to without help. What that means is that the developer is the one doing the casting. And that means that the developer needs to actually provide a casting operator, and this will tell Java what and how to cast to and from. Of course, because narrowing is a manual approach, it means that there's no real limit on what you can and can't cast to. Of course, if you try to cast a string into an integer, it may fail for different reasons, but technically from a code compilation perspective, it would be fine. The failure would happen at runtime, but should be perfectly fine at compile time. And the last difference between widening and narrowing is that with narrowing, you can cast a smaller data type. So if you wanted to cast an integer to a byte, you could do that as long as the value would fit in the byte, of course. So when we talk about widening a variable, we're really talking about converting it to a larger data type. So imagine you have a thimble of water and you want to put that water into a shot glass. You could absolutely do that. You would be widening the container. Then, over time, you added some more water into that shot glass, and you want to put it into a pint glass. Well, you could do that too. And again, you would be widening the container. Well, in Java, the same rule applies. As long as the data type that you want to cast is smaller than the data type that you want to cast to, then you can quickly and easily and automatically cast to the new data type, and Java will do it for you. But the order is very strict. In fact, the order for widening is byte, followed by short, then char, then int, then long, then float, and then double. Now, you can skip steps, like you can cast a byte to an int or even all the way to a double, but you must go in that direction, smallest to biggest. You can't cast a double to a float automatically because a double is bigger than a float, and so that would actually be narrowing. So let's go over a quick example of widening. In this code snippet, we create an integer variable called myInt, and we set its value to 50. Then, in the next line of code, we create a new float variable called myFloat, and we set its value to the myInt variable. Now what that's doing is it's telling Java to create a new float variable and initialize it with the integer value. Now Java has no problem with that. It creates the float and sets the value automatically. In the next couple of lines, we output the values to the console. And what we see is that the integer value is 50, and so is the float value. In fact, because it's a float value, the output now includes a decimal place. The cast is successful and it does exactly what we expect. So that's how widening works. In this demo, we're going to go over the concept of widening. We'll create a variable and we'll cast it to bigger and bigger data types, and we'll output each result to the console so we can see our widening working as we go. Alright, so to do this demo, we're going to piggyback a bit off of our previous demos which we built in Eclipse. So let's head over to the Eclipse IDE now. Alright, so I already have our project open from the previous demo, but if you don't, you go ahead and do that now. Now what we're going to do in this demo is we're going to create a simple variable and then cast it to a bigger and bigger data type. And this is called widening. So to do that, we're going to create a new class so that we can start from a fresh canvas. So the first thing we're going to do is create a new class. Now to do that in Eclipse, let's go to the File menu and select New Class. Perfect. Now in the pop-up, Eclipse is asking us for information about our class. The source folder and the package are pointed to the root of our project by default, and that's fine for our purposes here. So let's give our class a name. In this case, let's call it Widening with a capital W. Now I'll leave the modifiers, superclass, and interfaces as the defaults, but let's make sure that we check the public static void main method stub checkbox and leave the others unchecked. Good. Now let's click Finish. Excellent, we have our class, and now we can finally get started. Okay, so remember that the concept of widening in Java is to cast a variable from one data type to another, but always in an upwards direction. Or more appropriately, it's about casting to bigger data types. So for example, imagine you had a glass of water, and if you wanted to pour the whole glass into a swimming pool, you could absolutely do that. The glass and the pool are like data types, and the water is the value. In Java, we call that widening. Of course, on the other hand, if we had a glass of water and wanted to pour it into a thimble, that wouldn't work so well. In Java, that's called narrowing. Of course, for the purposes of this demo, we're concerned with widening, so let's focus on that. Now, the point is that widening is about converting variables to larger data types. So let's write out an example. Let's replace the comment with this code. Byte, my byte, equals 1 semicolon. Perfect. So what we've done here is we've created a variable called myByte, which uses the data type byte, and has been initialized to a value of 1. Now in Java, a byte is just about the smallest kind of data type that you can have. So let's start by proving that we have the right value. So let's drop a couple of lines down and type the following code. System.out.println, open bracket, myByte, close bracket, semicolon. Good. Now what we're doing here is we're creating a byte variable, and we're setting its value to 1, and then we're outputting that value to the console. So let's prove that. Let's save the file with a Ctrl S, and run the project with a Ctrl F11. Nice! So we now see a value of 1 being displayed in the console at the bottom of the screen. Congratulations, we created a variable and showed its value on the console. Now let's widen the variable. Let's say we want to create a short data type from my byte variable. Well, that would mean casting my byte to a short. And since a short is bigger than a byte, I can totally do that, so let's do it. On the line below our byte, let's type this code. Short, my short, equals my byte, semicolon. Now on the line below our print line command, let's type this code. System.out.println, my short, close bracket, semicolon. Excellent. So what we've done here is we've created a new variable called myShort that is using the short data type, and we've initialized its value from our byte. Then we added another print line command to output that value to the console. So let's save this and run it. Cool. So now we see 2 1s in the console output at the bottom of the screen. That shows that our cast worked. So let's keep going. Let's repeat the whole process, but for an integer. So below our short, let's add the code int myInt equals myShort. And then we'll add system.out.println myInt. Excellent. Now we'll save and run that. All right, now we have 3 ones. Excellent. But wait, there's more. Let's keep this going. Let's try this with a long. Below our integer, we'll add long, my long, equals my int. And as a last console output, we'll type system.out.println my long. We'll save it and we'll run it. Excellent, 4 ones. Okay, so that's the whole numbers, but what about our decimal numbers? Well, let's give that a whirl. So below our long, let's add this code. Float, my float, equals my long. Good, and we'll add our print line command, system.out.println my float, and we'll save and run that. Ooh, something different. Now remember that a float is a value that has a decimal number. So when we cast a whole number into a float, it worked, but we don't have an actual decimal number, so we get 1.0. Nice. All right, so let's do one more cast, and you probably guessed which one. Below our float, let's add the code double, my double, equals my float, semicolon. And we'll add one last console output, system.out.println my double, and we'll run that. Excellent, another 1.0. This worked seamlessly. But let's prove it a little bit more. Let's change our original byte value from 1 to 42. So if our casting is working properly, then every single value that we output to the console should now be changed to 42. So let's save the file and run the project again to see. Hey, we got 42! Great! Okay, so one last thing. Now remember that a widening is about casting to a larger data type. If you had a byte and you wanted to cast to a double, you can do that directly. You don't have to cast to each type in between like we did here. To prove that, let's change the myDouble variable to equal the myByte variable instead of the myFloat variable. myByte. Save and run. There it is. We still got the number 42 as our output. So that's widening in Java. Great job. In Java, there's automatic typecasting and then there's manual typecasting. With automatic typecasting, you can let Java do the work of widening your variables to larger data types. With manual typecasting, you're telling Java how to convert data from one type to another. Now, the process of manually converting a variable from one type to another is generally known as narrowing. Manual casting, as you can guess from the name, is an activity that always has to be performed by the programmer. There is no automation. Java may not know how to convert from one type to another, so you'll have to do the work of telling it what you want to do. And the way to do that is through a casting operator, and I'll show you more about that in a second. Now, the reason narrowing is a manual process is because Java can't automatically figure out how to convert certain data types. For example, with narrowing, target types can actually be smaller than the source type. You can't expect Java to automatically convert 1.23 to an integer because it's not a whole number. So you have to tell it what to do. So when we talk about narrowing variables, we're really talking about converting it from one data type to another. It's generally called narrowing because you're going from a larger data type to a smaller one. Now remember that with widening, Java could automatically convert a variable to another data type as long as that data type was larger than the one that you're coming from. So you can go from byte to short to int to long and so on. Well, with narrowing, you're asking Java to go in the opposite direction. But that's not without its dangers. So let's imagine that you have a pint glass of water and you want to put that water into a shot glass. Well, if the amount of water that you have in the pint glass is small, you could absolutely do that with no consequences, and you would be narrowing the container. Of course, if the amount of water that you have in the pint glass is more than the shot glass can handle, you'll have a big mess on your hands. Well, in Java the same rule applies. As long as the value that you have fits in the target data type, you'll be okay. But if you overrun the size of the target data type, you'll run into problems. More importantly, you'll run into situations where the data doesn't seem to match what you're expecting. Now, the good news is that the syntax for narrowing is pretty straightforward. All you have to do is define a variable of the data type you want, and then when you go to make it equal to some value, you prefix the source variable with the target data type in round brackets. So let's take a look at the syntax on the screen for example. In this snippet, we have a variable called source variable, and its data type is source data type. Great. Then on the next line, we create a new variable called target variable, and its data type is target data type. Then what we're doing is we're casting our source variable to the target data type class by using the target data type in round brackets. So what this code is doing is it's actually creating a new variable that is equal to a converted version of the source data type class variable. Now again, it's very important to remember that just because we're using the syntax, it doesn't mean that narrowing and casting of this type will always work. It's kind of like this. All dogs are animals, but not all animals are dogs. So if you try to narrow something that simply isn't compatible, the casting operation will fail on you, and that'll only happen at runtime. Okay, so let's go over an actual example of what narrowing would look like. In this code snippet, we created a double variable named myDouble, and then we set its value to 25.65. So far, so good. Now in the next line, we want to cast or narrow that value. And what we're doing is we're creating an integer variable called myInt. Then you see that we're setting its value to the myDouble variable, but we're using the manual casting syntax to convert it to an integer. Then in the next two lines, the values of myDouble and myInt are output to the console. And the result would be that the double value would still be 25.65, and the integer value would be 25. A successful narrowing. Now it's important to understand that even though a double is a decimal number, it doesn't mean it's fundamentally incompatible with an integer, so we can do this. But there are side effects. Java tries to be helpful when converting between known primitive types. In fact, let's pretend I set the myDouble variable value to be triple the maximum size of an integer. Well, instead of failing, Java will actually just overrun the integer size 3 times, and you'll get some number that equates to that overrun. And this is critical to understand. It means that Java is doing some magic for you, or at least it's doing something that you might not expect. Primarily, it means that the value that you get in the integer is technically not the value that was in the double. Some developers would say that they'd rather have Java throw an exception here rather than succeed with the wrong number. So just be careful when it comes to narrowing. In this demo, we're going to go over the concept of narrowing. We'll create a variable and we'll cast it to smaller and smaller data types. We'll output each result to the console so that we can see our narrowing working as we go. Alright, so to do this demo, we're going to piggyback a bit off of our previous demos which we built in Eclipse. So let's head over to the Eclipse IDE now. Alright, so I already have our project open from the previous demo, but if you don't, go ahead and do that now. Now, what we're going to do in this demo is we're going to create a simple variable and then cast it to smaller and smaller data types. And this is called narrowing. To do that, we're going to create a new class so that we can start from a fresh canvas. So the first thing we're going to do is create a new class. To do that in Eclipse, let's click on the File menu and select New Class. Now in the pop-up, Eclipse is asking us for information about our class. The source folder and package are pointed to the root of our project by default, and that's fine for our purposes. So let's give our class a name. In this case, let's call it Narrowing with a capital N. And we'll leave the modifiers, the superclass, and the interfaces as the defaults, but let's make sure that we check the public static void main method stub checkbox and leave the others unchecked. Good, now let's click Finish. Excellent, we have our class and we're ready to go. So now remember that the concept of narrowing in Java is to cast a variable from one data type to another. It doesn't actually matter what data types you convert from and to, but there is always a risk of incompatibility. So the data types still have to be compatible to perform a narrowing cast. So for example, imagine you had a glass of water. If you wanted to pour the whole glass into a thimble, you could do that, but you'd get a bit of a mess. But both the glass and the thimble hold water, so they are compatible types. In Java, we call that narrowing. Of course, on the other hand, if we had a bowl of spaghetti and we wanted to convert that into the color purple, we would get all confused. And the same is true for Java. One of the biggest differences between widening and narrowing is that widening can happen automatically in Java, while narrowing requires us to tell Java what to do. So let's write out an example. Let's replace the comment with this code. Double my double equals double dot max value all uppercase. And don't forget that semicolon. Perfect. So what we've done here is we've created a variable called myDouble, which uses the data type double and has been initialized to the maximum possible value of a double. Now in Java, a double is the largest numeric data type that you can have. So let's start by proving that we have the right value. Let's drop a couple of lines down and type the following code. System.out.println open bracket myDouble close bracket semicolon. Now what we're doing here is we're creating a double value, setting it to the maximum value of a double, and then outputting that value to the console. So let's prove it. Let's save the file with a Control S, and let's run the project with a Control F11. Nice! So we now see a monster value being displayed in the console at the bottom of the screen. Congratulations, we created a variable and showed its value on the console. We're getting good at this. Now let's narrow the variable. Let's say I wanted to create a float data type from my double variable. Well, that would mean casting my double to a float. And since a float is smaller than a double, I can't rely on Java doing that automatically. I have to manually tell Java to perform that cast. So let's do it. On the line below our double, let's add this code. Float my float equals, and then in round brackets, float, and then my double, semicolon. Now in the line below our printline command, let's add this code. System.out.println my float, close bracket and semicolon. Excellent. So what we've done here is we've created a new variable called myFloat that is using the float data type, and we've initialized its value from a double. But the important part of the code is that we specifically told Java to convert the double value to a float by adding the round brackets and the keyword float before the myDouble variable. Then we added another printline command to output our float value to the console. So let's save this and run it. Uh-oh. Suddenly we're seeing infinity in the console. Well, that's because we tried to put a value that's simply too large to fit into a float, so we overran it, and for float that results in infinity. That's the danger of narrowing. If you're trying to pour a glass of water into a thimble, you will overrun the container. So let's fix that. Let's change the double.max value to integer.max value. And now let's save and run this. Ah, much better. Now we see both values in the console. You can see that the float value is slightly different though, so that tells us the cast isn't necessarily exact. Regardless, let's keep going. Let's repeat the whole process for a long. Below our float, let's add this code. Long space mylong equals, and in round brackets, long, and then myFloat. And then let's add another print line, system.out.println mylong. Excellent. And now let's save and run this to see what we get. Perfect. We got the expected value. The format of the value is slightly different again, but it appears to be the same value. But wait, there's more. Let's try this with the int. Below our long, let's add this code. Int space myInt equals, and then in round brackets, int, and then mylong, semicolon. And then the print line command, system.out.println myInt. And now let's save and run this again. What is this now? We narrowed a huge number down to an int and got a negative number? What's that about? Well, this is once again the danger of narrowing. Downwards casting isn't exact. We lose some precision as the narrowing happens. So in this case, we've overrun the integer just enough that it rolled over to the other end of the spectrum. So you can see it's not going to work great. So let's fix that. Let's change our original value from the maximum size of an integer to say 65,000. Now let's run this again. Much better. Now we see all the values are exactly the same in the console. Fantastic. So let's keep going. Below our integer, let's add the code short myShort equals short in round brackets, and then myInt. And we'll add another console output, system.out.println myShort. And don't forget the semicolon. Now let's save and run this. What? Again? Oh man, now our number is overrunning the short. Well, let's change the number from 65,000 to 1,000 then. And we'll save and run that. Perfect. We're back to normal. All right, let's do one more cast, and you probably guessed which one. Below our short, let's add byte space myByte equals, and then in round brackets, byte, and then myShort. And we'll add a system print line, system.out.println myByte. Excellent, so we'll save and run this. Aw man, well, should we be shocked at this point? Another overrun. So that's narrowing in Java. You can convert from any data type to another. But where compatibility is a problem or overruns happen, you could find yourself in a position where you're getting unexpected results, just like we did. So be very careful about what you're casting from and to. Regardless, this has been how to perform a narrow cast. Great job! One of the most basic, common, and important non-primitive classes in Java is the string class. In fact, the string class is so common that most other programming languages include string as a primitive. So Java's a little special here. Now, the purpose of the string class is to define and manage text. Now, while a string is a non-primitive data type, it's actually composed of a primitive data type. Effectively, a string is a collection of chars. In fact, it's a special array of chars. But probably the most important detail about a string is that it's immutable. Immutable means that the value cannot be changed. That's right. Once you set the value of a string, that's it. That's what it is, forever. Oh, sure, you can create new strings, and you can even overwrite your existing string variables to make it look like you've changed the value, but you're not actually changing the value. In fact, the way it works is that Java allocates an area of memory where your string is located, and that's why you can't change it. If you want to change it, you need to create a new string, which means a new area of memory, and override the original value so Java can recover that bit of memory. In Java, there are two main ways that you can create an instance of a string. The first, and frankly easiest, is to use a literal. What that means is that you can define a string simply by saying it equals a piece of quoted text. And the second way is to use the new keyword. In this case, you create a new instance of the string class and pass it the text that you want it to be equal to. Now, the advantage of the new keyword is that you can create an instance of a string based on other data types, like arrays or chars, and it will also always create another area of memory. Now, the advantage of the literal, besides of course being easier, is that Java keeps all the literals in what it calls a constants pool. So if you created two strings with the same literal, Java would actually optimize your memory usage by having both variables point to the same memory block. So what's the syntax that we can use when creating a string? What's the actual code that we would use to create a string and then use it? Well, as I said earlier, there are two ways to do it. On the screen, we can see some code snippets that represent those two ways. At the top of this snippet, we see a string creation using a literal. You can declare your variable with a single string myString. Now, obviously, the text myString is the variable name. Then, after an equal sign, you can provide the text that you want to initialize the string variable to in double quotes. In the case of this snippet, we're saying that the myString variable is being set to the literal constant of hello world. Now, at the bottom of the snippet, you can see an example of creating a string using the new keyword. This code once again creates a string called myString, except this time, after the equal sign, we say new string. And then in the string's constructor, we pass in a double quoted string. Now, unlike using the literal, every time you use the new keyword, Java will allocate a new memory location for your string value, even if there's another string using that exact same value. In other words, Java guarantees a different object in memory if you use the new keyword. Downside is that it reduces the chances of Java being able to optimize your code's memory footprint. Now, the string class in Java has quite a number of built-in methods that can be used to attain information, or new strings altogether, from a given string. As an example, here are a few very common methods that can be used against a string. First, we have the char@at method. It can be used to search for a specific character in a string and return its index location. Next, we have the compare_to method. This can compare two strings and tell you how different they are based on the Unicode character values of the strings, and it's not often used. The concat method allows you to add a string to your string and produce another string. Now remember, strings are immutable, so you can't change your existing string, and that means that the concat method actually returns a whole new string. The contains method allows you to search for a piece of text in your string, and the result will be true, meaning it found the value, or false, meaning it didn't. Now, unlike the compare_to method, the equals method actually tells you if two strings are the same or not. If they are, the method will return true. And next there's the index_of method. Now this method is used to define at what index you might find a piece of text in your string. If the value isn't found, -1 is returned. And the length method tells you how many characters are in your string. The substring method is useful for being able to pull out parts of a string into a new string. And finally, the two lowercase and two uppercase methods create new versions of the string in all lowercase or uppercase respectively. Now, just because a string is immutable, it doesn't mean that you can't do things with it. In fact, let's consider this code snippet. In this code snippet, we have two strings. One is named mystring1 with a value of hello and a space, and the other is named mystring2 with a value of world. Then we create a whole other string called mystring3, and we make it equal to mystring1 plus mystring2. Now this results in the creation of a whole new block of memory that equals the value of the first two variables put together. Then, finally, we output the value of mystring3 to the console, and we get a value of hello world. But there's another way to combine strings, and that's to use the concat method. Let's consider this code snippet. In this code snippet, we once again have the same two strings. We've got mystring1 with a value of hello and a space, and we have mystring2, which has been given a value of world. Then we once again create a whole other string called mystring3, but this time we make it equal to something else. This time we take the mystring1 variable and call the concat method with the mystring2 variable as the parameter. Now what this does is add the value of string 2 to the end of string 1 and output a new string. And strings are immutable, so it doesn't change string 1 or string 2. Instead, it outputs a whole new string. So if we put the result into a new variable, mystring3, and then output the value of mystring3 to the console, then we get the value of hello world. Now I will tell you that the concat method is way more efficient than the plus operator, but it can only work with two variables at a time. Next, let's look at an example of a code snippet that shows how we would use the length method. In this code snippet, we create an instance of a string with the text hello world. Then, in the line below, we call the length method on that string, while outputting the result to the console using the print line command. Now, the purpose of the length method is to return the total number of characters, including spaces and special characters, in the string. Now, if you manually counted the number of characters in the string hello space world, you would arrive at 11 characters. So if we ran this code, that's what the result of the length method would be. And finally, let's take a look at a small code snippet and see the char@at method in action. In this code snippet that we have here, we create an instance of a string with the text hello world once again. Then in the line below, we call the char@at method on that string and ask for the character at index 6. Now the purpose of the char@at method is to return whatever character is at the given index. Now remember that indexes are all 0-based, so that means that index 6 actually means the 7th character in the string. So in this case, that would be the letter W in hello world. So if we ran this code, it would output the letter W to the console. In this demo, we're going to go over the features of the string class in Java. To do that, we're going to create a class in our existing project and then create and display strings in a couple of different ways. Alright, so to do this demo, we're going to piggyback a bit off our previous demos, which we built in Eclipse. So let's head over to the Eclipse IDE now. Alright, so I already have our project open from the previous demo, but if you don't, why don't you go ahead and do that now. Now, what we're going to do in this demo is we're going to create a simple string variable and then call a few methods to show what we can do with strings. To do that, we're going to create a new class so that we can start from a fresh canvas. So the first thing we're going to do is create that class. And to do that in Eclipse, let's click on the File menu and select New Class. Perfect. Now in the pop-up, Eclipse is asking us for information about our class. So let's give it a name. In this case, let's call it strings with a capital S. Now, we'll leave all of the settings default, but let's check the public static void main method stub checkbox and leave everything else alone. And then we'll click Finish. Excellent. We have our class and we can get started. So now we can get to creating and using a string. So let's start by creating a string variable. Let's replace the comment in the main function with the following code. String space myString space equals space and in double quotes hello, and don't forget to end with a semicolon. Good. Now let's drop a couple of lines down and type the following code. System.out.println open bracket myString close bracket semicolon. Now what we've done here is we've created a string variable named myString, and we've initialized it with a value of hello. Then we're using the println command to output the value to the console. So let's test this. Let's save the file with a Control S, and then run the project with a Control F11. Alright, so we're seeing the text hello in the console at the bottom of the screen. Nice job. Now before we go any further, notice that the hello has a capital H. Now remember that a string is a non-primitive data type, and that means that there are methods and properties that we can access against it. So let's do that. Below our println command, let's add another line of code like this. System.out.println open bracket myString dot char at with a capital A open bracket 1 close bracket semicolon. So here we're calling the char at method against our string variable. We're asking for whatever character is at index 1 of the string. And remember that in Java, indexes are 0-based. So asking for a character at index 1 is actually asking for the second character. So if we count that out, then the second character is the E in hello. So let's save this and run it to find out. Hey, perfect! We got the letter E in the console at the bottom of the screen. Great! Now let's add another method call. Beneath our last println command, let's add another line of code like this. System.out.println open bracket myString.concat open bracket and then in double quotes space world and the double quotes and the brackets and semicolon. So here we're calling the concat method against our string variable. We're passing in a value of space world. And what that means is we're asking Java to create a new string that appends space world to our existing string of hello. So if we run this code, we should get hello world. So let's save the file and run it and see what happens. Perfect! Hello world! Nice! Next, let's use the contains method. In the next line of code, let's type this code. System.out.println open bracket myString.contains open bracket double quote world double quote and then we'll close the brackets and a semicolon. Now what we're doing here is we're checking to see if our string contains the text world. Now remember that strings are immutable. In our previous line of code, we asked to add the word world to our string. But that should create a whole new string. That means that our existing string variable should not have the word world in it, and it should still just be hello. So if we try to find world inside a string that should only contain hello, we shouldn't find it. So let's run it and see what it says. We'll save it, and we'll run it. Excellent! The result is false, and that's exactly what it should be. But let's change it to make sure that we're using it properly. Instead of the text world, let's change it to EL. Now we know that that text is somewhere in the word hello, so this should give us an answer of true. So let's give it a rip. Nice, it's true. Okay, so now let's use the equals method. This is like the contains method, except instead of looking to see if a piece of text exists inside the string, it checks to see if the whole string equals some text. So let's try it. In the next line, let's type this code. System.out.println or println open bracket myString.equals open bracket double quote foo close quote close brackets and semicolon. So what we're doing here is we're asking Java if our string value is exactly the same as the text foo. Well, we know they're not the same, so we expect a value of false here. So let's run it and find out. And there it is, false, just like we expected. Okay, so now let's change the text foo to the text hello. And now let's try that. False again. Why is that? Well, it's because in Java, strings are case sensitive. Remember that we said our text hello has a capital H. So the text hello with a lowercase is not the same as the text hello with a capital H. So now let's try changing our text to capital H hello and run it again. That's got it. Perfect. Now continuing on with the searching pattern, let's take a look at the index of method. So in the next line, let's type this code. System.out.println open bracket my string.index of with a capital O, double quote, LL, double quote, close the brackets, and the semicolon. So what we're doing in this code is we're asking Java to tell us at what index we can find the text LL. Now remember that indexes in Java are zero-based, and we know that the text LL is in the string, and we know that the L's are the third and fourth letters in the word. But since indexes are zero-based, they're actually indexes 2 and 3. So that means that the text LL should begin at index 2. So let's run this code and see what we get. Perfect, we got index 2. But what if the text we're looking for doesn't exist in the string? Well, let's try it and see. Let's change the text we're looking for to foo. And now let's run that. So you can see now that we got a value of -1. Now, in a string, nothing can be at index -1. So if you get a value of -1, it really means that the text that you're looking for is not found in the string. Okay, so next let's use the length method. In the next line, let's type the following code. System.out.println open bracket my string.length open close bracket, then we'll close the bracket for the print line and a semicolon. Great. Now the length method tells us how many characters, including spaces and special characters, are in the string. So if we count the letters in the word hello, we get 5. So if we run this code, that's what we should see. So let's run the code and find out. Nice! Man, we're killing it here. Alright, lastly, let's take a look at the toUpperCase method. In the next line, let's type this code. System.out.println open bracket my string.toUpperCase with a capital U and a capital C, open close brackets, and then don't forget the semicolon at the end. Now the toUpperCase and the toLowerCase methods both work the same way, and their intent is pretty obvious from the naming of the methods. So what we expect to see here is that the string will be output as all uppercase characters. So let's run it and find out. Excellent! We got our string output in all capital letters, and nothing says warm greeting like screaming hello at somebody, right? So that's the string class and its methods. There are other methods and ways that you can use the string class, but this gives you a good idea of how to interact with it. Now remember that strings are immutable, and that means that they can't change. So you'll need to use these methods to gather information about your string and then generate new strings. So, happy stringing! In Java, strings are immutable, and that means that they can't be changed. To change a string means that you actually need to create a whole new string or overwrite your existing variable. So how do you work around that? Well, you can use the StringBuilder class. Like a string, the StringBuilder class is ultimately a collection of characters that are all put together to form a piece of text. Now the purpose of the StringBuilder is to manage the memory allocation of your text under the hood. The result is that you can call methods on the StringBuilder and actually manipulate the text that it contains. What that means is that the string value managed by the string class is mutable, which means that it can be changed. Now, the StringBuilder is not a replacement for the string class. It's better to consider the StringBuilder class as an alternative to the string class. The methods and the way that you interact with it is different than string. And you can't initialize it with a literal. So it is different, but it's a good alternative. In fact, StringBuilder is very useful for looping and threading conditions because it manages memory for you behind the scenes. Now, the StringBuilder class is extremely useful. It's fast and efficient. It manages strings and allows you to manipulate text without having to create other variables or override existing variables. As I said, it's particularly handy if you want to build strings using a looping mechanism. The StringBuilder class is almost identical to another class called StringBuffer. StringBuffer can also be used to manipulate strings in almost exactly the same way. It even has the exact same methods as StringBuilder, so it's worth exploring that class too. But the main difference between the two classes is that StringBuilder is thread safe, and what that means is that it can be accessed from multiple threads at once without collisions. However, it achieves that by making no guarantees of synchronization. In other words, if you were trying to append a bunch of text to a string builder from a bunch of different threads all at once, there would be no guarantee of what order those values would go in. However, the advantage of the string builder over the string buffer is that it's much faster and much more efficient. I personally use string builder all the time. So how would we go about using string builder? Well, the good news is that the string builder class is well known, and so it's built in just like the non-primitive cousin string. And that means that in order to use StringBuilder, you don't have to import any classes or packages. You can just get right to using it. And just like other non-primitives, you can create an instance by declaring the data type, then giving a variable name, and then, after an equal sign, create a new instance of that data type using the new keyword. So you can see in our example here that we're creating a new string builder named myBuilder. Now, as mentioned, the StringBuilder class allows strings to be changed. In other words, the strings are mutable. So to do that, there are a few methods that are included in the StringBuilder class. Specifically, the append method allows us to add more text to the existing string. The char_at method allows us to find a character in the existing string. The delete method allows us to remove a portion of the string. The insert method allows us to insert text somewhere in the existing string. The length method allows us to count the number of characters. The replace method allows us to replace a portion of the string with some other text. The reverse method allows us to reverse the order of the string. And finally, the substring method allows us to pull a portion of the string out into a whole new string. Now, it's important to note that most of the StringBuilder class methods use indexes to understand where to make the changes in the existing string. And those indexes are always zero-based. So a value of 0 means the very beginning of the string. Now, unlike the string class, you can't create a string builder class by just defining a string literal. You must always use a constructor. In other words, you'll always have to use the new keyword. And the string builder class has a bunch of constructors that you can use. For example, you can use the default empty constructor to simply create an instance and then get started. And this is particularly useful ahead of looping algorithms. You can also pass a char sequence value into the constructor to create a string entry from that. Now, if you want to set the initial capacity of a string builder instance, you can do that by calling the constructor that accepts the initial capacity value. Now, this is useful in cases where you want to keep a close eye on how much text is being allowed into that buffer. And finally, you can create an instance that already has a string in it. To do that, you can use a constructor that includes a string parameter. Now, let's take a look at an example of how you would use the append method, let's say. In the code snippet we see here, we're creating an instance of a string builder class. Then we use a for loop to iterate over a piece of code 10 times. Now, for each index of that loop, we call the append method to add the current index of the loop and a comma to the existing string. So the first time the loop runs, the string builder would be empty and the index would be 0. So after the append, the value of the string builder would be 0, comma. Then in the next iteration, the value of string builder would now be seen to be 0, comma, and the index would be 1. So after that append, the value of the string builder would now be 0, comma, 1, comma. And this would go on until the loop is finished, all 10 iterations. Now, once the loop is finished, we can output the value of the string builder to the console. So we get a final output after 10 iterations of 0, comma, 1, comma, 2, comma, 3, comma, 4, comma, 5, comma, 6, comma, 7, comma, 8, comma, 9, comma. Not too hard? In this demo, we're going to go over the features of the string builder class in Java. To do that, we're going to piggyback off our previous demo and then create an instance of a string builder object, and then explore the methods and features available within that object. Alright, so to do this demo, we're going to piggyback a bit off our previous demos, which we built in Eclipse. So let's head over to the Eclipse IDE now. Alright, so as you can see, I already have our project open here, but if you don't, go ahead and open it now. Now what we're going to do in this demo is we're going to create an instance of the StringBuilder class and then call a few methods to show what we can do with it. And to do that, we're going to create a new class so that we can start with a fresh canvas. So the first thing we're going to do is create that class. To do that in Eclipse, let's click on the File menu and select New Class. Perfect. Now in the pop-up, Eclipse is asking us for some information about our class. So let's just work on the name. We're going to call this Builder with a capital B. Good. Now we'll leave all the defaults alone and leave everything as it is, but we will check the public static void main method stub checkbox, and then click Finish. Excellent. We have our class. Now we can finally get started. Alright, so now we can get to playing with the StringBuilder. So the first thing we need to do is create an instance of a StringBuilder. So let's replace the comment in the main method with the following code. StringBuilder with a capital S and a capital B space builder equals new space StringBuilder, again with a capital S and B, open bracket, double quote, hello with a capital H, double quote, close bracket, and a semicolon. Good. Now unlike the string data type, in order to use the StringBuilder, we must use the new keyword to create a new instance. You can't set it to a string literal like we can with strings. Now just to see that this is working, let's add a print line command below our new builder object to output its value to the console. So let's type system.out.println open bracket builder close bracket semicolon. Good. Now let's save this file with a Control S and run it with a Control F11. Excellent. So in our console output at the bottom of the screen, we can see that the StringBuilder outputs the expected hello. Nice. Now, the purpose of the StringBuilder class is to help us with manipulating otherwise immutable strings. Remember that strings are immutable, which means that they can't change. Well, the StringBuilder allows us to actually change the text that it's managing. So let's play with the builder a bit. First, let's make our greeting a bit more personal. Let's add our name text. So in the line right below our StringBuilder, let's add the following code. Builder.append, open bracket, and then double quote, space, your name, double quote, end bracket, and semicolon. Good. Now let's save the file and run the project. Hey, look at that. Now our name is being output to the screen with our greeting. Cool. But it's worth noting that with the StringBuilder, you can actually chain commands. In fact, let's go back to our append command, and before the semicolon, let's add this code. .append, open bracket, double quote, exclamation mark, double quote. And we'll save that and run the project again. Cool. So now we know that the builder is working just as we want and that chaining works quite well. Alright, so that's appending. But what if we wanted to put some text at the beginning or somewhere in the middle of the string? Well, with the StringBuilder class, you can call the insert method to do that. So let's try it. Let's pretend we wanted to insert a surprised exclamation at the beginning of our greeting. To do that, let's drop down to the line after our append and type the following code. Builder.insert, open bracket, 0, comma, and then in double quotes, the word O, exclamation mark, and a space. And then we close the brackets and a semicolon. Now, as you can see, the insert method accepts two parameters. The first parameter is the zero-based index of where to place the new text, and the second parameter is the new text to insert. It's important to remember that in Java, indexes are zero-based. So by putting 0 in our command, we're actually asking for our new text to be inserted right at the beginning of the existing text. Anyway, let's save the file and run the project. Excellent! Now we've added our surprise to the beginning of the string. Nice job! Alright, so we've appended text to the end and we've inserted text at the beginning, though we could have put it anywhere. But what happens if we want to replace text? Well, StringBuilder has us covered there too. To replace some portion of the text, we just need to use the replace method. But be careful though, this isn't like a search and replace. You need to know the actual index locations of the text that you want to replace. In fact, let's add another command here. On the line below our insert, let's type the following code. Builder.replace, open bracket, 4, 9, and then in double quotes, hi, comma, and then end double quote, end bracket, semicolon. Good. Now in this case, we're telling the builder that we want to replace whatever text starts at index 4 and ends at index 9 with hi, comma. So we've effectively decided that we want to replace our existing hello with something a little less formal, but also correct a bit of grammar by adding a comma. So let's save and run this. Perfect! We've successfully replaced hello with hi. Nice job. Alright, so now let's say that we feel that our surprise thing at the beginning is goofy and we want to remove it. Well, with StringBuilder, we can remove text pretty easily. So to do that, we'll use the delete command. So let's add another line of code after our replace line. Let's add this code. Builder.delete, open bracket, 0, 4, close bracket, semicolon. Good. Now, just like the insert and replace, the delete command is accepting index locations for which part of the text to remove. In our case, we're removing the O, the exclamation mark, and the space that follows it. So let's save and run this. Nice. Now we're just left with the hi and our name. Now finally, let's play with one more method of the string builder. Let's adjust our print line command. Instead of just outputting the contents of the builder, let's reverse the text. So let's add the following code after the builder variable, but still inside the brackets. Dot, reverse, open close brackets. Good. Now all this is doing is taking the contents of the builder and reversing the order. So let's save it and run it. Perfect! Now our string has been reversed. There's not much left of our original hello, is there? Anyways, that's it. That's the string builder. With this class, you can create and manipulate strings to your heart's content. Great job. So in this course, we've examined data types and how to perform actions on them. We did this by exploring programming Java data types, declaring and initializing Java variables, programming Java data type casting and conversion, and using Java strings and the Java String Builder class. In our next course, we'll move on to explore how to create and use methods to manipulate the data inside a class.
Let's begin by talking about what Java methods are. You might also hear Java methods called functions, and you can use these terms pretty much interchangeably. A Java method or a Java function is effectively the same thing. Whether you refer to these things as Java methods or Java functions, it's all referring to the same type of thing. And what that thing is a collection of code that performs an operation. We're trying to look for operations that we would have to carry out in our code repeatedly, and rather than writing in that operation over and over again, we put it into a method which allows us to call that method repeatedly rather than having to duplicate code over and over again. So an example of this could be the operation of adding 5 to a number. Let's say for whatever reason we have a piece of code and we have to repeatedly add 5 to different numbers. So what we could do is have an add5 method. And what that method would do is take a parameter, such as an integer, and it would return to you the result of adding 5 to that integer. And then we can continually add 5 to different integers by passing different integers as parameters to the method. And in general, these Java methods don't run automatically. There are a few exceptions that we'll get into down the road, but generally methods are run when they're called. So if you have a method that's part of a class, and you create an object out of that class, in order to run a method, you would have to use the dot syntax to say object dot method name. And then that would tell Java, now I want you to run this method. And as I alluded to, the real benefits of the use of Java methods is that we can write code once and then use it many times. We don't want to have to be writing any more code than we have to. So if you find yourself performing the same operation multiple times, that can be a trigger to you to think, oh, maybe I should be putting this into a method so I can be calling the method many times rather than writing this code over and over again. Now we can talk about some of the features of Java methods. The first is that they have to be defined within the body of a class, or that they have to be members of that class. And that's because you have to have either an object to call the method on, or an actual instance of the class to call it on in some way. And we can pass parameters to a method. If our method was completely fixed in the values that it had to work on, it wouldn't be very useful to us. We need to have it dynamic in some way. And that's where parameters being passed to the method come in. Let's go back to our add5 method. If our add5 method was fixed and it could only ever add 5 to the value 7, that's not very useful to us. That would only be useful in the case where we wanted to add 5 to the value 7. But if instead we take a variable parameter as an argument to our method, now we can add 5 to that parameter. And we can add flexibility and dynamicism into our code by passing different parameters. Now we could pass the value 4, and it would give us a value of 9. And then further on in our code, we could pass the value 6, and it would give us a value of 11. And that's how we build this dynamic nature into our code, by the use of parameters to our method. Another feature of the Java method is that it has the ability to return results to us. When we call that add5 method, it returns to us the result of adding 5 to our parameter. In that case, its return value is an integer. Java methods don't have to return anything. They can be void in the return type, which means they perform an operation but don't necessarily return a value. So let's take a printing method, for example. Say we have a method that formats our statements for printing to the console, and that's all it does. Well, in that case, it can be void because it's just going to print to the console, but we don't care about any return values there. So Java methods can return results, but they don't have to. Methods in Java can either be static or non-static. The difference between the two: static methods don't require you to first instantiate an object of a class in order to call them, whereas non-static methods do require you to call them on an object. You have to first create an object out of a class and then call the non-static method. So to give you an example of what this kind of means in practice, let's say we have a class called example. And example has a static method called staticExample and a non-static method called non-staticExample. Well, the static example I can call directly on the class. So I could say example.staticExample, and that's totally legitimate. But I couldn't do that with my non-static method. I couldn't say example.non-staticExample. I would have to create an object first, so I could say example object is now an object of my example class, and then I could call my non-static method. I could say object example dot non-static example, and that's how I have to call a non-static method. At this point, we have a pretty good theoretical idea of what methods are and what we can do with them. So let's take a look at a practical example of how we could actually implement methods. So first, how do we create a method? Well, we do it with a declaration such as is on the screen, static void my method. Let's look at each of these parts of the declaration in turn. First, we have static, and this is declaring whether a method is static or not. A method by default is non-static, so if you leave the static keyword out, that makes a non-static method. And if you put the static keyword in there, that makes a static method. Next, we have void. This is the return type. The return type of the method goes right before the method name, and it defines what the method is going to be returning. So if the method isn't returning anything, we would type void. If it's returning an integer, it would be int. If it's returning a double, it would be double, and so on. Next, we have my method, which is the actual name of the method. It's convention in Java to do camel case, which means the first word starts with a lowercase letter, and then every other word starts with an uppercase letter. And then we have an opening and closed round parentheses. And this is where you would put any parameters. A method doesn't have to take parameters, so in this case, it's not taking any parameters. But if it was, it would go within these parentheses. And then you have an open curly brace. And that open curly brace signifies where the code of your method starts. And then you have a closed curly brace to signify that your method code has finished. If we want to call a method, we use the terminology my method, in the case if our method is called my method, followed by parentheses. So it's the name of the method followed by parentheses and then whatever parameters have to be given to the method. In this case, our method takes no parameters, so we don't pass it any parameters. And then we have a semicolon to signify our method call is over. And what goes in front of the method call depends on whether you're dealing with a static method or a non-static method. So if it's a static method, you can put the class name in front. dot myMethod. And if it's a non-static method, you could have the object name dot myMethod. If our method did happen to take parameters, let's say between that parentheses in our declaration line, it took an integer n, then we could pass it an integer, such as we see here with myMethod, open parentheses, 10, close parentheses, semicolon. And this would pass the value 10 to our method. The code on screen here represents our method structure without a return value, in this case using void methods. So we have two methods within our main class. So our class declaration is the first line with public class main, and then an open curly brace, and then near the bottom of the screen, just above the output line, is the closed curly brace signifying the end of that class. And within that class body, we have two defined methods. We have myMethod, and we have a main method. Let's look at myMethod first. It's defined as public static void myMethod, and this follows the signature line that we looked at on the previous page, followed by an open curly brace, and then two lines of code. We define a string called myString, and we set it equal to hello world. And then we print out the value of myString to the console. And then we have a closed curly brace, which signifies the end of myMethod. Then we have our main method. And our main method is sort of a special method in Java that gives our code an entry point, a starting point. So you can think of the main method as the point where all of our code is going to start. And it's defined as public static void main, string args as parameters, and then an open curly brace, followed by a line of code saying myMethod with an open parentheses and a closed parentheses and a semicolon, and then a closed curly brace below that to signify the end of our main method. One thing that we haven't talked about is the public modifier in front of both of our methods. That public modifier defines who can see and use our methods. In the case of a public access modifier in our method, it can be used by any Java class. We could also have our methods as private, and then the method can only be used by the class that it is defined within. And we can also have protected methods, in which case the method can be used by any class within the same Java package. Now, going back to this, our main method is calling myMethod. So what will happen is all of the code within myMethod will get executed, so we will print out the value of myString to the console. And we see that at the bottom of our screen beside output where it says hello world, because that's what will get printed out by this method. Here we have an example of passing parameters to a method. So once again, we have a main class defined on the first line. And then within that, we have two methods. Our first is called public static void myMethod, and our second is our main method, public static void main. But our signature call for myMethod has changed a little bit. Now, in the parentheses, instead of being empty, we have two parameters, int I and int j. So what this is telling Java is that anytime myMethod is called, expect to also have two integers passed to myMethod. And what myMethod will do is print out the value of I multiplied by j, as seen on the code line between the open curly brace and the closed curly brace following myMethod. And then in our main method, we call myMethod, and in the parentheses, we have two values, 5 and 10. So 5 will be the value of I when the method is run, and 10 will be the value of j when the method is run. So what will happen is myMethod will be called, and then we'll run that code line, system.out.println I times j, which will be 5 times 10, the result of which is 50. And we can see that on our output line at the bottom of the screen, 50. And finally, we have an example of calling a method on an object. Once again, we have our main class defined on line 1, public class main, and we have two methods defined within main. We have our first method, public static void breed, and it takes one parameter of type string called dogbreed. And then we have our second method, which is our main method, public static void main string args. Within our breed method, we simply print out the value of whatever is passed to it as a string. So system.out.println dogbreed is the code contained within the body of our breed method. Now within our main method, we first create an object called myDog, and that's on the code line main myDog equals new main. So what this is doing is instantiating an object out of the main class and assigning it to the variable myDog. And what we can then do near the bottom of our main method is call the method on that object, as seen with myDog.breed, and then we pass it the string value Labrador Retriever. And once that is called, the method breed will be run and the value will be printed to the console. And we can see the output at the bottom of our screen, Labrador Retriever. This actually raises an interesting point. Our breed method is static, so we don't actually have to create an object in order to call it, but we are allowed to call static methods on an object. So just because we can call static methods on classes directly doesn't mean we have to. We can still call static methods on objects. In this demonstration, I'm going to show how we can create and use methods in Java classes. So within my IDE, on the left side in the project pane, I'm going to right-click on my source folder, navigate to New, and click Java class. And this will create a new Java class for me. In this case, I'm going to call it method example.java, and then I hit enter, and it creates the class for me. I'm going to hit enter one time to create a space between my method declaration and the closing curly brace. And we can see the declaration automatically created for me on line 1, public class method example. So here we have our class, and we'll create our method in the body of that class. Let's have a method within our method example that takes in an integer, and it will add 5 to the value of that integer, and then return the new value with 5 added on to the original value. So to start with, to declare a method, we need an access modifier. In this case, we're going to make our access modifier public so that our method can be accessed from outside of the class. Then we need a return type. In this case, since we're going to be taking in an integer and returning an integer, then our return type is going to be int. And then we need a name for our method. So we'll call it add5, and we'll do it in camel case, which means that the first word is lowercase with the first letter, and then every other word is capitalized at the start. And then we have our open parentheses and close parentheses. Between these, we're going to be putting in our parameters or arguments. So we're going to be taking in one integer, and we'll call it n. And then we need to define the body of our method. So we define an open brace and a closed curly brace. And now on line 2, you can see our full method declaration. Public int add5, open parentheses, int n, close parentheses, open curly brace. And then on line 3, we have a blank line where we're going to start to put in our body of code. And on line 4, we have our closed curly brace indicating the end of the method. And in this case, the method is very simple. We're only going to have a single return statement. We're going to say return n plus 5. And now on line 3, we have our return statement, which will take in the value of n, add 5 to it, and return that. So this is how we can create our Java method. Now let's look at how we can use our Java method. So I'm going to go back to my project window pane on the left side, right-click my source folder, select new Java class, and I'm going to call this one simply main.java. And main.java is going to house our main method, which we're going to use to call our add5 method. Here we can see we now have a main.java in my main project window. So on line 1, we have our class declaration with public class main. On line 2, I have the main method declaration with public static void main string args. And now we're going to use the method that we created in our method example class. Because our method in method example is not static, we first need an object of method example to work on. In order to do that, I'm going to create method example, which is the type of my object, obj, which is the name of my object, equals new method example. And now I have an object of type method example that I can work on. What we're going to do is print out the result of our add5 method. So on line 4, I'm going to type in system.out.println, and then we're going to call obj.add5 with the value 4. And if everything works as it should, this will take in the value of 4, add 5 to it to give us a result of 9, and print that to the command line. So let's see if that works the way that we expect it to. I'm going to go to the bottom left corner of my IDE and click on the terminal button to open up a terminal where I can compile and run my program. I'm not in the directory that I need to be, so I'm going to change directory into my source folder. And then I'm going to compile with javac my main.java class. And now I can run my main.java by saying java main. And in our console window, just below the line where I've called java main, we have the value 9, which is what we've expected. So this is how we can create methods and use methods in Java. Java accessor methods are methods that we can use to access the instance variables or fields or properties of a class. You might also hear Java accessor methods called getters. That's because you can think of them as getting something for you. You're asking the method to get me this value or get me this piece of data. Most commonly, the use case for Java accessor methods is to retrieve the values of private fields. Since a private field can't be accessed by anything other than the class that it's defined in, we have to have a way to get that value somehow if we need that value. And that's where we have the accessor methods come in. So an accessor method has to have access to the value that you're trying to access. So usually your accessor method will be part of the same class that the instance variable that you're trying to retrieve is in. They are declared public, and that's because they're designed to be used by other classes. So in order to have the visibility such that another class can use your accessor method, we make sure that they are public. And then some sort of data or value or property of an object is returned to you. And at that point, what you do with it is up to you. And there's a specific naming scheme that's generally followed by accessor methods in Java. And that's you preface the method name with the word get. So you have something like get value or get number or get string. Whatever it is, you say get and then some sort of description of what it is that you're getting. And that's why they're often called getters. They don't have to follow this. That's just a convention that you'll see most commonly in code. And to conform and keep your code more manageable, it's good to follow that naming convention. Let's see what an accessor would actually look like in Java code. So on the screen here, we have an example of an accessor. It's defined within an accessor example class. So the class declaration is on the first line where it says class accessor example. And then we have an instance variable, which is defined underneath of that, called private var type var name. Now, this instance variable is private, so it's only accessible to the accessor example class. But if we needed to get the value of var name, then we'd have to have some way to access it from outside of the class. And that's where the accessor method comes in. So below our instance variable, we have the common accessor method. And below that, we have our actual definition of our accessor method. So it's public var type get var name. And then in the body of the method, it returns var name. So let's look a little closer at what's going on here. In the declaration, our first access identifier is public, as we touched on earlier. Its return type has to match the type of the variable that you're retrieving. In this case, our type is var type, So the return type of our accessor method is also var type. And then we have our naming convention. We have the accessor method starts with get, and then the name of what we're trying to retrieve, so var name, which leads us to the full accessor method name, get var name. Our method doesn't take any parameters, so our parentheses are empty, and that's because it doesn't need to. It's always going to retrieve the same variable. And then in the body of the code, it returns var name. And that's what an accessor method will look like in code. Here we have a more concrete example of an accessor method. Now that we know the rough syntax, let's look at an actual implementation. On the screen, we have a code snippet, and it's defining a class called dog. Dog has a instance variable private string breed, and then below that, it's got a constructor, public dog, which takes parameters string get breed, which will then set the value of breed to whatever is passed to the constructor in getBreed. So when we create the dog class, breed will be set by the constructor. And then below that, we have our accessor method. And our accessor method is defined by the line public string getBreed, and it returns the value of breed. We can see that since breed is of type string, our accessor method returns string. Our breed is private, while our accessor method is public. Our accessor method does not take any parameters because it doesn't need to, and it returns breed in the body of its code. And here we have an example of using this accessor method. So we have a new class called findMyDog, and findMyDog has a main method defined in it, where it says public static void main string args. And the main method is first creating an instance of our dog class on the line where it says dog1 equals new dog, and it's passing the value of Labrador Retriever to the constructor. So in dog1, the value of breed is going to be equal to Labrador Retriever. And then we want to print out that value. So our next line down is system.out.println, and we print the string breed followed by dog1.getBreed. So dog1.getBreed is an example of using our accessor method because we're calling our accessor method getBreed on our dog object dog1, and that returns to us the value of breed, which has been set to Labrador Retriever. So our output, as seen on the bottom of the screen where it says output, will read breed Labrador Retriever. Now let's take a look at a slightly different way of using an accessor. And this is a little less explicit than what we've looked at before. So here we have an accessor with multiple parameters. On the bottom of our screen, we have a dog class, and the dog class is a little different than our previous dog class. It's defined with 3 string instance variables: private string breed, private string color, and private int age. And then below that, it has a constructor, public dog, and it takes 3 parameters: string get breed, string get color, and int get age. And then it sets breed equal to get breed, color equal to get color, age equal to get age. So now when we instantiate an object of the dog class, we have to pass it 3 arguments corresponding to the breed, color, and the age in order for the constructor to run properly. In the top of our code example, we have another accessor example class defined with public class accessor example, and it has a main method within it, public static void main string args. And the first line within the main method defines a new dog object instantiating out of the dog class with dog1 equals new dog, and we pass it the 3 arguments: Labrador Retriever, gold, and 7. And then we do system.out.println dog1. Now, as of right now, we haven't really used an accessor. If we were to run this code as it is, this would print out a weird memory address pointing to where dog1 is stored in the memory, but we can use toString to act as our accessor method. So toString is built into every class by default, but if we explicitly define it like we have here with public string toString, and you would define this in your dog class, then it overrides the default behavior of toString, and it will instead perform whatever we define it to perform. In this case, we're using toString like an accessor because we have within our toString method return followed by the string breed concatenated with our breed instance variable, which is then concatenated with the string color, which is then concatenated with our color instance variable, which is next concatenated with the string age, which is finally concatenated with the age variable. So the actual result of this, when we call our print method, which was system.out.println dog1, is that it will look for our toString method, and it will actually print out breed, Labrador Retriever, color, golden, age, 7. So in a way, our toString method is acting as an accessor because it's retrieving these variables for us and then printing them out to the screen. In this video, I'm going to demonstrate the use of Java accessor methods. To get started, on the left side of my project window, I'm going to locate my source folder, right-click on it, navigate to New, and click Java class. And then we're going to make a Java class called AccessorExample.java. And now we have our AccessorExample class. On line 1, the class declaration reads public class AccessorExample with an open curly brace. And on line 3, we have the closed curly brace representing the end of the class. And it's within this class that I'm going to create an accessor method. Now, Java accessor methods are typically used to retrieve the value of an instance variable within a class. So first off, our accessor example is going to need some instance variable for us to retrieve. So let's create one now. On line 2, I've created our instance variable. I've called it retrieve_this. I've given it a private access modifier so that it's only accessible within this class. And it's of type int, and its value is 5. Since this instance variable is private, that means that any other class won't be able to directly access this value. But there are a lot of other times where I might want other Java classes to be able to get the value of this instance variable. So in order to facilitate that, I'm going to need an accessor method. You might also hear accessor methods called getters. That's another common term for these. And our accessor method is going to be public so that it can be accessed by other classes. And now on line 4, we have the declaration of our accessor method. It's public, like we mentioned. Its return type is int because the instance variable that it's going to be retrieving is of type int. We've called it getRetrieveThis. This is why people often call accessor methods getters, because they usually start with the word get. They don't have to, that's just a convention. It doesn't take any parameters because it doesn't need to. It's only going to return the instance variable. And then we have our open curly brace, followed by a closed curly brace on line 6. And now we're ready to put into the body of this accessor method what it's going to do. And what it's going to do is return retrieve_this. Which is what we've now put on line 5. Return, and in parentheses, the instance variable retrieve_this. So what this accessor method will do is give us a way to get the value of that instance variable. So let's see how you would use this by creating a new main method that will make use of this accessor method. Once again, I'm going to navigate into the left side of my project window, right-click on my source folder, navigate to New, and click Java class. And in this case, we're going to create a main method within a main.java class. And here I've created our main class. On line 1, the declaration reads public class main with an open curly brace, and on line 3, we have the closed curly brace indicating the end of the class. And now within this class, I'm going to define a main method. Now on line 2, I have my main method declaration, public static void main string args. And that's going to be where I'm going to use my accessor. Since our accessor is not static, that means I first need an object to work on in order to be able to call our accessor method. So let's create an object of type accessor example to work with. Now on line 3, I have my object that I am ready to work with. It's called obj. It's of type accessor example, and we've created it by calling new accessor example. Now I have an object that can call our accessor method. What I want to do is print out the value of retrieve this, our instance variable, which is 5. I can't call using the dot syntax obj.retrieve this directly because it's private, but that's why we have our accessor method. So we can call obj.getRetrieve this to get the value. Let's see how that looks in a print statement. On line 4, we have our print statement now with system.out.println, and in the parentheses I've called obj.getRetrieve this, which should return 5. So if everything works like we expect, when we run this in the console, we should see the value 5 printed out. Let's verify that that's the case. I'll go to the bottom left of my screen in the IDE and click on the terminal button to open up a terminal. I will change directory into my source folder. I will then compile my Java package with javac main.java. And now I will run the Java program with Java main. And in our console output, just below where I've called Java main, we have the value 5. So that's how we can use our accessor methods, or getters, to retrieve private instance variables. Java mutator methods, also called setters, are used to change the elements of a class. So this is basically the opposite of a Java accessor or a getter, because we're using the mutator methods to modify the instance variables or the fields of a class. So we might use a mutator method to change the value of a private integer from 5 to 7, for example, using a mutator method. Going over some of the features of mutator methods, they demonstrate code encapsulation by having not only the data contained in a class, but also the methods used to operate on that data contained within that same class. Their access modifier is public, and the most common use case for a mutator method is to use the public mutator method to modify a private variable of some sort. They don't have a return type, so in the method declaration, the return type will be void, and that's because they're not returning anything. They are instead accepting a parameter that matches the type of variable being modified, and then they are assigning that value to that variable. And that's all they're doing. They don't have to return anything. Let's take a look at the syntax of a mutator. On the screen, we have a code snippet, and it's declaring a class called mutator example. So in the first line, we see the class declaration, public class mutator example. And then below that, we have a private instance variable with some sort of type. So it's saying private var type var name. And then at the bottom of our class, we have our mutator method, where it says public void set var, and then in parentheses, it has var type var value, and then an open curly brace, followed by var name equals var value, followed by a closed curly brace. Let's take a closer look at this mutator method declaration. So first, we see the access modifier is public, because we want it to be available to any other class in order to allow us to mutate or set the private instance variable. The return type is void because the method itself is not returning anything. The name is setVar, and this is why they're sometimes called setters instead of mutators, because the naming convention is to have the word set followed by the rest of the method name. So in this case, we see our method name is setVar. And then it accepts a parameter, and the parameter matches our variable type. So the parameter for our mutator method is var type var value, and the var type is the same var type in our instance variable. And then in the body of the code, we're mutating var name by setting it equal to var value. And now that we have an idea of the general syntax of a mutator, let's take a look at a more concrete code example. So in this code snippet, we have a class declaration defining a class called dog. And that's on the first line where it says public class dog. Inside of dog, we have a private instance variable called breed, and it's of type string. That's on the second line where it says private string breed. Then, on the next line down, we have our mutator method, where it's defined by the line public void set breed, and it accepts the parameters string new breed. So our mutator method is public, the return type is void, and the name is set breed. And that's following our naming convention of set, and it's telling us what it's setting breed. And then in the body of the code for our mutator method, we set breed equal to whatever the parameter is. So in this case, breed equals new breed. And then our mutator method will actually print out the value of breed, just for clarity's sake. So it says system.out.println breed. And then we have our main method followed by that, where it says public static void main string args, and then the call to the setter goes in that main method. So this is what the main method would look like when we actually want to use the mutator method. So in public static void main string args, we first create an object of type dog. So we have dog type equals new dog, and then we can call the mutator method on that object by saying dog type dot set breed, and we pass it an argument Labrador Retriever. And the result of that is that the breed within the dog type object will be set to Labrador Retriever, and then it will be printed out to the screen. And we can see that on the bottom of our screen where it says output, and it prints Labrador Retriever. In this demonstration, I'm going to show the use of Java mutator methods. Mutator methods are also sometimes called setters. That's another common term for them. In order to see how these work, I'm going to get started by creating a Java class. So in the left-hand side of my screen, in my IDE in the project window, I'm going to click on the source folder, right-click on it, navigate to New, and click Java class. And I'm going to create a Java class called Mutator Example. And now in my main project window, on line 1, I have the declaration for my mutator example class, public class mutator example, followed by the open curly braces and the closed curly braces on line 3, indicating where the body of my class will go. Mutators in Java are used to modify the value of an instance variable. Generally, we use it to modify the value of a private instance variable. So to see how this works, first we'll have to have some sort of private instance variable defined within our class. So let's go ahead and do that now. And now on line 2, I have a private instance variable. It's called mutate this. It's of type int. Its access modifier is private, and its value is 7. So this is the value that we're going to mutate or set. Because this variable is private, that means we can't access it from outside of this class. But if for some reason within our code we wanted to be able to change this value, that's why we need a mutator method. So let's create that on line 4. And now we have our mutator method declaration, or our setter method. And it's on line 4. It's public as an access modifier because we want to be able to access this from outside the class. Its return type is void because it's not actually returning anything. It's just going to set the value of mutate this. Its name is called setMutateThis, which is why people often call these mutator methods setters, because they often start with set. They don't have to, that's just a convention. It takes in one parameter, an integer n, and that's the value that it's going to set mutate this to. So we're going to be using this mutator method to override the default value of 7 in mutate this. So to do that, we're going to set the mutate this variable equal to n within our mutator method. And that's what we've done here on line 5. The keyword this is telling Java to look for a mutate this variable that's defined within this class. And then we're setting that variable equal to n on line 5. I'm also going to add an accessor method or a getter method to this class in order to be able to show the before and after the mutation happens with the mutator method. And I've defined that accessor method on lines 8 to 10. So on 8, I have the declaration public int get mutate this, and then on line 9, it returns the value of mutate this. So I'm going to use this to first retrieve the value of mutate this before we modify it, and then once again after we've modified it. So in order to see how this works, let's create a second Java class with a main method in order to use these methods. So once again, I'm going to navigate on the left side of my screen in the project pane window, right-click on the source folder, navigate to New, Java class, and create a new Java class called main.java. And now we have our main class. On line 1, we have the declaration public class main, then we have the open curly brace, and on line 3, we have the closed curly brace indicating the end of the class. Within this class, I'm going to define my main method. And we can see the main method is now defined on line 2 with public static void main string args. And within this method, we're going to make use of our mutator method. Our mutator method is not static, so we first need an object of type mutator example in order to work with these methods. So let's go ahead and create that object now. And on line 3, we've created that object. It's called obj, its type is mutator example, and we've created it by calling new mutator example. This obj we can now use to make use of the mutator method. So let's do 3 print statements. The first print statement is going to show the value of mutate this as it is now before we do any changes. And we have that on line 4 with system.out.println obj.getMutate this. Since we haven't made any changes, we should see this value print out as 7. Now, let's use our mutator method to change the value of mutate this to 9. On line 5, we've now used our mutator method. We've said obj.setMutate this, and we've passed it an argument with a value of 9. So now the instance variable within the class called mutate this should be equal to 9. So let's put a print statement right after this just to indicate to us that the value has been changed. And we put that on line 6 with system.out.println, and we're printing the string, the value has been changed. And finally, let's put a third print statement in to print the current value of mutate this. And that's now on line 7. Once again, we've used the exact same getter or accessor method that we used on line 4. On line 7, it reads system.out.println obj.getMutate this, but now we should see the value of 9 printed to the console. So let's compile and run the program and make sure that everything looks and runs like it should. In the bottom left screen of my IDE, I'm going to click on the terminal button. I'm going to, within my terminal, change directory to the source folder. And then I'm going to compile my Java package with javac main.java. And then I'm going to run my Java program by calling java main. And now in the console output below java main, we see 3 lines. The first line has a value of 7, which is where we've printed out the current value of mutate this. Then we see our string, the value has been changed, because that's right after we've called the mutator method to change the value. And then we can see the value 9 printed out, because the value of mutate this has been changed with our setter or our mutator method. So that's how we can use mutator methods to modify private instance variables in Java. Method overloading in Java is where we have multiple methods that all have the same name, but have different parameters in some way. And then, because the methods all have the same name, Java decides at runtime, based on how the method is called at that point in the code, which instance of the method to use, and that's called polymorphism. And we have 3 ways to perform overloading. The first is with a different number of parameters. So we could have a method called overloaded, and in the first definition of overloaded, it takes 1 parameter. And then in the second definition of overloaded, it could take 2 parameters. And then Java will decide when that method is called, if it's called with 1 parameter, Java will use the instance where overloaded has 1 parameter. And if it's called with 2 parameters, Java will use the instance of overloaded where it has 2 parameters. We could also overload a method by giving it different types of parameters. So maybe we have an instance of overloaded where it takes an integer, and then we have an instance of overloaded where it takes a double. And Java will decide again at runtime, if overloaded is called with an integer, it will use the instance of the overloaded method that takes integer as a parameter. And if overloaded is called with a double as a parameter, then it will use the instance of overloaded where it takes a double as a parameter. And finally, we can overload by changing the order of parameters. So we could have an instance of overloaded that accepts an integer followed by a string as parameters. And then we could have a second instance of overloaded which accepts a string followed by an integer. Let's take a look at some examples of overloading. So in this code snippet, we have 3 method declarations, and they all have the same name. They're all called myMethod. But critically, they each take a different type of parameter. So the first declaration, static int myMethod, takes a parameter of type int. The second declaration, static double myMethod, takes a parameter of type double. And the third declaration, static float myMethod, takes a parameter of type float. Each method also has a different return type because what they're all doing is taking that parameter, assigning it to be equal to a variable of the same type as the parameter, and returning that variable. So the return type has to match the type of parameter in this case. But the return type isn't what's making this necessarily polymorphic. What's making this polymorphic is the fact that the parameters are different. By having one instance of myMethod take myVar as an int, another one take myVar as a double, and another one take myVar as a float, we've overloaded myMethod. And now Java will run whatever method matches the parameter type when the method is called. So if I pass an integer to my method, then the first instance of my method will be run where it says int return val equals myVar, return myVar. If I pass a double to my method, then the second instance of my method will be run where it says double return val equals myVar and return myVar. And if I pass a float to my method, then the third instance of my method will be run where we have a float return val equals myVar and then we return myVar. In our second example of overloading, we have a fully fleshed out class, and our class is defined on line 1 called public class method overloading. And in our class, we have an overloaded method called addMethod. And we can tell it's overloaded because we have 2 instances of addMethod, both with the same name. So our first line is static int addMethod, and it takes 2 parameters, int x and int y, and then it returns x plus y. And our second instance of addMethod is static double addMethod, and it takes a double x and double y as parameters, and it returns x plus y as well. And what makes this overloaded is the fact that the first instance takes 2 ints as parameters, and the second instance takes 2 doubles as parameters. And then below that, we have our main method, which is showing an example of how we can use these overloaded methods. So underneath public static void main string args, our first line is int add ints equals add method, and then we pass as arguments to add method 10 and 5. Since 10 and 5 are both ints, the first instance of add method, where it expects 2 ints as parameters, will be used. And the result will be 10 plus 5, which is 15. And 15 is an int, so we assign it to an integer type called add ints. And then our code prints that to the command line with system.out.println add ints. And our second line in our main method is double add doubles equals add method 10.0 5.0. So in this case, we're passing 2 doubles to our add method. 10.0 and 5.0 are both doubles. So the second instance of add method will be used in this case, where it will add double x plus double y. And the result will be stored in our double called add doubles, and that will be 15.0. And then this line is followed at the end with another print statement, system.out.println add doubles. And so we can see in the output, we have 15 and 15.0. So even though we've called the same method, add method, we've gotten different results because different instances of that method have been used based on what parameters have been passed. Now let's look at an example of overloading using different numbers of parameters. Once again, we have a class defined on line 1, public class method overloading, and we have an overloaded method called add method. But this method is overloaded in a different way now. So the return type for add method is int in both cases, because again, the return type is not what makes this overloaded. In our first declaration of add method, we have static int add method, and it expects 2 parameters, int x and int y, and it returns x plus y. And in our second declaration of add method, we have static int add method, but it expects 3 parameters, int x, int y, and int z, and it returns x plus y plus z. So the fact that add method in the first instance expects 2 parameters, and in the second instance expects 3 parameters is what makes this overloaded. So in our main method, public static void main string args, we have 2 calls to add method. On the first line, we have int add2 equals add method, and we pass as arguments 10 and 5. So because there's only 2 parameters, this will use the first instance of add method when it will return x plus y. So the result will be stored as 15 into add2, and then we print that to the command line with system.out.println add2. Then, in the second line of our main method, we have int add3, where we once again call add method, but we pass 10, 5, and 2 as parameters to our add method. So now we have 3 parameters, so the second instance of add method will be used, where we have an x, a y, and a z, and it will return 10 plus 5 plus 2, and the result will be 17, and that will be stored in add3. And then we print that out to the command line with system.out.println add3. And we can see the output at the bottom of our screen underneath the line where it says output, and the result is 15 and 17 as we expect. And finally, we have an example of overloading using a different order of parameters. So in this code snippet, we have a class called getFruit, and getFruit has an overloaded method called fruit method. In both cases, declaration starts the same with public void fruit method, but in the first instance, it expects an int called number as the first parameter, followed by a string called fruit as the second parameter. But in the second instance, it expects a string called fruit as the first parameter, followed by an int called number as the second parameter. And we can see based on the order of the parameters that our print lines are different. In the first case, we do system.out.println, the string there are concatenated with the parameter number, which is concatenated with the parameter fruit. And in the second instance, our print is different. In that instance, we print the parameter fruit, followed by the string cost dollars, concatenated with the parameter number. So if we look at our next class, which is defined near the bottom of the code snippet as displayFruit with public class displayFruit, it has a main method, public static void main string args. And in that main method, we first create an object out of the getFruit class called fruit with getFruit fruit equals new getFruit. And then we call fruit method twice. The first time we have fruit.fruit method and we pass it 12 and the string oranges. So in this case, it's an int followed by a string. And the first instance of the method will be used. And that's why on the output in the top right of the code, we see the first line is there are 12 oranges. Then in the main method, our second fruit method call, fruit.fruit method, passes apples as a string followed by an int as 2. And that's why in the output on the second line, our print statement is different because we've used the second instance of fruit method based on the order of parameters. And that's why it says apples cost $2. In this demonstration, I'm going to show how to use method overloading in Java. To get started, I'm going to create a class for us to work in. So on the left side of my IDE in the project pane window, I'm going to right-click on my source folder, navigate to New, and click Java class. And we're going to create a new Java class called overloadingexample.java. And now I have a class for us to work in. On line 1, we can see the class declaration, public class overloading example, followed by an open curly brace. And on line 3, we have the closed curly brace indicating the end of the class. So our class body will go between these two curly braces. Method overloading in Java is where we have two methods that have the same name, but they have differences in their signatures. So for example, you could have two methods with the same name, but that take different number of parameters. Or two methods of the same names, but they take different types of parameters. Let's see this in action. I'm going to create two overloaded methods in this class, and all they're going to do is perform different print statements based on how many parameters are passed to the method. So now I have the skeleton signature of my first method, which is defined on line 2. Public void print this, and it takes in a single parameter, int n. Now I'm going to create my overloaded method by giving a method with the same name but a different number of parameters. And now we've overloaded our method because on line 6 I have another signature with the same name, print this. Both methods are void and that they don't return anything. Both are public with their access modifier, but the second method on line 6 takes two parameters as its argument, int n and int y. So let's actually add some code to these methods. Now our methods have code and are actually doing something. So the first thing you'll notice is the actual parameters that get passed don't really matter. I'm not using them in this case. But what matters is that the number of parameters passed changes which method gets called. So if I pass one parameter, the first method from line 2 to 4 will get called, and I'll print out the line, you passed one parameter. As we can see on line 3, I have that print statement. Now if I pass two parameters, then the second method from line 6 to 8 will be called, and the print statement on line 7 will be printed saying you passed two parameters. But both methods have the same name. So how will Java know which one to choose? Well, it does this polymorphically at runtime. Let's see it in action by creating a main method for us to work within. So I'm going to create a second class by navigating to the project pane in the left side of my window, right-clicking on my source folder, navigating to New, Java class, and I'll create a new Java class called main.java. And now I have my main class as declared on line 1 with public class main. And within that, I'm going to define a main method. And now I've defined my main method on line 2 with public static void main string args. Neither of my overloaded methods in overloading example were static, so I'm going to have to create an object first in order to use those methods, and that object will have to be of type overloading example. So let's go ahead and create that now. And now I have my object. It's called obj as defined on line 3. It's of type overloading example, and we've created it by saying new overloading example. Now let's call our overloaded method, and we'll call it twice. The first time, I'm going to call it with one parameter. And the second time, I'm going to call it with two parameters. So on lines 4 and 5, I've called the same method, obj.printThis. But we can see on line 4, I've only called it with one argument, 5. But on line 5, I've called it with two arguments, 6 and 7. So what this will do is when I call print this on line 4, it should print out to the terminal, you only passed one parameter. And when I call print this on line 5, it should print out to the terminal, you passed two parameters. Because Java will decide based on how many parameters were passed, which method to pick. Let's make sure that this is the case. So I'm going to navigate to the bottom left side of my IDE and click on the terminal button. And then I'm going to change directory into my source folder. And then I'm going to compile my Java package with javac main.java. And finally, I'm going to run my program with Java main. And now in our terminal output, right below where I called Java main, we have two print lines. And the first one says you passed one parameter, and the second one says you passed two parameters, just as we expected. So this is how method overloading works. Interfaces in Java are very similar to classes in Java. And at first glance, they might appear to be the same thing, because they contain methods and variables just like a Java class. But there are a few key differences between an interface and a class. The first is that in an interface, all of your methods are abstract by default, and they don't actually contain any code bodies themselves. They have the method signature that defines the method name, the return type, its access modifier, and parameters, but it doesn't actually have any code. You don't specify what the method is doing. And any variables defined in an interface are public, static, and final by default. What's the purpose of interfaces in Java? Well, the first is that it helps us achieve abstraction in our code. And abstraction is a way of hiding the implementation from an end user or another developer, but still providing them with the necessary functionality to do their work. It also provides us with loose coupling because interfaces give us a method to reduce the dependency of our code modules on other modules and reduce the interdependency between classes. And it provides a method for us to implement multiple inheritance in Java. Java only supports single inheritance, so when you extend a class, you can only do so with one class. But with interfaces, you use the keyword implements, and you can actually implement as many interfaces as you want. So you provide a comma-separated list of interfaces, and that's a way of implementing multiple inheritance in Java. What are the features of Java interfaces? Well, an interface determines what a class does, but not how it does it. And that's because an interface specifies a set of methods, but it only specifies the signatures of those methods and not the code bodies. So really, when you are implementing an interface, you're making a promise to Java. You're saying, I promise that by implementing this interface, I will implement every method defined in this interface. So if an interface has 3 different methods defined, when you implement it in your class, you have to define those methods and provide the body of code for those methods saying what they'll do. And that forces a certain structure to the code. So if you have some sort of extensible framework and you want to make sure that any developer who is implementing your code or your framework follows a certain set of guidelines, then you would provide this interface with these methods, and then you're guaranteed that any developer implementing your interface will have those methods. The way that they work and the way that those methods run will be different based on each developer's use case, but at the very least they'll have those methods. And there are some rules surrounding interfaces. One is that an interface cannot implement another interface, but an interface can inherit from another interface, so you can extend another interface. Let's take a look at an example of what an interface actually looks like in code. So this code snippet demonstrates what an interface looks like in Java. On our first line, we have interface example. So the keyword, the first word interface, that tells Java that we're defining an interface. And then interface example is the name of the interface. And then we have a comment below that line saying, will be regarded as public abstract void myMethod1 and public abstract void myMethod2. And that's just describing how Java will interpret these methods. But within our interface, we have two methods defined, public void myMethod1 and public void myMethod2. We can see that's all of these methods have written down. There's no open and closed curly braces defining where the body of the code would start and stop for a method, because we don't have any code defined. We just have the pure signature, followed by a semicolon to indicate the end of the line. And now we're looking at a code snippet that shows how we can actually use that interface. So on the first line, we see public class imp methods implements interface example. Let's look at this a little closer. We have a class declaration, public class, and our class name is imp methods. After our class name, we have the keyword implements. So this is telling Java, expect us to be implementing an interface. After the keyword implements, we give the interface name, interface example. So now our imp methods class has made a promise to Java that we are going to implement whatever abstract methods have been defined in interface example. So in our imp methods class, we have defined two methods, and the method names match the method names defined in interface example. We have public void myMethod1 and public void myMethod2. But in our class, we have now given code into the body of the method. So instead of public void myMethod1 followed simply by a semicolon, as we saw in the interface, now we have a concrete method. Public void myMethod1 followed by an open curly brace, and then a print statement saying system.out.println, this is my method 1, and then a closed curly brace to signify the end of the method. Similarly, in method 2, we now have an open curly brace followed by a print statement system.out.println, this is my method 2, followed by a closed curly brace. So we've taken the abstract methods defined in the interface, and we've given them concrete implementations in our class. And then our class at the end has a main method, public static void main string args, where we would actually put our calls. And we'll see what that looks like on the next slide. And this is where we can show how we actually implement our interface in the main method. So this is a snippet or a closer look at the main method, public static void main string args. And the first thing we do in our main method is we create a new object. And the object's type is interface example. But you see we're creating the object out of the imp methods class. So we have interface example object equals new imp methods. And then we can call our methods on the object with object.myMethod1 and object.myMethod2. And those will each print out their respective print lines in turn. So we see that where at the bottom of the screen it says output, we have this is my method 1 and this is my method 2. So this is how we can use interfaces in Java. In this demonstration, I'm going to show how we can create and use Java interfaces. So first I'm going to create an interface, and then we can talk about how we would use it and why we would want to use an interface. So to get started, we're going to create an interface within our project. So on the left side of my window in my IDE, under the project pane, I'm going to right-click on my source folder, navigate to New, and we're going to click Java class. And then in my list of options, I have class, interface, enum, and annotation. So I'm going to select interface, and I'm going to call it car.java. And now we have the beginnings of our interface. You might be used to seeing the declaration look like public class and then the class name. But when we're making an interface, we use the keyword interface. So on line 1, we have the declaration public interface car. And that lets Java know we want to create an interface. In an interface, we're going to create a grouping of related methods, but the methods themselves won't have any code. So we're just laying out the method names, their access modifiers, and their types, but we're going to leave it to the code that actually implements the interface, which we'll talk about later, to make the body of the methods. So within the car interface, we want to think about what kind of methods would a car have. Well, we might have a method to start the car. We also might have a method to turn the car off or stop the car. And then maybe we'd have a method to turn the car left and turn the car right. And this completes our interface. So this is what an interface consists of: a grouping of methods without any code, just the method definitions. So we have our 4 methods: start, stop, turn left, turn right. We can see that none of the methods take any arguments, but they can if we want them to. So why don't we give a parameter to our start method? So now I've added a parameter to our start method, which is perfectly valid. It's accepting a string called keyType. And we could say that the key type is a normal key, maybe it's a push button or a remote start of some kind. But regardless, we can pass a parameter to this method now. Now that we know how we can define an interface, let's look at how we can actually use an interface. Interfaces are implemented by classes. And you can think of this similar to inheritance, but the difference is we can implement as many interfaces as we want. So with inheritance in Java, we can only inherit from one superclass. But with implementation in Java, we can implement as many interfaces as we want. So to see how we would implement this interface, let's create a class in our Java package. So I'm going to navigate over to our source folder in the left side on the project pane. I'm going to right-click, navigate to New, and then select Java class. And let's make something that would make use of this car interface. So for example, maybe something like electric vehicle would still be a type of car. We'll make electric vehicle.java. And I'm going to leave this on the class selection because now we want to create a concrete class. So here we have our public class electric vehicle as defined on line 1. We want electric vehicle to implement our car interface. So on the class signature on line 1, after the class name, I'm going to use the keyword implements, and then I'm going to give the name of the interface, car. And now our class electric vehicle is implementing the car interface. And on line 1, there's a red squiggly line underneath of our class signature because we haven't now created the methods that we've promised to create. By implementing the car interface, we have promised Java we will create every method that's contained in that interface, the start, stop, turn left, and turn right methods. So until I have those methods implemented with some sort of code behind them, I'm going to get this error. And we can have as many interface implementations as we want, we would just separate the names with a comma. So now, let's implement the actual methods. Our first method was the start method. So I've put on line 2 the signature for the start method, public void start string key type, and this matches the signature of that method in the interface. But now I need to put some code in there. So let's make our code simple. It's just going to be 2 print statements. One print statement saying you turn the car on, and another print statement saying the key type. Now let's implement the stop method. The stop method didn't take any parameters in the interface, so we don't put any parameters into it here. And we've matched the signature again, public void stop. And this will be a print statement saying you stopped the car, or you turned the car off, rather. And finally, we have our turn left and our turn right methods. So let's go ahead and implement those as well. And now we've implemented every method that we promised to implement. All 4 methods defined in the interface are now defined in our electric vehicle class, and they have code within them, so they're actually doing something. If we wanted the code to do something different for a different type of car, then the next time we implement car with a different class, we can change the code around in these methods as long as we still have all 4 methods as defined in the interface. So interfaces, we use them when we want to have some sort of structure to our code. We want to make sure that our code always has these certain methods. Regardless of what the methods are doing, we want them to have the same structure. And that can provide security by hiding certain details of the code from other elements of your Java class. And it can also lead to more structured, more manageable code bases by abstracting out the method signatures. At this point, we can use these methods in electric vehicle just like we would use any other method. We can create an object out of the electric vehicle class and then use the dot syntax to say dot start, dot stop, dot turn left, or dot turn right on that object. So that's how interfaces work in Java. Static methods are methods that belong to a class rather than an instance of the class. So what that means is you can access a static method without needing to instantiate an object first. Just having the class existing is enough to say class name dot static method, and that would call the static method. If you wanted to create an object, you can still call static methods on an object, but you don't have to. So our static methods can be used as part of a class, and static variables can also be used to define them as being part of a class. The behavior is a little bit different for static variables. That means that only one instance of the variable will ever be created. No matter how many times objects are created out of that class, there's only one instance of that variable. And we also have static blocks in Java, which are ways of statically initializing classes. Let's look at an example of a static method. In this code snippet, we have a class declaration declaring a class called staticExample. And that's on line 1 where it says public class staticExample. And in that class, just below the first line, we're declaring a static method where it says static void myMethod. So in that declaration, our first keyword is static. And that's telling Java that this is a static method. and then void is the return type of our method, and then the name is my method. And what that method does is it has a print statement, system.out.println hello world. And then that's it for our static method. Now we've defined ourselves a static method. Below that, we have a main method, public static void main string args. And here we're showing how we can call that method. And as is stated in the comment, we don't have to create an object. We can just call my method directly. Normally, you might be used to seeing something like object type object equals new object type, and then you would call object.myMethod. But since our method is static, we can just say my method, as we see here on the line below our main method declaration. In this second example of static methods, we're going to be making use of a static initialization block. So on this code snippet, we have a class called static method example, as we see defined on line 1 where it says public class static method example. And then we have two static instance variables defined in that class. On the second line, we have static int mynum, and on the third line, we have static string myString. So both mynum and myString are static instance variables that are members of the static method example class. So that means they'll only exist one time. Regardless of how many objects are created out of the static method example, they'll all be sharing the same instance of mynum and myString. So whatever the value is for mynum or myString, that value will be the same across every object. If one object changes the value of mynum or myString, then that change will be propagated to every other object as well. Below the two declarations for mynum and myString, we have our static initialization block. And that's defined on the line 4 where it says static followed by an open curly brace, and that's defining the start of a static initialization block. We simply write static and then put our code between curly braces. So right below our initialization block line where it says static, we have mynum equals 50 and myString equals hello world. So what this is doing is initializing the first values of mynum and myString. And it's important to note that a static initialization block can only be used to initialize static instance variables. So because mynum and myString are both static, we can set them in our static initialization block. And this static initialization block will only run one time when the class is first loaded, as opposed to what you might be used to with something like a constructor where it's run every time a class is instantiated. This is only run once. And then below that we have our main method, public static void main string args. And on the next slide, we'll look at what using this class and the static initialization block looks like. So here we have a close-up of our main method. We see the declaration on the first line with public static void main string args. And then we have two lines in our main method. Both of them are print statements. The first one reads system.out.println followed by the string mynum, which is concatenated with the variable mynum. And then the second print statement reads system.out.println followed by the string myString concatenated with the variable myString. And since both of these variables will have been set by the static initialization block because our class has been loaded, then they'll be equal to whatever our static initialization block set them to. In this case, mynum was set to 50 and myString was set to hello world. So at the bottom of our code snippet, we see our output below the line output, and it prints just as we would expect mynum 50 and myString hello world. This is how static methods work in Java. In this demonstration, I'm going to show how we can use static methods in Java. To get started, I'm going to create a class for us to work in. So on the left side of my IDE in the project pane, I'm going to right-click on Source, navigate to New, Java Class, and I'm going to create a new Java class called staticExample.java. And here we have the class declaration on line 1 with public class static example and the open curly brace followed by a closed curly brace on line 3, which is where the body of my code will go within my class. Let's start by defining a method that's not static, which is what we might be more familiar with. So on lines 2 to 4, I've added a standard non-static method. Public int add5 takes the parameter int n and it returns n plus 5. So to use this standard method, we would have to do the standard operation of creating an object using the static example class and then calling this method on that object. Now let's define a static method. Now on lines 6 to 8, I have a new method called add6, but it has a special keyword in the signature called static. So we have public static int add6 taking parameter int n on line 6. Now we have a static method because that keyword static makes this method static. In the body of the code, it returns n plus 6. But the difference is, with a static method, we don't need to create an object to call this method. We can actually call it directly on the class. So we could do something like static example dot add6. Let's see how this works using a main method. I'm going to create a new class by navigating over to the source folder in my project pane on the left side, right-clicking, navigating to new, and going to Java class. And I'm going to create a class called main.java. Now I have my main class with its class declaration on line 1 with public class main. And within that, I'm going to create the main method. And now we have our main method on line 2, public static void main string args. You might notice something interesting about our main method. It's actually a static method in itself. So let's start by calling the non-static method. This is what we might be more used to. So I need to create an object first of type static example to do that. Now, on line 3, I've created an object, obj1, of type static example, and then on line 4, I've made a print statement that will call add5 on the obj1 object, passing an argument of 5 to that method. So theoretically, this will add 5 to that value, and then we'll print that out. So this should print out a value of 10. This is the standard way of doing it. Now, let's look at how we can call our static method. Now on line 5, within my print statement, I've called our static method. And you can see the difference between how we call a non-static method and how we call a static method. I've called the static method by simply typing in the class static example dot add6, as opposed to how I had to do it previously on line 4, where I had to create an object and then call it on the object. So if a method is not static, I can't call it the way that I'm calling it on line 5, but interestingly enough, I can call a static method the same way that I call a non-static method. Now on line 6, I've added another print statement which actually calls our static method on obj1 instead of the class directly. And I've passed an argument of 6 to it. So both line 5 and 6 show valid uses of a static method. So when we print this out, we should see 3 lines. We should see 10, 12, and 12. Let's actually compile and run this program to make sure it looks like we expect it to. So in the bottom left of my IDE, I'm going to click on the terminal button. to bring up a terminal. I'm going to change directory into my source folder. I'm going to compile and run this program. First, I'll compile it by doing javac main.java. And now I will run the program with java main. And below java main, we have 3 printed lines, just as we expected, 10, 12, and 12. So that's how we can use static methods in Java. So in this course, we've examined how to create and use methods to manipulate the data inside a class. We did this by exploring programming with Java methods, programming with Java Accessor and Mutator methods, working with method overloading in Java, and programming with Java interfaces and using static keyword methods.